Now I request the director, Professor Sudhakar Panda of NISER Bhubaneswar, to give a welcome address.
Thank you, Dr. Krishnan. It's a great opportunity to talk to chemists early in the morning. So good morning, good afternoon, good evening, wherever you are in the globe. And I, on behalf of National Institute of Science, Education and Research, which we call shortly NISER, and sometimes I take the pride to call it NISER, I welcome you all to this second international conference on main group molecules to materials. Shortly, we are calling this as MMM2, which is being organized, as you heard from my colleague, by the School of Chemical Science of NISER. And as you heard from Dr. Krishnan, this conference, we have been planning to have it in December, and then we thought that we'll have it in the middle of 2021, December 2020, then middle of December 21, thinking that my auditorium will be ready and we can accommodate lots of participants. And I'm happy that the auditorium is ready now, but however, still the travel restrictions and in fact, the COVID guidelines in my campus is more stricter than government guidelines. I have to take care of more of things. I have a COVID task force. So only when they allow to have big scale gathering in my campus, we'll be able to get people here and have offline, not anymore virtual conferences. Because that gives a great pleasure to me to meet people from other fields, besides the whatever the academic program goes on in these conferences. And I know that there are people from Germany, France, Canada, Australia, USA, all of them are being participating here. And I just talked to my predecessor, Professor B. Chandrasekhar, who is also an advisory board as well as giving a plenary session. And so I'm happy. I really welcome. I feel like Professor Chandrasekhar is with me, besides me, in this director's office. And we'll be talking more about how to take NISER forward. And most important thing is that even if the time and space constraints are there, still, I congratulate my colleagues from School of Chemical Science to organize this meeting in the virtual mode. And I understand that there are 12 plenary talks, 20 invited lectures, 50 poster presentations by young researchers, and altogether there are 300 participants who will be attending this conference, both from India and abroad. And to encourage the people, the best poster presentation will also be awarded by the American Chemical Society as well as Royal Society of Chemistry with the directorial transactions. I wish all of you will have a good exchange of ideas, work what you are doing, and I sincerely hope it should lead to some collaborations that will make me happy, and that will also help my young faculty in the School of Chemical Science. And without wasting more time, I would like to again welcome you to NISER, though virtually, and wish this conference the best of luck, and you will enjoy the next 2-3 days discussion sessions and the lectures. Thank you very much.
So thank you very much, Professor Sudhakar Panda, Director NISER, for your inspiring words. Next, we're moving on for the next session. Now we request Professor V. Chandrasekhar, Director of TFR Hyderabad, to deliver the inaugural address.
Thank you, Krishnan and Professor Sudhakar Panda, and all people who have joined from various parts of the world. I can see some familiar names from outside, Frieder from USA, and then I can see Cameron Jones and various other people from India. So getting up or staying late, to attend this conference. So thank you all. And although I'm not in NISER, I think I still feel part of it. Therefore, I welcome all of you to this conference at NISER. And I'm so happy that Krishnan is organizing from the School of Chemical Sciences at NISER this particular conference. Now, main group elements, as Krishnan has pointed out, have had a lot of, there has been a renaissance in this chemistry since nearly 30, 40 years. And main group chemistry has taken off in various parts of the world in a big way. Firstly, from a fundamental point of view, in terms of, for example, trying to figure out whether one can put main group elements in low valence situations, low coordinate situations, situations where multiple bonds are involved, all of which was unfamiliar territory to the main group elements just a few decades ago. And the process of doing this has allowed not just new chemistry to be developed, but also our ideas about bonding got refined, chemical bonding got refined, which could be applied to other parts of chemistry as well, including the main group chemistry. But in addition to these wonderful developments, which by themselves are really very exciting, main group chemistry also had a tremendous impact in terms of, for example, can compounds of main group elements replace transition metal compounds in catalytic reactions? While this has not made much headway, but even the thinking process itself is quite remarkable, that you could have situations where compounds of main group elements can be utilized in catalytic reaction. So this is something that again is an area of extremely intense research with great possibilities and great potential. Similarly, of course, main group compounds as parts of ligands in coordination chemistry and organometallic chemistry has been for such a long time being studied. For example, like phosphines are such an integral part of transition metal organometallic chemistry that we forget. Phosphorus, which in fact plays the most important role in that, is the main playing the role for all the catalytic reactions that are now very well. And of course, as materials. So there are so many applications of main group elements in materials. Main group like boron compounds, for example, optical properties, and several such applications are there. So this is really quite timely. And also main group elements are part of macromolecular systems like polymers. The conventional carbon systems, of course, are well known for such a long time, but polymers based on main group elements have also made a tremendous impact. The most, of course, commercially important one being the polysiloxanes, but there are other polymers also which are extremely important. So therefore, the topic of main group elements in terms of their chemistry, fundamental chemistry, their breadth in terms of use in materials is something that is really exciting and taking the entire field of chemistry along with. So this is very apt that this particular conference is being organized. I hope it continues in a periodic way. Just to tell you a little bit of a history about the Indian connection to the main group chemistry. The Indian in India, when chemistry started, of course, Professor Prafulla Chandra Ray at Kolkata is the father of the modern Indian chemistry and also Indian chemical industry. So he worked on all aspects of chemistry. But after him, when chemistry began to develop at other places in the country, notably at the Indian Institute of Science, it started off, the inorganic chemistry started off as non-metal chemistry, which is now today we are calling it as the main group element chemistry. The non-metal chemistry of sulfur, chemistry of silicon, and so on. So various of these aspects have been studied. Particularly, I would like to mention the names of Professor A.R. Vasudeva Murthy. So who was a professor at the Indian Institute of Science. Today we say "Make in India" is a fashionable slogan, but Vasudeva Murthy in the 70s has and maybe the late 70s and 80s was so passionate about developing a silicon technology for India. So he collaborated with colleagues from the physics department of the Indian Institute of Science and extended this to an industry, which is Mittur Chemicals, which is just a few 100 kilometers from the Indian Institute of Science, and established the first Indian silicon technology at Mittur Chemicals. Of course, it's a different thing that better technologies have come up, and we have now technologies which are better than this. But the fact is that the connection of chemistry and connection of chemistry to translational aspects and to aspects that we today think very important in terms of being self-sufficient in particularly crucial technologies was a matter that was recognized long ago, particularly at the Indian Institute of Science and other places in India. Similarly, I would also like to mention the name of Professor D.K. Padma, who was a student of Professor Vasudeva Murthy, and later she became a faculty member at the Indian Institute of Science. The reason I want to mention her name is that she was the first person to start chemistry of fluorine compounds in the country. And she actually was the first person to be able to use a fluorine gas cylinder. And those of you who know the difficulties of handling gaseous fluorine because of its extreme toxicity and extreme the difficulties that are encountered in handling this gas. But she was extremely successful, and she took up this challenge and started this chemistry at the Indian Institute of Science. This was again in the early 70s. And then Professor S.S. Krishnamurthy, who was my supervisor, and who built a large cohort of chemists practicing main group chemistry. He, after his training from Indian Institute of Science and in England with Professor M.F. Lappert, came back to the country and set up a vibrant group of main group chemistry, particularly in inorganic ring systems. So he pioneered research in cyclophosphazines and various other heterocyclic compounds in the country, and which diversified into other areas. There are many others in the country, but I mean, these contributions I would like to remember today, particularly in the context of this conference, and since this conference started at the Indian Institute of Science, Bangalore, in terms of the contributions of these pioneers, which have led to the development of this chemistry in the country. And also now today we find, for example, that almost every major institute and university in the country has a flourishing main group chemistry research group, but we keeping in with the times of the day, this is necessarily interdisciplinary. So there you find combination of main group chemistry with other aspects of chemistry, with other aspects of material science, like photophysical sciences and so on. I myself have drifted away from main group chemistry for a long time, now focusing on a substantial part of my interest lying in lanthanide. But passion that we started off with main group chemistry remains. So happy that this conference is being organized by Krishnan, which would help not necessarily just the practitioners of this science, but also the young people in this country and probably outside who will be attending this conference to learn. It's one thing to read a paper, of course you understand, but it's another thing to actually hear it from the person who has done that work. It's completely different. And that's the reason why physical meetings, for all their inconvenience, provide this great opportunity that you're actually able to talk to persons, and that really is something that this the COVID has taken away from us. I hope that we'll get back to a situation where we can have physical meetings, where this interaction becomes possible, and that makes all the difference in terms of our understanding of a concept. Even when we read the paper, we understand some parts of it, but it's so much different when we are hearing from people who have actually done it and talking. So as Krishnan mentioned, this conference got started in the Indian Institute of Science. Professor Tilagar organized this conference along with the help of other colleagues from the rest of the country and outside. And then it was a thought that can we have this conference on a regular basis? And as Krishnan mentioned, the plan was to have it every 2 years. So 2020 was the proper time, but then we were hit with COVID. And we were thinking, when will it go? We have the first wave, second wave, and then we have Omicron. So keeping all of this, of course, it's the best thing that Krishnan has decided that let's have a meeting online, which will at least allow all of us to come together, even though all of us won't be there at the same time, given the various time zones that we are working in. but it's still a wonderful opportunity to meet all people, even virtually, and to listen to talks such interesting. So I hope that this conference really acts as a stimulus in this country, and to even drive this field and actually branch out to other parts of the science. So in today's science, it's no good to be in our silos and say that, okay, I'm a practitioner of main group chemistry, so I'll do nothing else than that. It's very important that we use our knowledge, our depth of our knowledge, and seek out to areas where it's possible to lay connections. And I think that's what this particular conference would give opportunity. And the title is apt because it starts from molecules to materials concerning main. So with this, I once again thank Krishnan for this opportunity to speak at length about this conference, and also to invite all of you to this conference again on behalf of NISER, where I was associated earlier, as Professor Sudhakar Panda has welcomed you already, and also on behalf of the School of Chemical Sciences, to which also I belonged once at NISER, and also on my own personal behalf as a practicing main group chemist. Thank you very much.
Yes, thank you very much, sir, for the nice history and inspiring words. So we'll start around 9 o'clock. We will give 10 minutes break.
Okay, so Krishnan, I will be off now.
Yes, thank you very much, sir. Thank you very much. Yeah. So we'll take a 10-minute break, and we'll start the session again 9 o'clock. Hello.
Hi, Krishnan. Ravikant. Hey, you're muted, I think.
Yeah. Hello, sir. How are you?
Yeah, fine. So we'll be starting at 9?
Yeah, 9 o'clock we'll start.
Okay. And is there any kind of time for question and answering thing? I mean, 5 minutes, 10 minutes before.
So quick questions, maybe 1 or 2 you can allow.
Okay. Including the plenary lecture, right?
Yeah.
Okay.
Good morning, Ravikant.
Good morning, sir.
So, you must be busy with activities of your department.
Yeah, learning.
By the time you learn it, the term will be over.
Yeah, no, that's what. So whatever your predecessor has done, you have to correct them for the next 2 years. Third year, you have to create problems for the next guy.
Okay.
There is the agenda.
Yeah.
Yeah, we have all these MMR drive and all. No? So,
Okay.
soon we have some selection.
Okay.
I think this time, IIT asked to take about 50 faculty members in various departments.
Okay. Good.
So you're not moving around much, or?
Yeah. I mean, I'm moving, but unless it's like really very, very, very important.
Yeah.
Yeah. Actually, I made a couple of trips to Bombay because that was I had an unavoidable side.
Okay. Not to IIT.
Not to IIT, no.
Yeah.
Good morning, sir.
Dastagiri.
Hi, Dastagiri.
Good morning. Good morning, everyone.
Hey, Bhumi, good morning.
Morning.
This is the way we can see each other, I think.
Reddy Garu, you have transformed into a macho man now. Oh, hairstyle and your vehicle.
Yeah, while Rajinikanth is out, I think this fellow will be in, I think. Huh?
Becoming old, how come I become
Becoming old. Our teachers are there. Hmm?
yeah, of course.
Morning, Frida. I mean, for you, good evening, Frida. Yeah.
Yeah, it's relatively late. Good morning, everyone.
Yeah.
It's great to see you. I wished it was in person, but well, next time, right?
Yeah, I hope so. Yeah, yeah. So how are you,
Hello.
Frida? How is your wife? You're doing well?
Oh yeah. No, we're well.
Okay.
I guess we got the worst at the beginning of last year, so
Oh, okay. Yeah.
ever since it's okay here. Yeah.
Wonderful. Good.
Yeah. Only this semester we're fully back though.
Yeah.
Yeah.
Hello, Professor Jones.
Hello, sorry.
Hello, good afternoon, Professor Jones. Sharon here.
Hello, how you all doing?
Yeah.
Hey, Frida, how you
Everyone,
going?
hello.
Yeah, been a while.
Yeah, quite a while.
So, with regard to setting up, maybe I should get my thing organized here. I'm not very familiar doing these things on Zoom. I've only done a couple in the last couple of weeks, the only ones I've done since all the problems started. So that's set up, so I should be able to share my screen, I think. Yeah, when I need to. Yeah. So what time is it there, Frida?
5 more minutes to go.
Yes, it's 10:30.
Okay,
Actually, it's
that's not
funny
too bad.
because I guess I looked at the time difference a couple of weeks ago, and I put everything in my calendar. And it turns out when I double checked this morning, the time changed by half an hour.
Right. Yeah.
So I was like, okay, I'm glad I checked on this once more. I guess in India, do you have a time change like winter time, summertime, or something like that?
No, we don't have.
No, maybe I just put
Do
it
you have
in.
West time zones?
No, we have enough difficulties without changing watches. So I think if you put that in, then we
So
would
all of
have
India
total chaos.
is all one time zone.
No, I mean, ideally we should have time zones because they like, in the eastern part of India versus the west, there is a substantial,
Sure.
difference. But I think,
Big country.
yeah, people haven't done it because they were worried about the confusion it might cause in terms of changing watches. Somebody forgets to change the watch. It's done so religiously in the US in terms of, when the spring ahead, fall back, and all of that is done, and people remind you all of that. I think it's like a tough act to do this here.
Yeah, it's all pretty confusing though, especially if you have relatives in Europe and they change the time, of course, at different time of the year. They're usually like a month ahead of time or so.
Have you been out of the US yet, Frida?
Say it again.
You've been out of the US?
Have I been out of the US? Yeah.
Over the last couple of years?
Yeah, I did a trip this summer
Mhm.
just to visit family in Germany.
Right.
Just around the time when things got a bit better there.
Mhm.
I guess now probably there's restrictions back in place, so it was good to go that time.
Sure.
And
So
I
I
did go
noticed
to a live conference recently.
Did you? All right.
Yeah, yeah. Take a guess in which state of the United States.
Texas?
Texas it is.
I don't know. Which one?
Texas.
Oh, it was Texas. Right.
It was
Good.
Texas. Texas it is. Yes. It was good though. It was nice to reconnect with folks.
Uh-huh. Yeah. Did you go to A&M?
No, it was in Austin.
Ah,
The ACS regional meeting. Main group symposium.
Oh, yeah. I saw that one. Yeah. That was, who was running? That was
Todd Hudnall.
Todd, that's right. Yeah.
Good morning, folks.
Good morning.
Good
Morning.
Good morning.
Morning.
Yeah.
So Sharanappa, Krishnan, all set?
Yeah.
Thank you.
Everything's set.
Yeah.
Yeah.
Thank you. I'll say, please.
Okay, we'll start. So the first session will be chaired by Professor Ravikant, Head of the Department, IIT Bombay. So I welcome Professor Ravikant.
Yeah. Thank you, Professor Krishnan. So first of all, good morning, good afternoon, maybe good evening to all of you. And I take this opportunity to thank both Professor Krishnan and Professor Sharanappa, along with his team at NICER, for giving me this opportunity. So in this session, we have 3 talks, 1 plenary lecture and 2 invited lectures. So the first plenary lecture is given by Professor Cameron Jones of School of Chemistry, Monash University. So I just give a very brief introduction of Professor Jones, which all of you, of course, is a well-known person. So he obtained his PhD from Griffith University, Brisbane in 1992. And he has done a postdoc at Sussex University under Professor John F. Nixon. And he took up a very brief lectureship at the University of Wales. Then he continued readership at Cardiff University, where he was there for a long time. And he is also a founder and co-directed the Center for Fundamental and Applied Main Group Chemistry. In 2007, he moved to Monash University as a R.L. Martin Distinguished Professor and a Director of Monash Catalysis Initiative. See, of course, no need to say that he has won several prizes and fellowships. He is a inaugural Thomas Powell Heap Foundation Hegler Institute Chair for Science at Texas A&M University. And he was a Senior Research Award from Alexander Van Humboldt in 2008, which he went back in 2017, and is an elected fellow of several academies that includes Australian Academy of Sciences, Royal Society of Chemistry, and so on. So today's talk is on highly activated magnesium 1 compounds, powerful reagents for small molecule activations. So with this brief introduction, I invite Professor Jones to give his lecture. Thank you.
Okay, thanks very much. I suppose I need to share my screen. Got to share the right one, I suppose. So, can you see that?
Yes.
Yeah.
I just want to get rid of this thing at the top. Okay, I'm going to move that out of the way. Sorry, figure this out here. Okay, well, thanks, Mr. Chairman, for the kind introduction, and thank you to the organisers for the invitation to come here virtually to NICER in Bhubaneswar. It would have been great to be there in person. Hopefully I can be one day. So today I wanted to really give you an idea of one area of chemistry we've been looking at over the last 5 years or so. And this is really an extension of chemistry we developed way back in 2007, where we developed the first examples of magnesium-1 compounds. And these are compounds that contain a magnesium-magnesium covalent bond. And in this case, this compound is kinetically stabilized with respect to disproportionation by this bulky beta-diketnomate ligand. So these, I think, have some fundamental interest, but since 2007, we've pretty extensively developed the use of these systems as what we like to call universal reducing agents in inorganic and organic transformations. And in fact, I think we've shown that we can use these compounds, or these have a lot of advantages over classical reducing agents like alkali metals, potassium graphite, etc. And you can access compound types that you just can't access with those classical reducing agents. But more recently, we began to become interested in trying to reduce or reductively couple enthalpically strong small molecules like carbon monoxide, dihydrogen, dinitrogen, etc., to build up value-added products from these small molecule substrates. Now that's all well and good. It's carried out by a lot of transition metals, as I'm sure you know, but unfortunately, most of these small molecule substrates don't react with these normal magnesium-1 compounds that we've initially developed. So we had to develop a range of highly activated examples of such systems. I'm going to tell you about our work today. For example, reductively coupling carbon monoxide to form an arene, such as this beautiful compound here, which I'll talk about a little bit later. So this area of chemistry lies with a more broader area of chemistry that deals with, as it's been mentioned in the introduction, trying to find effective replacements for toxic and expensive transition metals in a range of synthetic and catalytic transformations. And that's really an area that we're looking at, although most of that work has been dealt with with low-valent P-block systems rather than these low-valent S-block systems. But before I go into that, I just wanted to give you a bit of a brief historical overview of the chemistry we've carried out in this area. So first of all, the first examples of magnesium-1 compounds, or the first example, was prepared back in 2007, as I said. And this was this system here that's kinetically stabilized by this bulky beta-diketnomate, this bulky guanidinate group. We can simply prepare that by reducing a magnesium-2 iodide with an alkali metal to give this compound in low to moderate yield. It's pretty thermally stable. So this was part of a study. We were looking at the analogies between guanidinates and bulky beta-diketnomates, this type of ligand here, which I'm sure this audience is very familiar with. So we thought we could perhaps form compounds like this as well, analogues of this system here. And that proved to be the case. We could simply prepare these very easy to make magnesium-2 iodide systems, produce with potassium metal, and give good yields of this, for example, this compound here. Extremely thermally stable, these compounds don't decompose until temperatures in excess of 300 degrees Celsius, and they normally have an unsupported magnesium-magnesium bond of about 2.85 angstroms. Well, since those first preparations, there's probably been about 40 or so other magnesium-1 compounds come forward. The vast majority are 3-coordinate systems. They have chelating, end-donor, anionic ligands stabilizing the magnesium-magnesium fragment, and their further chemistry is not dissimilar for all of these systems here. You can form higher coordinate systems. For example, the electrophilic magnesium centers in these compounds will form simple adducts with simple Lewis bases, such as these 4-coordinate systems here. And this type of compound will become important a little bit later on. You can also form adducts with organic fragments, such as this diphenyl ketene system here, interestingly. So you might expect that if you wanted to increase the reactivity of these compounds, you could perhaps form even less coordinatively saturated systems like 2-coordinate systems. And we spent a lot of time trying to prepare such compounds, and we achieved that. We had to develop these extremely bulky amide ligands that I show here, and we did manage to kinetically stabilize such systems as this here. They are much more reactive, but unfortunately they're a little bit more difficult to prepare and handle. So we were really looking at other ways to activate these systems, which is what I'll talk about today. Now, not our work, but it would be remiss of me not to mention very recent work from Serd Harder's group, who's extended this work to the preparation of magnesium zero compounds with magnesium in the zero oxidation state, remarkably. And this is simply achieved by using a bigger ligand. So if you can make a big enough ligand, you can stabilize anything, it seems. This is the bulky NAC or beta-diketamate ligand developed by Harder. He reduced this system with this suspension of 5% sodium on sodium chloride. And this is actually a reducing agent we developed a couple of years ago. It's proving to be very useful by a number of groups. So remarkable compound, anionic magnesium zero compound, not terribly thermally stable. Will decompose partially, interestingly, in one case to give this beautiful mixed valence magnesium 1, magnesium 2 system. Now, I'm not going to talk about magnesium zero systems. As you know, I'm going to talk about magnesium 1 compounds. So I think before we go any further, we need to look at the nature of the magnesium-magnesium bond in these dimers. We've carried out a whole range of experimental and theoretical studies over the years, and I think it's fair to say that these compounds are best described as containing a covalently bonded dimagnesium dicationic unit that has an ionic interaction, in this case with beta-diketamate anionic ligand. Interestingly, when you look at the experimental charge density studies, you see that the charge density between the two magnesium centers is really quite diffuse, and the density is not dissimilar to that's been calculated in a disodium molecule. And this would suggest that these compounds really hold their electrons quite loosely and could deliver them quite easily to a coordinated substrate. And that indeed proves to be the case. The HOMO is the magnesium-magnesium sigma bond. The LUMO is an empty pi orbital between the two magnesium centers here. And the HOMO-LUMO gap's pretty high at about 4 electron volts. So as I said, these systems have been used widely by, I don't know, 50 or so groups around the world now, I would imagine, as reducing agents in further chemistry. So why would you use these systems and not the more classical reducing agents, many examples of which are readily available? Well, first of all, we've carried out a whole range of electrochemical studies, and we haven't been able to nail down the redox potential of these magnesium-1 compounds because their reduction and oxidation is not reversible. But we imagine it's going to be something around that has been recorded for magnesium metal, about minus 2.7 electron volts. Now, these compounds have a whole range of unique properties which really lend them to the cause of use as what we call universal reducing agents, as I mentioned. Firstly, you can make them on large scales in high yields, greater than 10 grams at a time. As I said, they're very stable, thermally stable, not terribly air sensitive. They're soluble in a whole range of organic solvents, so you can dissolve them and use them to deliver electrons to a substrate in a stoichiometric, selective way in a one-phase system. A lot of reducing agents, solid reducing agents, you get over reduction problems. That's not the case with these systems at all. So you can do this in a stoichiometric sense, as I've said, and they're also safer. They present less of a fire hazard than, say, potassium metal. Moreover, you can alter their reducing ability simply by altering the steric bulk of these aryl substituents. So the bigger the aryl substituent, the less reducing they appear to be. So I just wanted to go over just give you a very brief overview of some of the work we've done using these as reducing agents in inorganic and organic synthesis before I move on to small molecules. And most of that work has lain with a low-valent group 14 compounds. And this is an area of chemistry that's studied widely in India. So you can use these compounds to access a whole variety of low oxidation state group 14 compounds simply by reducing a group 14 halide precursor with a magnesium bonded system. Just some examples here. You can form a group 14 element 0 compound simply coordinated by NHCs, and these can act as sources of the element, soluble sources of the element. You can prepare element bonded systems, such as these 1,2-dicarbene analogues or heavier analogues of 1,2-dicarbines, such as here with an amaginate ligand or a bulky beta-diketamate ligand. If you use one coordinate ligand, you can even form the valence isomers of these systems, that is the heavier analogues of alkynes. And if you use a big enough substituent here, you can frustrate this bond forming, and you can even isolate a stable, neutral, in this case, germanium-1 radical. So pretty universal. And this is only a couple of examples of compounds we've prepared, and the further chemistry of these are interesting in their own right. Now, group 14 is not the only area of the periodic table that we've had success, just in a few other examples. We can reduce aluminium hydride precursors to give these first example of an aluminium-1 hydride compound, which is also the first real extension of polyhedral borane chemistry to heavier aluminium. You can have mixed valence antimony clusters, soluble models, if you like, of intermetallic materials, such as this platinum tin cluster compound here. You can form very unusual transition metal bonds, which have low coordination numbers. They're carbonyl-free, even 3 metal atoms in a row, all of them 2 coordinate, very similar to Harder's magnesium-3 system. Magnesium transition metal bonded systems, very reactive in their own right, and unusual compounds such as this iron-1 system, which has the shortest iron-iron bond, still by some degree. In organic chemistry, these magnesium-1 compounds have been used as either 1 electron, 2 electron, or 3 electron reducing agents with respect to reduction of unsaturated organic substrates. You can affect reductive NN coupling reactions, reductive CC coupling reactions. You can react with CO2, for example, to give reductive disproportionation to generate carbon monoxide and a magnesium carbonate system here. And you can even activate very strong bonds, inert bonds, such as CF bonds or arene CF bonds selectively, as in this work from Mark Kremen at Imperial Chemistry. So these are just a few examples of the chemistry that we have done in the past. But as I said, we were more interested in extending this work over the last few years to the reduction of enthalpically strong molecules, especially carbon monoxide, because we thought that if we could build up these molecules to more value-added materials, we could perhaps mimic industrial processes such as the Fischer-Tropsch process or hydroformylation, etc. And that's something that we continue to work on. So where did this work all begin? Well, it began back in 2015, where we were looking at trying to build some molecules out of synthesis gas using Fischer-Tropsch-like reactivity. As you, I'm sure, are all aware, in Fischer-Tropsch you use heterogeneous transition metal catalysts to react with synthesis gas to give higher alkanes and oxygenates. So we thought we'd just have a bit of a look here. And the only trouble is both hydrogen and carbon monoxide do not react with these magnesium-1 systems. So in this early work, we cheated a little bit, and we used 1,3-cyclohexadiene as a source of dihydrogen, and that delivers dihydrogen to the magnesium molecule. The driving force is elimination of benzene, and that gave rise to quantitative yields of these magnesium hydride systems. So that's kind of nice, but when you carry out the reaction under an atmosphere of carbon monoxide, do you get CC bond forming reactions occurring, which are the initial stages in Fischer-Tropsch process? Well, in the case where you have a bulky dip 2,6-diisopropyl phenol substituent at the nitrogen center, you only get one carbon-carbon bond forming, generating this ethylene diolate type molecule here, which is interesting, but this type of chemistry had been seen before for the lanthanide equivalents of these systems. So we wondered, what if we use smaller substituents here? And we did that with 2,6-diethylphenol substituents, thinking we might be able to build up bigger oligomers, and that indeed proved to be the case. And in that case, we formed 3 carbon-carbon bonds and the formation of this magnesium cyclopropane triolate system. This has not been seen before, this type of molecule. So it was an initial indication that you could build up oligomers of carbon monoxide and other molecules through CC bond-forming reactions. Now, most of our work relies on computational studies to assess what's going on, what the mechanisms of these reactions are. And so this is typically carried out in collaboration with Laurent Moron and Toulouse. So firstly here, the initial hydrogenation of the magnesium dimer is downhill, as you might expect. the magnesium hydride then reacts with CO to give an ether 2 4-mole system, as is often the case in transition metal catalyzed Fischer-Tropsch chemistry. Then this reacts with more magnesium hydride, a second molecule of CO, to give this ethylene dialate system here that we observed experimentally for the big substituent. For the smaller substituent, this is an intermediate. So the endpoint for DIP is an intermediate for the DEP substituent. That reacts with another molecule of the ether 2 4-mole system to ultimately give the cyclopropane triolate compound here. So as I said, that was a starting point for this chemistry, and we were very keen to look at building up other oligomers of carbon monoxide, because as I said, these are some of the initial stages, or thought to be some of the initial stages in Fischer-Tropsch-like processes. So again, before I go into that, just a bit of a historical overview. The reductive homologation, so that's reductively coupling CO, if you like, has been known for nearly 200 years. Back in 1825, Gmelin showed that if you put an atmosphere of CO above molten potassium, you ended up with a range of different cyclic oligomers with a 2- charge. So these are oxygenates of carbon monoxide, either 2-membered, well, this is not a ring, but this ethylene dialate, deltate, squarate, croconate, or rhodizonate systems. But he suggested that you had a system where N equals 2, 5, or 6, but there was no real evidence for that. That was it was proved later in the 60s, but it was they didn't really have many of the tools that we have today. A bit later, Liebig found that if you used even hotter molten potassium, you could reductively hexamerize CO to give this beautiful 6-membered ring, benzene hexalate, where the charge on the ring is 6-. Now, this hasn't been seen since. This was just a thought that he had prepared such a compound, but no one has done this in a molecular sense since that time. With the smaller deltate and squarates, which haven't been seen in these systems here, it wasn't really until 2006 that Cloak described in this paper that you could take a uranium-3 organometallic compound, react with CO, and end up with either ethyne dialate, deltate, or squarate systems, depending on the size of the organic substituent here. So you could selectively form these compounds by altering the size of the organic substituents here. And that was a bit of a starting point for this chemistry that we were interested in. He also showed that you could react these uranium-3 systems with synthesis gas to give methanol, albeit only stoichiometrically and not catalytically. So we wanted to see if our magnesium-1 compounds could do similar chemistry, and that would be great because uranium-3 is very toxic. It's radioactive. It doesn't have NMR handles as well. So if we could do it with magnesium, that would be a big advantage. However, as I've told you, the magnesium-1 compounds that we originally developed don't react with carbon monoxide. So we had to come up with some activated systems, and we drew some inspiration from diborane chemistry. And it's well known with diboranes, if you react with one equivalent of a Lewis base, you can activate the systems, which are unsymmetrical, make the boron-boron bond polarized. And that, in fact, proved to be the case with these magnesium systems here. You can take a whole range of these compounds, simply react with one equivalent of a simple Lewis base, like N-heterocyclic carbene or pyridine, and you get a polarization of the magnesium-magnesium bond, making the 3-coordinate end nucleophilic. Moreover, the magnesium-magnesium bond length increases by about 0.2 of an angstrom, which is remarkable lengthening, and we believe that adds to the increased reactivity of these systems as well. Computational studies prove that we do get this polarization of negative charge towards the 3-coordinate magnesium center here. But are these compounds more reactive than their 3-coordinate counterparts? Well, it seems that they are, because we can take a range of these activated systems, put them under an atmosphere of CO, 1 atmosphere at room temperature, and we get very good yields of, in this case, this deltate type compound quite readily. These systems are easy to crystallographically characterize, and this chemistry is very similar to that of Cloak's. So that was a nice start for us. this type of chemistry hadn't been seen before for a main group element at all. So we thought, well, let's look at the mechanism of this reaction. Is the formation of this one-to-one adduct important? It seems it is, because the initial stages of the reaction involve CO coordinating to the 3-coordinate end of the magnesium dimer. That inserts into the magnesium-magnesium bond to give a system such as this. This reacts with another molecule of CO to give this C2O2 2- fragment. Now, this is not linear. It's not an ethylene ethine diolate. It's what we call a zigzag intermediate, and it seems to be very important in these reactions. Okay, so this is a reactive intermediate which we found can react with another molecule of CO to ultimately give the the deltate system that I show here. We calculated this ethine diolate is unreactive towards carbon monoxide. So like Cloak's work, we wondered if we could change the sterics of our magnesium system. Perhaps we could alter or selectively prepare other oligomers of carbon monoxide, reductive or reduced oligomers. And that proved to be the case as well. So we thought, well, that initial system had dip substituents at the nitrogen centers. If we use the smaller mesotyl or xylyl substituents, we can form a one-to-one adduct, place under an atmosphere of carbon monoxide. We believe we are going through a zigzag intermediate again, but instead of this reacting with a third molecule of carbon monoxide, what occurs is that you get an interaction of this CH fragment on the of this pyridine with this carbon center here, and you get CH activation to give an ethylene diolate system such as this. Okay, I should point out that Mike Hill has very recently formed an ethine diolate with another an ionic magnesium-1 compound that he has prepared in his laboratory. Okay, again, these compounds are crystallographically readily characterized. So what's going on here is the sterics here allowing us to access dimerization instead of trimerization products. Well, the theory again suggests that's the case. Again, the reaction goes through a zigzag intermediate. So I've left out all the stuff that leads up to this zigzag intermediate. This allows a close interaction between the CH fragment and the pyridine with the C2O2 fragment. Ultimately, this leads to a range of rearrangement CH activation processes to give the observed ethylene diolate product. Now, this is the thermodynamic product, and the deltate, which could have occurred, that seems to be the kinetic product, because when you calculate that reaction of the zigzag intermediate with CO, the barrier here is lower, but the thermodynamics of the ultimate product are more favorable for this product here. So that's one way that we've activated these magnesium-1 compounds, simply by forming one-to-one adducts. We have found another way, and that is by using heterobimetallic cooperativity, using our main group magnesium-1 compounds in the presence of transition metal catalysts in low oxidation states. We have looked at a range of these systems, but in this case, we've had most success simply with molybdenum hexacarbonate, a very simple molecule. And we found that this heterobimetallic cooperativity can allow us access to really unusual compound types, such as this beautiful benzene hexalate compound here. So if we take magnesium-1 systems, react with carbon monoxide simply at room temperature, in the presence of this catalyst, we can end up with the hexamerization of carbon monoxide to give a relatively good yield of this benzene hexalate system here, which is the direct analog of what Liebig suggested that he had formed nearly 200 years ago. So this is really the first well-defined reactivity that gives rise to such a system. And this is the crystal structure of the compound, which I think is really quite nice. It's worth mentioning that Liebig, when he first carried out the reaction between molten potassium and carbon monoxide to give his benzene hexalate, it has been suggested that that molten potassium was contaminated with small amounts of transition metal impurities, and that was actually acting as a catalyst in that reaction. This might actually be an indication that there is some truth to that. So the mechanism of the reaction, again, what we can see why we need the molybdenum carbonate there, because this system, as we said, doesn't react with CO. The barrier here is quite high to CO insertion. But if you take one of the carbonyl, terminal carbonyl ligands of molybdenum hexacarbonyl, that can insert into the magnesium-magnesium bond to give a system such as this. You can then get activation of two other coordinated molybdenum carbonyl fragments to end up giving a trimeric system such as this, which can then dimerize to give a tetra anionic system, which can then be reduced finally with an excess of magnesium 1 to give the overall product. So that's two ways of activating magnesium: Lewis base adduction, if you like, and also heterobimetallic cooperativity. But what if we use a combination of those methods? And we've done that to try and build up even different oligomers of carbon monoxide. And very recently, we've done this by taking an adduct of one magnesium compound in the presence of catalytic molybdenum hexacarbonyl under a CO atmosphere. And this is the same complex that forms the deltate in the absence of the molybdenum carbonyl. But in the presence of the molybdenum carbonyl, you end up with a square complex, and you selectively get square formation. Now, this work is really quite recent. We're carrying out theoretical studies at the moment, so I don't have any reason for why we have this selectivity yet. So that's some of the work we've been doing with carbon monoxide, but we're also interested in alkenes, and indeed coupling alkenes to carbon monoxide and indeed hydrogen in hydroformylation type reactivity. I'm going to move on to that now. And this work began back in 2017 now, where we were looking at the reactions of alkenes with magnesium 1. Typically, they don't react. So we use this activated alkene, diphenylethylene. And interestingly, we found that this undergoes a 1,2 addition reaction with magnesium 1 to give this system here. So that's kind of nice. This is actually quite an interesting compound because you can consider it as an acyclic 1,2 digrignard reagent. And such acyclic digrignards in a 1,2 sense are unknown, and even though people have been trying to make them since the days of Grignard. So they have a high charge density and they should be reactive species, and that indeed proves to be the case. But perhaps more importantly, this reaction is rapidly reversible at room temperature, and there's an equilibrium involved here. You get about 20% of this and 80% of this at room temperature. And a Van't Hoff analysis suggests that the reaction is pretty close to being thermoneutral. The equilibration process also is very rapid, so it would suggest that the barrier for this reaction is really quite low. And that made us wonder if the intermediate in this reaction could be a monomeric magnesium 1 radical. And this is a compound type that we've been trying to prepare for some time. And we thought, well, if that's the case, this should activate our magnesium 1 compounds, for example, to reaction with dihydrogen. These systems don't react with hydrogen. We thought these might to give a magnesium hydride. So we took this equilibrium mixture, put it under an atmosphere of dihydrogen, and indeed we did get this magnesium hydride species, but only about 50% of it. The other 50% product was this magnesium alkyl. So that suggests that a different reaction is occurring rather than going by a magnesium 1 radical here. That proved to be the case when we looked at it computationally. We found that firstly, insertion of the diphenylethylene into the magnesium-magnesium bond is close to thermoneutral to give this system here. It's barrierless, so that's in line with the experimental rapidity of the equilibrium process. Instead of a magnesium 1 radical, we think the reaction goes by a sigma bond metathesis type reaction to give this magnesium, or to spit out the magnesium hydride and give this magnesium alkyl. Now you might see that this could perhaps undergo a beta hydride elimination to give another molecule of the magnesium hydride species, but this barrier here is too high for that to occur. So we wondered, well, if this is a reactive species, perhaps we can couple it with other small molecules. Will this system react with carbon monoxide, for example, this alkene CO coupling? And indeed it does. You put this mixture under carbon monoxide, you end up with coupling to give this cyclobutene dialect system that I show here. Okay? And I won't go into the mechanism of that reaction in any detail. You can couple inserted alkenes with other alkenes. So for example, here this GPE that's inserted will couple with ethylene to give very selective this butane-diol system here. You can do the same with ethylene itself. When you have a Lewis base presence to activate the magnesium-1 system, you can end up with this butane-diol system that I show here. So you can couple selectively or selectively dimerize alkenes. You can couple them with CO and a range of other reactions as well. Again, what is important here is that you have to have initial coordination by this Lewis base to activate the magnesium-1 compound. The ethylene that can then coordinate to the magnesium center here. It can then insert into the magnesium-magnesium bond to give this system here, react with a second molecule of ethylene to give the final product. So we've got different ways to activate these magnesium-1 compounds: Lewis base adduction, heterobimetallic cooperativity. We have another way now, which is something that we've looked at quite recently. That's the photochemical activation of magnesium-1 compound. So the magnesium-magnesium bond here, it's not terribly strong, it's not terribly weak either. It's about 45 kilocalories per mole. We wondered if we irradiated these compounds, could we generate in situ these magnesium-1 radicals by magnesium-magnesium bond cleavage? That proved to be the case, I think, because these systems are stable in benzene, but when you irradiate them, even with blue light or UV light, you end up with very high yields of a double product in which the benzene is doubly reduced. So it's like a birch-like reduction product that I show here that can be isolated and crystallographically characterized. You heat these further and you can generate magnesium phenyl and magnesium hydride. So this is the formal CH activation of this inert array, okay? So that was kind of nice. And we thought, well, could we do that with other inert arenes? And we looked at a whole range of different systems, for example, toluene and the isomers of mesitylene. And we found in all cases, irradiation simply with blue light generates quantitative yields and with complete regioselectivity, these CH activated products that I show here. So really remarkable chemistry that we're extending now, because the activation of CH activation of inert arenes is really important in pharmaceutical production, for example, and it's typically always carried out with transition metal systems. I won't go into I'm just looking at the time. I don't know how much time I've got. I'm running a little bit late here, so I won't go into the mechanism of the reactivity here, except to point out some potential experimental evidence for the cleavage of the magnesium bonds in these systems. So we've taken these compounds, taken frozen solutions of these compounds and irradiated them with UV light at very low temperature and taken their EPR spectra. And indeed, you do see a signal. It's not the prettiest of spectra, but we can simulate these systems as being magnesium-1 radicals. There is a little bit of something else. There's another paramagnetic species there, but we're looking at that in more detail now. You might expect that if you took mixtures of two magnesium-1 compounds irradiated with blue light, in this case, you might get a scrambling reaction occurring if the reactions are occurring via magnesium-1 radicals. That indeed is the case. You end up with this scrambled system here almost quantitatively. The reaction is quite rapid and very clean. It's about 50% over after about 1 hour's radiation. So just one more slide here before I finish, because I haven't talked about the activation of dinitrogen yet. That is something we are looking at. We've started looking at it. It's difficult to do. But because we found that we took carbon monoxide coordinated to a molybdenum center, we could reduce that. The molybdenum was activated. We wondered if we could do the same with dinitrogen. And the system that we decided upon was this system here developed by Kit Cummins at MIT. And we found that if we can react this molybdenum-3 system with our magnesium-1 compound in the presence of a In heterocyclic carbene, we can indeed get reduction of the coordinated dinitrogen to this molybdenum-2 system here, and we can quench this system with electrophiles to give functionalized dinitrogen molecules, such as this system that I show here. And I'm sure that you could do that with a bunch of other electrophiles as well, but that work is in its infancy. So I'm really struggling to see how my time is going here, but I think I am well and truly out in a couple of minutes. So if we want to draw some conclusions, I think firstly that would be the magnesium compounds really are universal and very useful reducing agents in both organic and inorganic synthesis. You can activate these systems simply by adding Lewis bases, radiating these systems or using transition cooperativity. I certainly think that magnesium-1 compounds have been shown to be very useful in the transformation of enthalpically strong small molecules into value-added products, and hopefully that, and I'm sure that chemistry will advance as that work is in its infancy. Most of that, well, all of the chemistry I've showed you is stoichiometric, but we are looking at making it catalytic in the magnesium-1 compound by using electrochemical methods. You would think that it would be very difficult to do it in the absence of a source of electrons, and we're thinking the electrochemical method is the best way to turn these reactions over. So just to thank all the people that carried out the work. I've got a bunch of great people working. Yuvraj here carried out a great deal of the work. He's an excellent chemist. Has been with me for a few years. Albert as well from Germany was heavily involved in the work in DAFID, carried out the work on the photochemical activation of arenes. Theory, as I said, is central to all of the work that we've carried out. Laurent carried out all of the theory I talked about today. A range of other collaborators are involved in this work, some of whose names are shown here. Funding was from the Australian Research Council. Also, the US Air Force has funded us for the last 12 years or so, and I thank them for their ongoing support. And very recently, as was mentioned in the introduction, I have a fellowship at Texas A&M University who have supplied a couple of students and some funding to carry out aspects of this work. And really that just leaves me to thank you for your kind attention. Now I think I'll leave this screen up just in case someone's got a question. I don't know if I've got time for questions. Mr. Chairman.
Yeah, thank you, Professor Cameron Jones for such a wonderful talk and very unusual magnesium-1 compounds. So the talk is open for discussion.
Yeah, Sharon here. Hello, hi, Professor Cameron.
How's it going, Sharon?
Yeah, great, thanks. Very nice talk. Great, thanks, Professor Cameron. Yeah, I have a question. Is this as far as the activation of CO is concerned? For magnesium-1 compounds, right? So is this that elongation of MG-MG bond is the key thing in that?
I think it's a combination. I mean, that's obviously make the compounds more active because that bond is ready to split, if you like. But with the 4 coordinate, we have 2 molecules of the Lewis base. Those systems, their reactivity is low. So I think by putting 1 Lewis base on at one end, you're polarizing the molecule. So you have a nucleophilic magnesium center, but it's also electrophilic because it's got the potential to coordinate a substrate there, which could then be reduced. And I think that's the main reason for the reactivity or the enhanced reactivity of the base coordinated systems.
Okay, great. Thank you, Professor Cameron. Yeah.
Any more questions?
I have a question,
Yeah,
Professor Ravikant.
Yeah, please go ahead.
Hello, Professor Jones. Very nice
Hi.
talk. I'm Momita from Isopune.
Hang on a minute. I can't see you.
Yeah, so I have a question. So most of these CO coupling reactions that we come across, they are a resultant of homologation, right? So CO and then the CC combination instead of CO combination.
Yeah.
You get my point? Like I got only one or a few examples from Professor Braunschweig's group early on with the diborines, where they have activated carbon monoxide and made a COOC, so head to tail coupling.
Right. Yeah. We've seen from these reactions, which we don't believe are intermediates, but you do get cleavage of CO, and the empirical formula is the same, but the structure of the molecule is different.
So I mean, can you make some comments why it's more preferentially head-to-head coupling and not a head-to-tail coupling in most of the cases, including yours?
Because of the mechanism of reaction, where you've got this the zigzag intermediate, where the CC coupling is thermodynamically favoured, and then the interaction of another CO with that zigzag intermediate is also thermodynamically favoured. We don't, theoretically at least, head to tail coupling, if you like. You get disproportion, well, not disproportionation, but rearrangement, if you like. So you get CO cleavage, CO2 fragment coordinated to, so you get CC fragments, if you like. So we do see other products, but they're not the main product.
Okay, so you mean that computationally also you do not get this as a thermodynamically stabilized product?
We have looked at it, and it's not kinetically viable as well as being thermodynamically viable. It's mainly kinetics, I think, is the problem there, at least with our systems. I know Holger seen some examples.
Yeah. Thank you so much. It was a really nice one. Thank you.
Okay.
Yeah.
Professor Jones, so Professor Ravikant, I have one question.
Yeah. This is the last question.
Sure.
Yeah. So Professor John, this is Anukul from TIPAR, Hyderabad.
Yep. Sorry?
So actually, so I have a question. So regarding the donor coordination to magnesium bond. So when I see there is a 4 dimethyl pyridine, 2 donor can coordinate it to the magnesium bonded compound. Yes.
Sorry, say again. 2 can? Yes, they can. Yeah.
Yeah, but what would be the case if the 2 carbene coordinated to the magnesium 1 center, 2 carbene, 2 magnesium 1 center?
So in that case,
whatever I can see only 1 magnesium.
Yeah. So in that case, both magnesium centers are coordinated, and that shuts the reactivity down. You need to have 1 3-coordinate magnesium center so the substrate can come in and coordinate it, because we believe that these reductions are inner sphere reductions. So you need to have whatever the substrate is, organic or inorganic, coordinates to the 3-coordinate magnesium center, which is activated by the Lewis base on the proximal magnesium center. But if you've got both magnesium centers coordinated, they're both 4-coordinate, and the substrate can't come in and react with the dimagnesium unit, if that makes sense.
So Professor John, that 3-coordinated magnesium, that's okay. No, I'm wondering what happens if the NAC will add instead of the other chelating, that NAC. Because one NAC, there is an elongation of the magnesium bond. So
correct.
What is that another NAC can cleave the magnesium bond compound?
Can cleave it, did you say?
Yeah, because when you have a 1 equivalent magnesium.
Yeah, okay, I get it. I get the question. Yeah. So we've seen with other Lewis bases like pyridines, you can coordinate 2 pyridines to the magnesium. So you've got magnesium diamond, 2 pyridines, but with NAC, the stronger donor, and we do believe that you are getting cleavage, because if you put 2 equivalents of the NHC in, you end up with a bit of a mess. But you can see that you've got NAC magnesium with an NHC coordinated and some other fragment that's probably generated from a radical process. So yeah, that is true. Okay. So if you put 2 equivalents of an tetramethylcarbene in, for example, we do believe we're getting cleavage of the magnesium bond. Okay. But it's not very controlled. It's not a controlled source of radicals, if you like.
Okay.
Okay. Thank you. Because
Thanks, Professor Jones.
Yeah, because of time constraint, we will not be taking any more questions. Please join me in thanking Professor Cameron Jones for a wonderful talk. And now we'll move on to the second speaker of today's morning. Invited lecture by Professor Shabana Khan from IISER, Pune. So Shabana got her PhD from IIT Delhi in 2008. And then she did a couple of postdocs, with Professor Albert Roeski at the University of Göttingen, and a second postdoc at Max Planck Institute for cold research with Professor Manuel Alcarazo. And she joined IISER Pune in 2013. And she is, of course, received this year CRB Power Fellowship Award. And she's also an advisory board member of European Journal of Inorganic Chemistry and Asian Journal. And our title of talk for today morning is Access to Cyclic Alkyl Amino Carbons, Stabilized Stable Cold Nanoparticles. Dr. Shabana Khan.
Yeah, thank you, Professor Ravikant, for kind introduction. And today I'm going to talk about the CAC carbene stabilized gold nanoparticle. But before I begin my talk, I would like to thank the organizers of MMM conference to give me the invitation, which is enabling me to present my talk today. And I would also like to acknowledge my students, especially the work today I'm presenting is done by Mashaki Ghosh, and in the collaboration with Professor Pramod Pillai and Dr. Shri Kumar Kurungut, who help us in the nanoparticle synthesis and the electrocatalysis part. And of course, the funding agencies also for providing us the generous funding, which makes us to work in our laboratories. So I work in the area of inorganic chemistry and main group chemistry also, which includes catalysis some part. And my major interest is in the tetraylines, which is actually carbene, silylene, germylene, and stenylene. Utilization of them as a ligand in transition metal chemistry and their application as a catalyst in some organic transformations. Very recently, we have started a very new field, which is the use of tetraylines as a ligand in nanoparticle chemistry. So today I'm going to talk about this first result from this area. So before I begin the talk, I would like to give a brief about the gold nanoparticle, because we were interested to prepare the gold nanoparticles. And gold nanoparticles have gained a lot of attention in recent years because of the ease of preparation, and as well as their very broad application in different fields, from organic photovoltaics to sensory probes to therapeutic agents, drug delivery, electronic conductors to catalysis. And they range somewhere from 1 nanometer to 8 micrometer. And they have a very particular characteristic color, wine red. And usually their stability and dispersity of them in the solution plays very important role in the applications. And most of them are not soluble or well dispersed. And therefore you require some functionalization over the surface by using different ligands. Most commonly is thiols and amines and some surfactants to provide them extra stabilization, which makes them better for the catalytic application further. So these are some common ligands which are being used to stabilize the gold nanoparticles. And usually the properties of the gold nanoparticles can be tuned by changing the surface size and shape. So there comes the role of the ligand also. So since we work on the tetraylines like carbene and silylene, germylene, and they have a pair of electron with an empty p orbital, that makes them ideal candidate as a donor ligand. So first we looked at the literature that how is the status of the N-heterocyclic carbene, which is very popular ligand in organometallic chemistry, inorganic chemistry as a coordinating ligand, as well as in many transition metal complexes and organocatalysis. So we looked at the literature and we found there are plenty of reports on N-heterocyclic carbene where they have been utilized on the surface of the metal nanoparticles. And there are many reports on the gold nanoparticle synthesis also where N-heterocyclic carbene is utilized. So these are some very selected reports where N-heterocyclic carbene is utilized to bind the metal surface. This is one of the report by Matusi, where they have recently showed the mono versus multidentate ligands on the gold nanoparticle surface. This one is by the Johnson group. There they use the combination of heterocyclic carbene and thiolate and prepare the gold nanorods. And this is a report by Cruden, where they utilize the bidentate carbene ligand and prepared a very stable multidentate NHC gold nanoparticles by utilizing the two different synthetic protocol. This is another report where the N-heterocyclic carbene has been utilized to make a nanoparticle of different sizes. These are two very important application of the NHC gold nanoparticles, which is in the electrocatalysis. This one is the MES carbene stabilized gold nanoparticle, which was utilized by the group of Chang, and they showed the CO2 reduction by these gold nanoparticles. And in this paper, they showed that when the NHC, the MES carbene is bound to the metal surface, the efficiency of that nanoparticle is much more higher as compared to the parent gold nanoparticle. And this one is the another example where the nanoparticle is bound on the polymeric surface, having a carbene as a donor site. And that is also showing a selective CO2 reduction because of the enhanced sigma donation of the NHC on the surface, which actually makes the surface electron rich. So with this information in hand, we thought if NHC can act as a ligand to stabilize the nanoparticle, gold nanoparticle, why not CAC? Because CAC is the one which comes in the category of the stable singlet carbene, which was developed by the group of Bertrand. And since the one nitrogen of here is replaced by the carbon, that makes the HOMO-LUMO gap quite lesser. And that's the reason the CAC has been very much well known to activate many small molecules like hydrogen, ammonia, and as well as they can stabilize several reactive species. And they also have several examples in the metal catalyst. So that was the main motivation to pick up the CAC as a ligand and see how we can stabilize the gold nanoparticle. Before beginning our work, we first looked at the literature and we found there were only very few reports where the CAC ligand was tried for the synthesis of the nanoparticles. Rather, that was a serendipitous. So these are the two contributions, one from the Maurice Bullock and one from the group of Glorious. And in both the cases, they were utilizing CAC supported rhodium molecular catalyst for the arene hydrogenation. And during the process, they observed there is a formation of some solid particles, which they probed for the analysis that what actually it is. And they figure out there is a formation of a rhodium nanoparticle where the CAC protonated carbene was present on the surface. And similar observation was made by Glorious. He also utilized the same type of rhodium catalyst. And he found that during the course of the reaction, that CAC is actually modified to these protonated iminium salt as well as the CH2 group here. And these are present as a modulator on the surface of the rhodium nanoparticle. So these are the two reports where actually the CAC ligand was initially present in the precursor, but after during the course of the reaction, the reduction method, there are no more carbene on the surface of the nanoparticle. So this is a very recent report. This is actually only available report by the group of Glorious, where they further used the CAC CO2 adduct, and they deposited it by heating under vacuum on the gold and silver and copper crystals. And this is the very clean formation because that was they confirmed from the XPS also that there is a one type of nitrogen is present, binding is present, which comes in the 400.7 electron volt. Because in the previous case, when they used the reduction method, there was the decomposition of the carbene, and therefore there was no presence of the carbene carbon on the surface. So this is the only available CAC carbene on the metal surface, which actually sets some kind of an reference for us to look for the comparison with other system. So usually N-heterocyclic carbene-based nanoparticle synthesis has two types of methods of preparation, which involves a top-down approach, where the ligand exchange is done with the preformed gold nanoparticle, which is usually dodecane thiol or olailamine capped nanoparticle with a defined the particle size. And another one is the bottom-up approach, where you have a metal halide precursor and you do the reduction with different reducing agent to get the desired nanoparticle. So this is the one report by Cruden where they have used the bidentate carbene. So they adopted both the methodologies, the top-down and the bottom-up, and they isolated the multidentate MHC gold nanoparticles. So since we have already seen this, there is a decomposition in the reduction method, though we were not aware when we started. We started with the top-down approach, and we picked up a pre-formed oleolamine capped gold nanoparticles, and we did the ligand exchange with the CAC carbene, and we isolated the gold nanoparticles. And the first data which we collected was the UV visible spectrum, which shows a lambda max X525 and a wine color, which is actually the characteristic of the plasmonic color of the gold nanoparticle. So that confirms there is a gold nanoparticle. There is a little shift when we compared with the oleolamine gold nanoparticle, but then since the solvent is different, so we are not sure that how much exact shift is there. But then that was certain there is a gold nanoparticle in the system. So it's very important, since we have seen in the previous case also that it's very important to prove that carbenic carbon is attached to the gold still after the exchange. So we have done a few characterization to confirm that. So first we did the FTIR for the CAC ligand and the CAC ligated gold nanoparticle, which was the methodology adopted by Kaos and co-workers here. You can see they have recorded for the free carbene, gold nanoparticle as well as olein nanoparticle, and matched the fingerprint region to tell that there is a backbone of the carbene is present in the gold nanoparticle. So same way we also recorded the IR for the CAC as well as for the CAC gold nanoparticle, and we matched the region and we found that there is a backbone of the carbene, the CAC carbene is present, and this is specifically for the CH stretching of the isopropyl group, though it's a little broad, but then if you zoom in a little bit, you will see there is an almost similar match to this group. So this confirmed us that there is a presence of the CAC group there. So we further needed to confirm whether the carbenic carbon is there or it is protonated one. So this is before we went for the XPS analysis, we recorded the 10 images for that. And we found that there is a nanosphere present, which has a particle size of 5 to 7 nanoparticle, which was actually present in the oleolamine cap nanoparticle also, because that comes, the preformed nanoparticle range is 5 to 7 nanometer. So usually when you are doing the ligand exchange method, then there is a high chance that your particle size is intact after the ligand exchange. So to confirm that, we further recorded the XPS data, and we looked at the nitrogen, carbon, and gold binding on the surface, and we compared it with the existing literature to make sure that there is the carbenic carbon on the gold surface. So this is the nitrogen peak binding energy, which is we got as a 400.55 electron volt, and for carbon, we got it 285.35, and for gold, usually it comes the two. You see the two peak here for two different because of the spin orbital coupling. And usually we compare it with the 7/2 one because it's a low energy and is more prone for the changes in the electronic environment. So when after getting the data, we compared it with the literature because we did not have any precedence before. So we looked at the different binding energies reported by the people, and then we found there is a very good comparison by Camden and co-worker in this paper, and they have compiled this result and shown that carbon 1s binding energy for carbene comes in this range 284.9 to 285. And the same, so this is actually matching with what we got for the carbon, so 285.35. And gold also comes in the range of 84.1 to 83.96, and we also got 84.33 in the same range. And nitrogen binding is also reported for the carbene, which is present on the surface, is close to 400.7, 400.2, and exactly for the CAC was observed by the group of Glorious, that 400.7. So that actually confirmed there is a presence of the carbenic carbon on the gold surface. So once we got this confirmation, we further looked for the stability of the CAC gold nanoparticle, because if you want to do the catalysis, it is very important to understand that how stable these nanoparticles are. So usually the DDT, the dodecaine thiol, is being used to check the stability. So we looked at the literature and found there were two reports. One is this polymer modified gold nanoparticle, and one this is polymeric, the polycarbene cage. So in both the cases, they have used DDT to see that how stable their nanoparticles are. So in this case, you can see that after 1 hour, there is a slight decomposition in the peak. So, but when you look at this cage one, you will see even after 5 days, there is no change in the peak. So the cage nanoparticles are much more stable as compared to the polymeric one, which is expected because this is an encapsulated one. So then with the same method, we also did the DDT test to see the ligand stability. And we found till at least 12 hours, at approximately 12 hours, we started seeing the change in the peak position. That means there was some changes on the surface, which actually continued to 48 hours. We recorded it to up to 2 hours. So that tells that this is stable, perhaps up to more than 8 to 10 hours, but then it start having the changes in the surface. So comparatively, it is more stable than the polymeric modified gold nanoparticles, but of course, it is less than the cage gold nanoparticles. So since with this information in hand, we were further interested to see that how, as a catalyst, it will be. So we first just picked up the model reaction, which is very much known. This is an aromatic nitro reduction with gold nanoparticles. So these are the 3 reports from the literature. This is a polymeric NHC capped gold nanoparticles where the paranitrophenol is used as the precursor for the reduction. And the same is for the cage encapsulated gold nanoparticles. And this is the ultra small one, which is where the nitrophenol was used as a model reaction to see the efficiency of the gold nanoparticles. So we also went for the same, the precursor first to see how our catalyst is working. And actually, it is very difficult here to compare one-one efficiency because the concentration and the loading, everything is different. But one thing is important here to notice that most of the reactions are done within 5 minutes. So to do the control experiment and optimization, we picked up the paranitrophenol and we did the reaction, and we found when we are doing the 220 nanomolar of the catalyst we are using, there is a consumption within 1 minute. That reduction happens. This is very clear that all the nitroarene is consumed. So we also recorded it after 10 minutes, and as such, there was no change. So with this 220 nanometer catalyst loading, nanomolar, sorry, is loading, this consumption is happening in 1 minute. So this proves that this catalyst, which has the CAC as a ligand on the surface, is actually very efficient for the reduction. We further also did with the reduction of the concentration of the catalyst, and we found this is working. However, the time which is being taken for the reduction is quite higher as compared to this loading. So we still have to probe the substrate and find out the kinetics for this reaction. So later in this part, we also did some preliminary test for the formic acid oxidation. This is an electrochemical activity to see the electrochemical activity of the CAC supported gold nanoparticles. And in this, we recorded the CV for this HCO oxidation for the olylamine gold nanoparticles, CAC nanoparticles at different concentration. And we found that for the 0.25 molar peak potential is 1.49, and there is a current density of 2.23 for the CAC gold nanoparticle, while for this same condition, the olylamine gold nanoparticle is not working fine. So this was a preliminary data which is telling that CAC gold nanoparticle is actually working better than the olyl gold nanoparticle. So as a ligand, it has a more potential to probe further for the catalytic application. And still we have to probe, because usually in the formic acid oxidation, there is the CO2 formation as the end product. But we need to confirm it by the GC, as well as we need to look for the quantification of the efficiency for a more concrete efficiency comparison. So in conclusion, we have first time utilized the CAC stabilized CAC ligand to prepare the gold nanoparticles, and we have characterized it with all the characterization data like XPS, IR, and UV, and all the and stability test also we have done, which shows that the CAC is quite stable on the surface of the gold nanoparticle. And we further also have performed the reduction of the arene nitro groups and as well as the formic acid oxidation. So there is of course a great potential for this nanoparticle to be utilized in the catalytic reactions further. So with that, I would like to thank you all for your kind attention.
Thank you. Any questions? We can take 1 or 2 questions.
Yeah.
Can I ask one question?
Yeah, please.
Yeah. So, do you have an idea how much is the surface coverage?
Actually, we have still not done that data. We have to do it. And since it's just a beginning, we first just done the characterization, but we have a plan to do it.
By any chance, is it possible in this area to do the carbon-13 NMR?
It is possible, yes. I think I have seen in the paper of the Glorious, the SES catalysis, where they have come with this 2 presence of carbonic peak. They have done the carbon NMR solid state.
My final question is that if you look at your CAC, the very design of it, that is exposed to bind one gold, because you see the substituents on the nitrogen and also the side carbon. There is a lot of methyl group, and they all are free rotation is possible. So I was wondering that to approach a surface by that carbon would be sterically more cumbersome.
Okay. I mean, you are meaning to say that we probably would be interesting to know how much is the percentage of the ligand versus the gold nanoparticles, right? If I understand correctly.
Yes, and in the same range, that why one wouldn't go for a much more long chain rather than a phenyl, isopropyl, that type of bulky substituents at the orthogonist.
For CAC, actually, there is no report as such so far. For NHC, there are many.
No, I understand. So that's what I'm looking. So do you think? Don't you think that the interaction between the surface and the carbon?
Since it is a little tricky because it's a more of an heterogeneous, and it requires, of course, expertise to understand how this ligand is binding on the surface, like what kind of binding things and how you study. So still we are just getting into that. So honestly, if you ask me, it's a very, very beginning for us. So we probably will look into that further, that how the surface is being binded with the carbene.
Okay, thanks.
Yeah.
Yeah. Any more questions?
Professor Ravikant, I have a question. This is Anantharaman.
Go ahead.
Yeah. Shabana, it's a good piece of work and congratulations for your results.
Yes, thank you.
I have questions related to, like in continuation to the last discussion. You said you don't know how much and how far the interaction between the gold nanoparticle and the CAC.
Yeah.
So one of the things, if you see it like Ananiko's paper and other thing, they all believe that the imidazolium salts are present rather than the carbene type. So to me, please.
Yeah, please, you complete the question.
To me, I do agree with that, the imidazolium model rather than the imidazolidine type of a model. So what is your understanding on this?
So there are actually reports, of course, where the imidazolium salt as well as the CH2 isotope is present. But then that's where comes your XPS data, which tells you the oxidation, this binding state of the carbon. So that tells you that how the carbon is present
XPS is not a very quantitative, right? It's just still a qualitative. You don't have
not really.
quantitative
I think
XPS,
the carbon
right?
NMR solid state can also confirm that, because that how it is the carbon 2 or carbon 4 or salt, I think that can be clarified with that one.
Yeah, that could throw some light on it. Maybe solid state
solid state carbon
could help
NMR,
you.
yes.
And second part is when you do the formic acid to the CO2, how quantitative it is?
Still, we have not reached to that one. So it's just a rough estimate that with this concentration, we are getting this much potential as compared to the oleilamine nanoparticles. So this is just preliminary data. We have to do the quantification.
Okay.
Yeah.
Okay, fine. Thank you.
Yeah.
Shabana, if you're, this is VC here. If you're looking for a collaboration on carbon-13 solid state, we have some outstanding facility here at TIFR Hyderabad. So Professor Vipin Agrawal does solid state NMR, and if you think that you need to talk to somebody, then I should go ahead.
Okay, yeah, thank you very much. Maybe it will be very helpful information for me.
Yeah, thank you, Dr. Shabana. Please join me in thanking Professor Shabana for a wonderful talk. Then we'll move on to the last speaker of this session, Dr. Tarun Kanti Panda from IIT Hyderabad. So Tarun got his PhD. Tarun, you start sharing your.
Yes.
Yeah, Tarun got his PhD from Friday University, Bali. In 2005, working with Professor Peter Royski, and he did a postdoc with Professor Matthias Stam of Technical University Brunswick, and he was a JSPS postdoctoral fellow with Professor Mashima, Osaka University. He joined Department of Chemistry IIT Hyderabad in 2010 as an assistant professor, and currently is a professor at IIT Hyderabad. This year he has received a CRSI bronze medal, and the talk, the title of his talk is Synthesis of Organophosphorus Compounds Mediated by Main Group Metal Catalyst. Hello.
So thank you very much. So very good morning. So is it visible, my screen?
Yes.
Okay, just 2 seconds. Okay, is it visible? Fine. So very good morning to all of you. Thank you, Chairman sir, for a kind introduction.
Arun,
Arun,
can you make it
full screen?
Full screen.
Is it visible?
Yeah, it's visible. Make it full screen.
Yes. Is it fine now?
Yeah.
Okay. Okay, thank you. So thank you once again. So Chairman sir, for your kind introductions. So today I'm going to talk about some of the applications of the main group metal catalyst, and also I would like to say that how this main group metal catalyst can replace the transition metals, although there are some challenges, but we are also working on a few examples I will show in this case. And one of those example is that to form that carbon phosphorus bond. So now if you come to this, that formation of this organophosphorus compounds, which is basically the carbon phosphorus bond. So then we would like to tell that the utilization or the application of this organophosphorus compounds in different dimensions. As you can see, they have a crucial role to play in a major physiological and process in photosynthesis and energy transfer. They also have several organic synthesis and medicinal fields, synthon for the natural products. And of course, they are used in various ligands in organometallic chemistry. Some of the examples I am trying to show here in the slides. Just let me make this pointer here. So as you can see in this case, this compound is mimic to the amino acid derivatives. And also in this case, you see this compound is also can be effective protein inhibitors. Here already you know that this kind of compound is used for asymmetric synthesis. Various organic researchers are using this organophosphorus compounds. And here is another important compound, natural product, which has a different biological activity, and they are used in many purposes. So now if you try to make this kind of organophosphorus compound, just to make it generalized, so which is called these hydroelementation reactions. So in this category also you can tell that hydroamination reaction, hydroalkoxylation reaction, hydrothiolation, and so on. So basically the addition of a EH bond into a carbon-nitrogen unsaturation or carbon-carbon unsaturations. So typically if we want to make a catalyst, so what the things we have to keep in mind? First of all, say for example, this is my main group metals. So now to stabilize these metals, because most of the metal in their elemental state, either they are active or sometimes they are not reactive or cannot act as a catalyst. So in this case, we have to have a spectator ligand we can stabilize this metal. And at the same time, you should have one leaving group which can actually clip during the catalytic reactions to give a active catalyst, and that can perform the catalytic reactions. So this is actually the concept. And in this case, there can be various kind of leaving group. It can be a amide group, it can be alkyl group, or also it can be a benzyl groups. So our group is also focusing various kind of metal complexes using this main group metal and different ligands. So now when the metal complex is prepared, then what are the challenges when you try to activate a small molecules? Suppose you want to make this hydrophosphonation or hydroamination, hydrothioylation, and so on. So main challenges is that they have a decreased nucleophilicity, and most of the cases they need harsh conditions if you do without catalyst, or some cases of transition metals. And also many other catalysts are known, which is a rare earth metal or the transition metal catalysts. Those are sometimes expensive. So if you replace these metals by using the main group metals, so what you can have? So you can have a atom economic reaction, because this is a one-step reactions. You can have 100% atom economic, and which is also in the line of green chemistry. And then once you prepare these compounds, then you can have a various kind of metal carbon heteroatom bonds. Say, for example, carbon phosphorus, carbon nitrogen, carbon carbon, carbon sulfur. So if you prepare one catalyst, they have a multiple role by this methodology. And one also advantage is that this kind of metals, if you say various main group metals, they are highly abundant in nature and cheaper and non-toxic. So you can use also increase the catalyst loading 5 mole% or 10 mole%. It does not really cost much. And most of the cases, they have also high catalytic efficiency. Now, just you think that if you want to make that carbon phosphorus bond, so what we have to need, we need the organophosphorus reagents. We can give the phosphorus moiety. And then, of course, we need this carbon-carbon unsaturation or carbon-nitrogen unsaturation, such that this phosphorus can be installed into this carbon. But it does not happen automatically. You need a catalyst. So that's why we try to make that if we can make a suitable main group metal catalyst, so then it is possible to form this carbon phosphorus bond. And of course, a number of advantages we have, that one-step reaction, atom economic and non-toxic, and more sustainable this process. So now coming to this organophosphorus compound, which is already available. So sometimes back, I was thinking to make, or our group was thinking to make hydrophosphonation reactions. But many cases, this compound may not be available. So in our country, it is not available. At least I did not find it. So then we have to find out that whether available phosphorus reagents can be utilized or not. So in this case, say, for example, we can also use the hydrophosphorylation reaction can be possible. Hydrophosphonylation, also this is also possible to make this organophosphorus compound. And also in this case, hydrophosphonylation by using this one, dialkyl phosphonate, can also be used to carbon phosphorus bond. So now the main group metals which is available there, we can use that alkali metals, we can use these alkaline earth metal, we can use also the p block elements, we can use it. So in our group, we are using alkali metals, alkaline earth metal, and mostly this aluminum or the indium metal we are using. So again, the advantage is that it is a low cost and readily available, and also it's greater sustainability for this. So now if we look back to the literatures, these hydrophosphonation reactions, so mostly this Westerhausen group, they first prepared this calcium, the bis diphenyl phosphonate compound, and they introduced these into this hydrophosphonation reaction of these alkynes. And they found that this is forming a quantitative yield of these compounds. And not only that, they also proposed the mechanism here. They said there is a formation of this catalyst, the addition with these alkynes, butadiene here in this case, and then it also add calcium, which is forming the carbon-calcium bond, and followed by the addition of this diphenyl phosphine. Then it gives the catalyst, and again this moiety, and further also it can give another intermediate C, and further addition of this diphenyl phosphine to get this kind of vinyl compounds in this case. So not only that, they also prepare a series of these vinyl phosphanes using this methodology. So this methodology quite successful using this calcium catalyst. And then also from Hui group from China, they also utilized another kind of calcium complex by using these compounds, you can see this one, and then utilize for these alkynes to react with this hydrophosphonation reaction to get a mixture of products. And these are regioselective, and mostly you can see they have preferred this jet preference of these E compounds. Then another group from the Trifonov from Russia, they also make a different calcium complex, a tridentate ligand in this case, you see. So these tridentate ligands are also used to this hydrophosphonation of these alkynes to give the corresponding product E and J, and these are all 100% residue-selective products. So then if you also see that Michael Hill groups also, they also tried to make the beta-diketominate ligand to make a calcium amide complex. And this calcium amide complex, when is treated for this as a catalyst for this complex, so then they got the corresponding compound. And in this case, they use a styrene. They got the corresponding organophosphorus compound here. And also they proposed the mechanism that, so during this reaction, this leaving group is cleaved to form this calcium phosphorus bond, followed by the addition of this styrene to get this another intermediate, which immediately add another kind of diphenyl phosphate to give the corresponding organophosphorus compounds. So if we see, so there is a number of main group metals are capable of doing these one-step hydrophosphonation reactions. So then there is a series of that compounds are prepared by this Carpentier and the Sarrazin group. They also use these ligands, where you can see is the anilido group here in this case, and living group are different, and different complexes, calcium, strontium, barium, they are prepared. And then this also can be utilized for the hydrophosphonation of this alkene and the alkynes. So then we are also in collaboration with the Carpentier group, then we thought that if we can take this moiety and also if we can introduce then another chalcogenide group here, in this case E, so then also it is possible to make this kind of complex, and this potential compound can also be utilized for these hydrophosphonation reactions. So in this case also we can make sure that, because if you add this kind of ligand, there will be another kind of ligand also can be come to the metal to make it homoleptic. But if we add another donor system here, then we can prevent the approaching of the another ligand to it, such that we can make the heteroleptic complex. So in such cases, so we have synthesized the ligand from this the orthonitro-benzaldehyde and the corresponding aniline. Then we can have this compound here, and followed by the introduction of the chalcogen in these steps. It can be sulfur or selenium or even also oxygen. We can add it to get these corresponding compounds. And then once we have prepared the ligand, so then as you can see, there is a selenium is there. So we can also characterize by the phosphorus, the 31 phosphorus and also the selenium, and also can nicely see the coupling between phosphorus and the selenium. Also we have synthesized or established the single crystal XRD structures. Then we introduce this ligand into this calcium or group 2 metals by using the known strategy. First we have to reacting with this potassium amide and followed by the calcium iodide. Then we could able to synthesize the sulfur analog and the selenium analog of this calcium, and as expected we have this amide as the living group. So we also have established the crystal structure of the corresponding compound and identified it. Then here also you can see the corresponding coupling between this sulfur and selenium and the phosphorus can be seen. Then when we did this catalyst for the styrene hydrophosphonation reactions, then you can see we have done a series of reaction here. Then you can find that it could give at least the 60 degree temperature. So I think this is the best result here, where here 94% under neat conditions here and 60 degree temperature, we could able to get the corresponding organophosphorus compound. However, if you get the solvent effect, so it will be reducing the yield of the products. So in the moving on, then also we also have tried out hydrophosphorylation reactions by using different the phosphorus reagents. So in this case, we are trying to introduce phosphorus group into this carbon nitrogen or the nitrile groups. So then looking back into this previous reports, they have seen there are some here triethylamine, in the presence of triethylamine you could also get, but the time is around 7 days, or also in this case the HCl, it can be happening like this. And also you can see some of the transition metal catalysts are also known to get the corresponding these organophosphorus compounds. In this case also chromium catalysts are known. But we are thinking that if we can make a very simple alkali metal catalyst, which can catalyze these compounds. Then we took nitrile, and then we use the diphenyl phosphine oxides here. And then we have taken the simple various metal amides, say for example, lithium, sodium, or potassium amides, which is commercially available. And then we use a solvent and temperature here. Then we could see, if you see here in this control reaction, so we could see here at 20 mole% of this catalyst loading, and the neat condition here, we could get also 96% of the product by using the potassium amide here. So then also, if we use the toluene as a solvent, then the yield does not change. So we prefer that the use of this potassium salt under the neat condition could be suitable to prepare this 1,2 addition product from the nitrates. So then we extended this substrate scope. So we have used the various kind of the nitrates, the different R groups here. So then also electron donating and electron withdrawing, all the cases. So just I would like to mention here, even you have an electron withdrawing group which is deactivate the aromatic ring, but still we are getting almost quantitative yield by using this alkali metal amides as a catalyst. Although you can say that we are using 20 mole%, but as you can say that sodium, potassium, these are not so harmful and also quite cheap. So we can afford it quite easily. Then once we have done this nitrile, then we thought that we also can extend it to this carbon-carbon triple bond or alkyne case. So because they have a lot of similarity here. And then if we check the literature, there are some cases where they use the ytterbium, there is a copper or the magnesium and some copper compounds that are used as a catalyst. So you would like to extend this, whether this potassium amide can be useful for this kind of reaction or not. Then we have done this. This is an optimization table. As you can see, we have used this alkynes, terminal alkynes. And then if we see this potassium amide in the 5 mole% catalyst loading under neat condition, we could able to get 95% yield of that particular products. So then after that, we also extended this in the different substrate scope. Then we have synthesized various organophosphorus compound, even in this case with electron withdrawing groups, so it does not change much of the yield formation of this. So that's why we could establish that the potassium amides, simple potassium amide commercially available, can also make this hydrophosphorylation reaction with nitrile as well as alkynes. So now we are also interested to this synthesis of the alpha aminophosphonates. So normally these alpha aminophosphonates are useful in various dimensions. They are the structural analogs of the alpha amino acids. They're also used in ligands in synthetic organic chemistry, and also they have a medicinal and pharmacological and agricultural chemistry due to their potential biological activity. So we are thinking then how we can make this a 3-component reaction by using a main group metal catalyst. So normally these alpha aminophosphonates are used in 2 different procedures. So first of all is called the phosphomanic or the Kawalnik-Feld 3-component reactions, where you can take aldehyde, amine, and this diphenyl phosphonate here. And then you can make a one pot reactions, whether you can get the corresponding alpha aminophosphonate here. Some other catalysts are also known here in this case. So these are metal free, and these are also magnesium, gallium, bismuth metals are also known. And in another procedures, the route 2, where you can say the photovic or azapotovic reactions, in that case you need to have an imine here, and then which you have to add to this diphenyl phosphine oxides in this case, and then you can get this corresponding alpha amino phosphonates. And in this case, they are using iodine or quinine or any other chiral thiourea can also act as a catalyst in this case. So we have synthesized the corresponding the indium complex. As a ligand, we have used this beta ketominate, because you can say this only one oxygen has been replaced by the amine. So then when we reacted with this indium chloride in the presence of lithium HMDS to replace this NH deprotonated and followed by it reacted with indium, then we can see that the 2 ligands attached to this indium and 1 chlorine is there, which is also helpful to replace this chlorine in the next step by reaction with the silver triplet to get the indium triplet in this case. So we have synthesized these compounds, and also the various other groups, depending on what kind of acetylacetonate group we are taking. So we can also synthesize a number of compounds. As you can see, this is the R groups here. Here the DIF and MENS. So this is coming from this corresponding aniline here. So both the cases we have crystallized compounds. So DIP and the mesotype case, as well as also we have synthesized or crystallographically characterized the corresponding triplet complex, indium complexes. And then we try to use this indium complex for this 3-component reaction or one-pot reactions. So first, the optimization are given here. So when you take the benzaldehyde, then aniline, and this the phosphine here. And in this case, what will happen? And then we got the corresponding compound, and then we see that this 3A, which is a dip here, in this case at room temperature and 6 hours, we can get 97% yield of the corresponding organophosphorus compounds. So keeping this as the optimal conditions, then we try to elaborate this substrate scope. So as you can see, we have used first different aldehydes, and then also we have used different anilines here. By using this phosphorus reagents, so we could able to get a number of organophosphorus compounds or alpha aminophosphonates by using the same strategy here. So not only that, when also we change these different phosphorus reagents here, as you can see here, diphenyl, phenyl phosphonates or diethyl phosphonates, then also it works fine, and we could able to isolate a number of organophosphorus compounds using the same strategy. So this is also the part of the substrate scope we have seen. And then some cases we also are able to isolate the corresponding product and characterize by single crystal X-ray diffractions. So in the mechanism, so we propose here that in these 3-component reactions, the reaction, this indium complex was react with this aldehyde here, where there is an indium which coordinated with the oxygen of this aldehyde, followed by the addition of the imine, where you can see this imine comes here, and this in plus there is a proton transfer here. In this case, there is elimination of water to get the corresponding form of the imine, and this imine, once this is formed, then it comes here to the addition of this the diphenyl phosphine oxide. But in this case, if you see diphenyl phosphine at tautomerize +5 to +3, and then this 3 form is reacting with this indium to make these intermediates, and followed by the rearrangement and proton transfer to get the corresponding alpha amino phosphonates here. So to understand this mechanism also, then we collaborated with Dr. Puneet Gupta from IIT Roorkee to computationally to understand how it is going on. So he helped us to do so. So first he optimized the structures. So he took the corresponding methyl analogs just to avoid the number of the atoms here for simplicity. So then he first did this reaction initially when the three component means that when catalyst, the aldehyde as well as the amine comes here, and then here the proton abstraction here coming here, which is also you said 22 6 kilocalorie here, and in this case then there is a formation of this carbinol amine here, and then there is a rearrangement of the lone pairs of the oxygen happens, and finally, as in this case you see, so this OH, this also from this water elimination at this step, and then it undergoes the 2 paths he also calculated, taking care that diphenyl phosphine oxide, which is +5, and the corresponding tautomeric form. And then we have seen that when you are using this diphenyl phosphine oxide as it is, so then this is a high energy path, which is around 46.8 kcal. So in this case, this is too high at room temperature. So this process, it does not work. Then we found out that it is already known in the literature by this Montchamp group. So that diphenyl phosphine oxide, they tautomerize to form the corresponding this phosphine here. This one tautomerize here to get through this 3-member ring to get the corresponding this one phosphorus 3 compound here. But also when it is a monomeric process, there is also high energy process. But if it is 2 molecules of it, they come closer and they form, the 6-member, in this case, the 6-member intermediate, and they can tautomerize from +5 to +3 forms, and which eventually react with the corresponding intermediates. But also I would like to mention, so the diphenyl phosphine oxide actually predominantly present during the reaction only tautomerize, and then it will react in the intermediates. So then once we did that, this +3 here, then we react with the catalyst intermediates here. Then you can see all this downhill process, and we can also obtain the corresponding product, alpha amino phosphonates. So in summary, so I could give a overview of the synthetic strategy of the organophosphorus compounds. And then also we have synthesized a calcium complex for the hydroamination of styrene. And also we have shown that that double phosphorylation product of nitrile and the alkynes by using a simple potassium amide. Then also we show a series of indium metal complexes with the beta ketoamine ligands, and also how this indium complex can be used to synthesize these alpha amino phosphonates. And also with the collaboration of Dr. Puneet Gupta, we have shown that how this DFT calculation is helpful to understand the mechanisms. So then I would like to also thank all my PhD students. So this work mostly done by Sumon and Joita, as well as I think some part of the done by Srinivas also. So I would like to thank my present PhD students and also our collaborators. And also I would like to thank the Science and Engineering Research Board, ACRB, and also Department of Chemistry, IIT Hyderabad, for their financial support. And then this is the group photo recently taken. And I would like to thank you for your kind attention. Thank you.
Thank you, Tarun. So we can have 1 or 2 quick questions.
Ask you a question. Hello. This is Kumaraswamy.
Okay, please go ahead.
Yeah. In the case of for this alpha amino phosphine oxides or alpha amino phosphonates, did you try to see whether you can get the optically pure form of that one, because the central carbon there is chiral?
So you are saying our last part of the talk?
Yeah, last part of the talk.
Oh, this one.
Yeah, in this case, okay,
So
you see that in the final product, this alpha amino phosphate, this is phosphine oxide though. Okay.
Yes.
This one at the carbon center, you have.
Yes, actually, you are correct. So, but we have not seen it because I think we get a racemic mixture.
Because those are the compounds which are analogous to this alpha amino acids.
Exactly.
Yeah, that will be, I think, if you have a chiral catalyst or a chiral auxiliary, I thought that will be really very interesting, because that is something that people are looking for.
Thank you, sir. This is an excellent idea, actually, that we can look for it.
Okay. Professor Mani.
Yes, I have one question regarding that catalyst reaction, phosphonation, phosphorylations. I'm wondering whether you have carried out this reaction in the absence of catalyst, and what is the yield if you have done that?
So this reaction, right?
Yes.
This
what is any phosphorylation or phosphonation reactions in the absence of catalyst, whether it is going?
No, I think you can see on this case, in this case, without catalyst, where no catalyst is here, so we cannot get any product here. And also hydrophosphonation reaction, also there will be no product without catalyst.
Yeah, but I have seen one report without catalyst, it goes. That is why I was asking. Okay.
Yeah.
Thank you.
Thank you.
Okay. Dr. Sakya. Sakya Sen.
Yeah. Tarun, nice talk.
Sakya, thank you.
Here. So just a quick question regarding your indium complex.
Indium complex, yes, right.
So, so you have prepared a homoleptic one. So did you try to prepare the heteroleptic one and compare the reactivity?
Just 1 second. This you're talking this one, right?
One side N and one side O.
This one. Yes. Okay.
Yeah.
So you are saying beta diketamine at all? There's both side N.
So what about the indium dichloride with one ligand?
Okay, okay. So actually, I think I understood. So the problem is in this case, we have to play with the ligand because once you did even into 1:1 reaction, so you will get only this compound. So the control is to get only dichloride. We are not able to do that.
Okay.
Only one ligand you are saying, na?
Yeah.
To have indium dichloride. So yeah. So that is not happening. So maybe we have to increase this bulkness here, R group, then only it might be possible.
Yeah. Okay. Thank you.
Okay. So please join me in thanking Dr. Tarun
Thank
Kanti
you, sir.
Panda. So with this, the session completes. Once again, I thank the organizers for giving me this opportunity. Thank you very much. So I hand over to organizers.
Yes, thank you very much, Professor Ravikant, for sharing this session. And also we extend our thanks to all the speakers for this session. Please give us a very big round of applause. So if it would have been in the offline mode, it would be very, very interesting. So anyhow, so thank you very much for everyone. And we'll be back 11 o'clock and we'll take a short break.
Okay, thank you.
Good morning, everyone. Those who joined late, once again, we welcome you for this main group molecules and materials conference. And the next session chair will be Professor Jitendra K. Bera from IIT Kanpur and HOD of the chemistry department.
Okay. Yeah, sorry, two screens were on. Thank you. It's time. Let's start the second session of the first day. First speaker is Professor V. Chandrasekhar. He's actually the one who doesn't need any introduction, but let me say few lines about him. He is presently the Center Director at TIFR Hyderabad, and he's on leave from IIT Kanpur. So technically, he's my current colleague. He has been recipient of several awards. That's a reflection of his outstanding contributions in the field of inorganic and organometallic chemistry. He received, just to name a few, he received Shanti Swarup Bhatnagar Award, Frederick Wilhelm Bessel Prizes. He is the Fellow of World Academy of Science and also the Fellow of 3 Indian academies. His main interest is main group organometallic chemistry, polynuclear metal complexes, inorganic rings, and in general area of molecular materials. With this very brief introduction, Vishri.
Thank you. Thanks a lot, Jitin. Yeah, thank you. So let me just share the screen. Is this visible?
This is the, yeah. Can you go to the full?
Yeah.
Yes, it's fine. Yeah, please.
Yeah, thanks a lot. Okay. Thank you, Jitin, for the kind introduction, and let me get started. Thanks, Krishnan, for asking me to talk in this very nice conference. So I'll be talking to you on 2 aspects. One is on low coordinate phosphorus compounds and which have a multiple bond of phosphorus double bonded compound. And also I'll talk to you about strategies to prepare ligands based on phosphorus, which is now this particular ligand I'll be speaking to you will be an NPN ligand. So let me just get started. But before I do, I need to acknowledge the funding agencies and the institutes. I'm thankful to DST, SCRB, IIT Kanpur, TIFR Hyderabad. And this work is done in close collaboration with 2 groups. One is here at TIFR Hyderabad, Anukul Jana. And the student who has done all the work is Devabrata Dhara. And Surya Narayanan, who was a postdoc here, did most of the crystallography. And then I also had collaboration with Tarun Panda at IIT Hyderabad. Srinivas Anga, who was from Tarun's group, as a postdoc here with me, and Himadri Karmakar, who's a PhD student at IIT Hyderabad, but also is now working at TIFR Hyderabad as a visiting student. So I'm thankful to all of these people for this wonderful opportunity to interact. So let me just get started with the first topic, which is reactivity of an NHC coordinated diphosphine. So the background is that main group chemistry, particularly those of the heavier main group elements, they have derived a lot of inspiration from the lighter congener carbon. Looking at the carbon chemistry with all its diversity and the millions of compounds that are known in the domain of organic chemistry, where carbon is found, the richness and diversity is primarily because of the various ways carbon can bind to itself and to other elements, single bonds, double bonds, triple bonds, and so on with itself, and then to oxygen, sulfur, and nitrogen. So this is an aspect that has been something that main group chemists have been thinking about. Can we replicate some of this chemistry, at least to some extent? Is it possible for us to prepare similar compounds where such bonds can be present, and what would be the strategies? So, of course, after several initial efforts which were unsuccessful, really the breakthrough came through some outstanding insight into how one can stabilize these compounds. And this insight was, even if these compounds are thermodynamically not stable, it may be possible to trap them in kinetic wells by means of putting substituents which are statically hindered, so that further reactivity is not possible of such a type of compounds, and particularly under certain conditions. So I think one of the greatest organometallic chemists, which is Mike Lappert at the University of Sussex, was far ahead of his time. So he, by this very simple reaction of tin dichloride and this silylated carbon derivative, was able to prepare this compound, which was a monomer in solution. But when you crystallize it, it's a dimer, and probably it's the first compound where you have this tin-tin double bond. And this was published in 1976. A few years later, in 1981, you had several compounds of this type which were reported by Robert West, who prepared the silicon-silicon double bond and reported it in Science. Then Brook from University of Toronto reported the silicon-carbon double bonded compound, and Yoshifuji from Japan reported the phosphorus-phosphorus double bond. So all of these have, as you can see, the features of all of these, the way they could stabilize was by using different sterically hindered substituents. On a silicon over here, the mesotyl group, the tertiary brittle benzene group over here, or the adamantyl group on the carbon. So this kind of brought in the design of various types of sterically hindered substituents, ranging from the simple bis trimethylsilyl methyl group over here, or the silicon analog of this, or various groups like the trip group of Philip Power, or the mesotyl group, or the supermesotyl, and the TBT group of Okazaki and Norihiro Tokito from Japan, or the CP star groups so famously popularized by Peter Utsi. So a number of such types of sterically hindered groups were developed to meet specific requirements of different main group elements and different main group situations. So such steric protections allowed the possibility of stabilizing. Otherwise, of course, they're still thermodynamically not stable, but you can trap them in kinetic wells. Another way of stabilizing compounds, which, for example, could be like the tetralenes that Shabana was talking about in terms of the carbenes or the stanniolines, etc. They have a lone pair of electrons, but they also have an empty orbital, and you could engage either both or one of them by interaction with, for example, a Lewis base to engage with the lone pair, to engage with the empty orbital, or engage the lone pair that is present with an appropriate Lewis acid, and you can stabilize. So such systems have two reactive sites, a lone pair and a vacant p orbital, and you can utilize one or both to stabilize such compounds and study their reactivity. And in fact, this particular feature was utilized very successfully for various types of compounds, including a number of compounds in formal zero oxidation state of zero, in a formal oxidation state of zero, starting from the first silicon-silicon double bonded system over here with a zero oxidation state to hetero element compounds such as this. So with this sort of a background, let me take into the investigations that Debabrata Dhara started at Hyderabad. So this was started with the objective of looking at a compound which has got a silicon and a nitrogen, which are formally present in a double bonded system. And Debabrata Dhara was looking at the possibility of having a hydrogen and silicon for later utilization. This never materialized because he got interested in other interesting things, and therefore, while he could succeed in preparing this, the reactivity of this SiH itself is still something that needs to be looked up. But what he was looking at is a simple, direct method, and a method that would allow you to quantitatively prepare a compound of this type. And various types of substituents were tried, and utilizing the stir ligand, which is a ligand of Philip Power. So you could put it on silicon, and then a dip ligand, which is this, which has got two isopropyl groups in the benzene on the nitrogen. And having this appropriate substituents on silicon and nitrogen, over here you have a hydrogen and a chlorine, which can be dehydrochlorination can occur, but that has to be accepted by a base which is not very aggressive, but a mild base such as a carbene. And the carbene itself can be utilized to bind to the silicon, so you can stabilize this. This was the thought process that went into this reaction. And the reaction works extremely well. It's a one-step process to give you this compound. And you not only generate the silicon-nitrogen double bond, but you stabilize it by means of this N-heterocyclic carbene. The reactivity of this was studied briefly, just with water, and you find that, yeah, addition across the silicon nitrogen double bond does occur. But because of the fact that you have this carbene still around, that SiOH really gets, you generate a silonylate with the hydrogen getting transferred to the carbon. So you're able to isolate this compound, which can be characterized by all techniques. So you know that this is happening. Similarly, by a very similar sort of a technique, one could also prepare a silicon phosphorus compound. So, for example, the way you do it is create the precursor by the reaction of this silicon dichloride, which is, and the silicon has a TER group already. And so by reaction with this tip PHLI, you prepare this compound which has got a SiCl over here and the phosphorus as a hydrogen. And you can characterize this by all techniques, including X-ray crystallography. So you can note that the silicon phosphorus bond distance is 2.3 angstroms, and the fact that you have a direct silicon hydrogen bond and a direct silicon phosphorus bond is manifested in the silicon 29 NMR by the coupling with the silicon hydrogen, which gives you a doublet, further split by the silicon phosphorus coupling to a doublet of doublets, as you can see over here. But there's also a 2-bond coupling with hydrogen, so that is, of course, it's a small coupling, about 7.8 Hertz. So this compound, which has got the chlorine and the hydrogen in exactly the positions that are needed for a dehydrochlorination reaction, again undergoes a very beautiful reaction, and you obtain this compound with a silicon phosphorus double, where silicon has a hydrogen, and you can see that this now cleanly, how cleanly this product can be obtained. You have the silicon phosphorus coupling as well as the silicon hydrogen coupling that is present in this particular compound. You can also characterize this compound by X-ray crystallography. And importantly, one of the interesting things that Devabrata found out was that this NHC that is used for stabilizing this compound by binding to the silicon can be exchanged. That is, the one that NHC that was used had this Me2 isopropyl 2 as a substituent. You can exchange it with NHC Me4, and you can follow this exchange by variable, by NMR. As the time progresses, you can see complete exchange occurs. So this was quite interesting. And in fact, it's an interesting, I think this kind of also is similar to what Shabana was telling in terms of the gold nanoparticles, where you have different stabilizing groups and one can be replaced by the other, which also can lead to change of reactivity. So this is something that needs again to be explored, but the fact that you can change one of the NHCs with the other after forming this compound means that small subtle changes are possible in this particular compound, which can be utilized for further modulation and reactivity. Okay, so with this very brief background, I will just take you to the first part of the story, which is reactivity of a diphosphine. So diphosphanes, now the question may be that you take great trouble to kinetically stabilize these compounds, so that they don't react indiscriminately and the double bond is lost. What is the interest in studying the reactivity? So the interest, of course, lies in a controlled sort of a reaction. If you are able to study them and utilize their reactivity in various reactions, it could be really wonderful. So that is the sort of motivation for studying the reactivity of such unusual main group compounds containing multiple double bonds. So to our surprise, when we had this TER group, which is the one that Devabrata investigated, we find that there is no reaction even with water. So there was absolutely no reaction. It's completely inert. Now, this is in contrast to this, a number of diphosphanes, but just to give you this example, where you have a very bulky group, such as this one that is used by Okazaki and Tokito regularly in their research lab. But even when you have such a large bulky group, as long as the other phosphorus doesn't have such a bulky group, it is prone to reaction quite readily. Even with, for example, alcohol, water, the P double bond P splits up. So the question that was asked was, can you increase the reactivity by the previous examples where we knew that silicon phosphorus and silicon nitrogen double bonds could be stabilized by N-heterocyclic carbenes? The question here is, can you polarize double bond by adding an N-heterocyclic carbene? So the answer is yes, you can do this by reacting this with N-heterocyclic carbene. You set up an equilibrium, and it's possible to isolate what is on the right side. And also, of course, you can turn the equilibrium back to the left side. but you can set up an equilibrium between the double bonded compound and the one where an heterocyclic carbene interacts with the phosphorus. So you can see here, of course, those who are familiar with this field must be immediately recognizing the extremely de-shielded signal for the PP double bond. In fact, this is the one signal that Yoshifuji missed and Alan Cowley picked up when he was doing the same reaction. So this is 492 at 492 ppm. And once it reacts with the N-heterocyclic carbene, of course, the two phosphorus now are non-equivalent. So you have this doublet or doublets which are shielded at these regions that you see. Actually, in fact, this particular signal is very highly shielded. So, but you can see that they become non-equivalent. And you can turn this equilibrium back to the left side by removing this N-heterocyclic carbene by interacting with a stronger Lewis acid. So, for example, with either a zinc salt or with the triphenyl borane, you can have this N-heterocyclic carbene replaced from this, and you'll take it back to the left side. So then this equilibrium was studied in greater detail, and it was found that, in fact, because of the fact that you have only one particle on the right side compared to two on the left side, the equilibrium can be stabilized to the right side if you do it at low temperatures. So at low temperatures, it is possible to stabilize this completely to the right side. And in fact, the adduct can be isolated and can be studied by various techniques, including by X-ray crystallography, which was what was done. So you find that in comparison to the PP double bonded system, where you have a bond distance of 1.985, when these adducts are formed, the bond distance increases as anticipated to 2.13. So there is a short increase of the bond distance as anticipated upon losing this double bond character. And of course, you can study this further by checking what would happen if, for example, deliberately I add an excess of NHC, would I cleave this bond? And indeed, it was found that you can cleave this PP bond. Particularly, this was successful with 3 N-heterocyclic carbenes, as noted over here. And within a time period that ranges from 2 days to 15 days, you can completely break this and generate this corresponding phosphinidenes. So the rate of this PP bond formation is proportional also to the stability of this NHC diphosphine adduct. And we could isolate the phosphinidenes and characterize them, as you can see over here. So in some cases, you can see that the bond angle is almost close to 90 degrees. In some, they're slightly larger than 90 degrees. In all cases, we could completely characterize this by both multinuclear NMR as well as by X-ray crystallography. Okay. Now, at this particular point, Debabrata was looking at this. I showed you in the introductory slide that you can have an interaction with both the Lewis in terms of a Lewis acid interacting with such compounds as well as a Lewis base. That is, the lone pair present in these compounds can you utilize them for forming let us say metal complexes. So what Debabrata was looking at was, if I interact this double bond, that phosphorus compound, with the N-heterocyclic carbene, generate this compound now which has a Lewis base attached to phosphorus, but it still has 2 lone pairs on the phosphorus over here. In fact, also another one over here. Can you interact with a metal and form a compound where simultaneously you have both a Lewis base and a Lewis acid interacting here? So what was chosen was gold chloride. I'll come back to this a little later about why this was chosen. So this gold chloride adduct with dimethyl sulfide was chosen, and you have this phosphorus interacting as anticipated with this gold chloride, forming a gold 1 compound. So you have this gold 1 compound which is characterized, and you can see, as I mentioned earlier also to you, that how this bond distances change. When you have the P double bond P, it is 1.985. It goes to 2.134. Upon further interaction with the gold chloride, the bond length further increases and goes to 2.21. But you can see that this very nicely interacts with gold chloride, forming this compound. Okay. What was also noticed that the interaction with gold with this phosphorus accelerates the PP bond cleavage. So before this interaction, if you are trying to cleave this only with certain NHCs, you could affect this. Also, the time taken for such cleavage, as I said, range from 2 days to 15 days. But when you interact already with this gold chloride and then you subject this to further reaction with an NHC, you almost have an instantaneous PP bond cleavage, generating this NHC gold chloride adduct along with the phosphorus-phosphorus bond broken compound, the phosphonidine. So this reactivity seems to be also accelerated in a dramatic manner once this is interacting with the Lewis acid. I'll come back to this gold chloride and what we have done with this little later. The motivation for this reaction with NHC was to in fact check whether the NHC can form an adduct and then can increase the reactivity of the PP double bond. So as just to kind of put you back on this thing, this was what we had tried before. This compound, upon reaction with water, there is no reaction. Similarly, when we try to hydrogenate this with ammonia borane, it does occur, but it's an extremely slow reaction. So the entire process that I showed you before was, can we polarize the PP bond by NHC and therefore increase the reactivity? So this was, of course, achieved. So when we did this, for this particular adduct, I've already shown you with a number of NHCs that could be characterized. And this is an equilibrium, but you can also isolate this compound. So to this polarized phosphorus-phosphorus bond, now if we react it with water, there is an immediate addition of water across the PP double bond. And again, like in the case of the silicon system, there is a hydrogen that is abstracted by this NHC to form this imidazolium cation. This hydrogen actually is formally coming from this phosphorus because there is an oxygen hydrogen. The water adds on to the PP double bond, and therefore that is coming from over here to generate this imidazolium cation, which is hydrogen bonded to the P double bond over here. But this can also be in equilibrium with this phosphine oxide species, where the where this carbene is completely separated from this particular phosphorus. And in fact, this can be studied again. So these two species are in equilibrium. One there, this imidazolium cation is hydrogen bonded to the oxygen of this with this. So what you can do is, by again adding a Lewis acid, you can completely remove this the NHC, so that now generates this adduct, the Lewis acid Lewis base adduct, which frees up the phosphine oxide type of a compound, and therefore this possibility is completely prevented now. So fortunately, we have evidence from all sources, including X-ray crystallography, where you could isolate these compounds and study them, and you can notice this bond length increase in both of these compounds, and also the PO bond in terms of the fact that in one particular case a formal P double bonder with a 1.473, and in other case a slightly lengthened PO bond with 1.490 could be established. We tried to, with the help of theoretical studies with collaboration, we tried to figure out how is this addition occurring. And it seems to be a sort of a simultaneous interaction of water molecule with both the phosphorus centers, generating this reactivity that we have seen. And in fact, we also, Debabrata established that this can also occur catalytically at low temperatures, because that's where the adduct formation is driven to the right. So even, for example, with 10 mole% of this, you can completely hydrolyze this particular product into a particular reactant into this product. So the addition of carbene, of course, we have established is reversible, but you don't need the entire stoichiometric amount of the catalyst. Even at 10 mole% this works at low temperatures. So Debabrata got into something quite interesting. So what he thought was, is it necessary that you have to have a stable adduct to do this polarization and in fact carry out the reaction to the right? What if the adduct formation doesn't take place, but if the phosphine, if the phosphorus-phosphorus double bonded system, that is phosphine with the ENE, and the carbene, they are in close proximity, but they haven't formed an adduct. Like for example, with these carbenes, the adduct formation, stable adduct formation was not noticed, but the question was, if you just combine them together and now you add the reactant, namely water, would the reaction proceed? So something analogous, but not exactly similar to the FLP concept, but something that there are two things that are coming close to each other, but there is a frustration because an adduct formation cannot take place, but would that assist further reactivity? So this is basically what he set out to try. So you have this in the adduct formation doesn't occur because we could never isolate the adduct. But when you combine them and add water, you find immediately this reaction occurring. And you get the products that you were able to isolate even when the adduct formation did not occur. So essentially, therefore, this reaction proceeds in two ways. One is one where a clear adduct formation occurs, and then you can the reactivity of this phosphorus double bond is accelerated, and you can generate these compounds as you had as indicated, but not necessary. You can also have in a manner that is analogous but not similar. There is the NHC is not able to form an adduct with the phosphorus, but nevertheless seems to be in reasonable proximity to the phosphorus, that when you have a water molecule added to it, then the reaction is promoted by this closeness to this, and you can have the reaction occur. Unfortunately, we haven't really done more in terms of determining the mechanism of this, how close the NHC and the phosphorus centers have to be for this reaction to occur. But this is something that we would really be interested in kind of unraveling. Okay. So similarly, hydrogenation reaction. So the hydrogenation reaction of the unactivated phosphorus-phosphorus double bonded compound takes a lot of time. It occurs, and you get this diastereomers. You get this DL diastereomers where you have the phosphorus centers hydrogenated. Both the D and L are formed together, and the D and L can get converted eventually to the mesoform. So you can see here the D and L forms coming at -101 and the mesoform at -109, which is initially the mesoform is much lower in its yield, but it eventually gets converted into the mesoform. Okay. But when you add the NHC, and this reaction, which took about 7 days, now happens in 10 minutes. And you generate this hydrogenated products. Also, of course, one must be aware that the NHC itself is prone to hydrogenation. So you generate the hydrogenated product of this. But the point of reactivity, which we wanted to establish, is fairly clear, that once you are able to form an adduct with the PP and then polarize this PP bond, the hydrogenation reaction occurs very quickly. And at low temperature, the DL formation, DL product is a major product, this diastereomers, and then you are eventually converted into the meso as you increase the temperature and the time. Okay. And in fact, you can really prove this very beautifully by very nice NMR studies. So as you can see, these are a very beautiful AA prime, XX prime systems, both meso and DL. Their coupling constants are different, therefore the patterns are different, but both are AA prime, XX prime systems. So they can be very beautifully simulated, and you can obtain their parameters involved, namely the one bond couplings, the two bond couplings, and 3 bond couplings, and simulate them perfectly. So you know that this is basically what's happening. Okay. Now I'll just take you to the gold system that I had previously shown, where we had the formation of the gold chloride complex with one of the phosphorus centers of the PP double bond. Now, some years ago, there was a report that an NHC can stabilize this gold hydride, and this gold hydride, you can see, is 2 coordinate. Gold is 2 coordinate, and gold is in a formal oxidation state of 1, and this is a linear complex where, of course, you have this hydride that is present. This was reported in Angavan Tashimi in 2008. So what we thought really was the gold chloride that we had, is it possible to convert this into this gold hydride and stabilize it in that form? So the reaction was, as I had shown before, was this, that you polarize the phosphorus-phosphorus double bond and then reacted to this gold 1 compound. So you generate this gold chloride, which was characterized as shown before, with a slight, actually reasonable lengthening of the bond compared to the PP double bond. So this first has an initial lengthening, and then has a subsequent lengthening of the bond, and you have a gold chloride. Now, this can be quite nicely hydrogenated by standard borane hydrogenating reagents like N-selectride, and you get this gold hydride. And this is stabilized, and you can also see that it can be characterized both in solution as well as in the solid state. So the phosphorus coupling constant, which is, for example, the 2-bond coupling constant is about 138 Hz here, and you can stabilize it by other means, characterize it by other means also. Interestingly, there is a thermal rearrangement that we noticed, that you heat it and you find that this carbene center comes back to the gold, and the hydrogen goes to the phosphorus upon heating, and that also can be characterized by both solution NMR as well as by solid state structural techniques. So, so there is this interesting thing that's happening. But more interestingly, what Debabrata wanted to kind of really investigate was, is it possible to utilize this gold hydride to react it with carbon dioxide, and then see whether, for example, we can have a system like this. Can we have this formate generated, which can be reversible and can be demonstrate that such a reaction with carbon dioxide occurs. And indeed, it occurs very readily. And these are in equilibrium, but it's possible to isolate one or the other. And you can isolate this compound, and also you can remove carbon dioxide from it. And but also this compound has been characterized, as you can see over here, by X-ray crystallography as well as by solution NMR. So this is kind of giving you a summary that you can isolate this compound, and then you can generate by addition of a further NHC, the carbon dioxide can be transferred to the NHC, regenerating the gold hydride. Or you can go through this intermediate upon addition of the NHC and go through this particular eventual reaction that is there. Now, of course, formic acid is considered as something that has this potential of releasing hydrogen. So it was we wanted to check whether the formate derivative that we have can be considered similar in terms of can it be generated by reaction, that is the hydride compound. If it reacts with formic acid, can it replace hydrogen and generate this compound as shown on the right? And this reaction seems to occur quite cleanly. Okay. Now I must mention, I haven't done this in comparison. For example, the NHC stabilized gold hydride itself, which was reported, as I mentioned, in Angavan Tashimi a few years ago, itself doesn't undergo these reactions. Now, we are not sure of the exact reasons of this, but we need to kind of delve into the energetics of this, particularly maybe with theoretical studies. But it appears that the phosphine stabilized gold hydride seems to be much more reactive than just the NHC stabilized derivative. So just to kind of continue this theme and see whether this gold hydride can react with other substrates, this was done with the terminal acetylene, and it forms, as you can see, by losing hydrogen, this forms this acetylide compound. Whereas again, similarly, a similar reaction which was investigated earlier did not seem to generate a similar product. And this was studied with other systems. So for example, you can have this addition reactions with this internal acetylenes, and you can isolate these compounds. And also not only that, diazoacetates and generate these compounds. But I'll have to quickly go through because I have another topic and have 5 minutes. I will not take you through the details of this, but we can. These are published, so you can look up at these papers. But before I step out of this topic, I should mention that it was also possible to look at this phosphinidines and look at their reactivity, particularly by seeing whether one can isolate the nitroso analogs. But the phosphine analogs are the nitroso compounds. Nitroso compounds and the NO2 compounds, of course, very well known. So whether one can isolate these compounds. And indeed, by mild oxidation agents like N2O, you can actually isolate this ARPO derivative. And on further oxygenation, you can generate a derivative which is an analog of this NO2 derivative. And in fact, you can, again, like previously, you can characterize all of them by X-ray crystallography as well as in solution. So for example, you can check that the bond distance variations upon conversion of PO to P double bond O. And also you can, for example, take this compound and convert this into a radical cation and prepare the POH derivative. And of course, the H now migrates to the phosphorus in a tautomerism and generates the P double bond OH. Finally, this compound can be reduced to give you this radical anion now. And this radical anion because of the fact that you have this potassium ions that are there, which are used for reduction of this. In fact, this is one of the examples, like for what would be like a coupling between the PP and the P. So you generate this PP coupled product, which further assembles to this tetranuclear derivative. So this is where this phosphorus chemistry is right now, and we hope to take it further by further exploring this reactivity of these compounds. Very quickly, in about 5 to 6 minutes time, I'll dwell on our efforts to generate compounds where we have the phosphorus is supporting unsymmetric ligands. So the background of this work arises from the fact that you have ligands which can eventually, upon complexation, give you 4-membered rings like carboxylates or imidinates or guanidinates. In the morning, we have seen, for example, Cameron Jones was alluding to this guanidinate ligands for isolating, the magnesium 1 compounds. So such ligands are really extremely useful and extremely important in a variety of applications. So all of these have a negative charge there, and then you can interact with a metal, a variety of metal ions, and create the possibility of compounds which have unusual reactivity. And in fact, I'll just dwell on one of them, which is using this imidinate ligand. For example, Roeski was able to isolate this silicon 2 compound and was able to then exploit the reactivity of this in a variety of ways. There are many other examples. I just chose this particular example to illustrate this point. But there are other systems which can give you similar type of ligands. So for example, can you replace that carbon with sulfur, with phosphorus, or with boron? So it is indeed possible to prepare such ligand systems where the carbon is replaced with other main group elements and give you similar types of ligands. But the difference is that because of the fact that the atomic radii of these elements are different, the bite angle and therefore the distance that this nitrogen binds to the metal will be different, and that might have an impact on the eventual reactivity of the metal complex. So this was basically what motivated us to look into this particular family of ligands. So this is our monoanionic ligand, which is imidinates, which are very well studied, or it could be the guanidinate, where R is an N group. This is symmetrical. It is monoanionic, and it is an N donor. So we wanted to generate with phosphorus. If you have, for example, another amino group, that will be a dianionic system, because you'll have 2 amino groups, and if you deprotonate them, you'll have a dianionic system. So we wanted to have an equivalent of this, which would be a monoanionic. So on one side, we had this particular group over here, and then the other side we had an aryl amine, which we could deprotonate and generate this imidinate ligand. Okay, so this was of course well studied by Tam and other people in terms of how this ligand behaves, and they showed that it is possible to write resonance structures where the nitrogen exclusively have the negative charge and this carbon center would have this positive charge. So we prepared this compound, as I'll show you, and utilized it in its reactivity. And the reaction itself is pretty straightforward. Srinivas Anga did these reactions. So he took this compound and reacted with this aryl amine, generating this amino derivative, and then with the lithium salt of this imino compound, generated this amino derivative, which could be characterized very readily. And we did several other studies. I'll just show you one of them, where we reacted with an yttrium compound, because the reason we chose the yttrium compound was analogous yttrium compounds were characterized and their reactivity studied. And we could prepare this yttrium complex and study its reactivity. And in fact, we could prepare not just the yttrium with also the alkali metal ions, and we are probing also with other metal ions. But I'll skip this. And the yttrium derivative itself, we could utilize in catalytic hydroboration just as a proof of principle, because such complexes are known to indulge in this catalysis. So we took both ketones and aldehydes and saw whether they would be they could be catalyzed by this yttrium complex that we prepared, and indeed these work beautifully at very low catalytic mole percentages, actually at 0.01% very quickly, and as anticipated, even in a competitive reaction, the aldehyde of course reacts much faster, and therefore the aldehyde gets hydrogenated. Okay, the mechanism, we haven't probed the details of the mechanism, so our mechanism is based on what is postulated in the literature, but honestly, we haven't done any efforts to probe this, which we should perhaps do it. But the first step seems to be converting this borane, pinacol borane, into this derivative, and generating the hydrogen is transferred to the yttrium, and that catalyzes. Okay. Similarly, very quickly, I'll just take you in a minute or so. Himadri has been working on analogous compounds with aluminum. So he prepared this aluminum derivative with 2 methyl groups. And in fact, a variety of such compounds have been prepared. And he showed that these compounds would be extremely good catalysts for this guanylation of unactivated carbodiamides. So you generate these guanylated products. Because my time is running out, I will not take you through the details of it, but needless to say that it works really very well. And also the mechanism of this, which is based on a mechanism known earlier, we have postulated this. I think it's a time to stop, and I'll give you a summary of this. That we looked at this phosphorus double bonded compounds and tried to figure out if one can increase the reactivity by reacting with NHC. And indeed it does. We studied the reaction with water and dihydrogen. And also it can be utilized for stabilization of gold hydride, and it's later used in activation of carbon dioxide. And the product of it, with the cleavage of the PP double bond, which is a phosphinidine, can be used for a variety of things. One of the things that we did was for oxygenation, which gives you analogs of nitroso and nitro aromatic compounds, which are known in carbon chemistry. You have the analogs in phosphorus chemistry. And then the second part of it, very quickly, I took you through the monoanionic imino-phosphanamidinate ligands, which has the possibility of tunable steric and electronic properties, and showed you that it can bind to several metals. But the ones I showed you was yttrium and aluminum. Thank you very much. I am kind of right on the dot, but I hope I haven't crossed the time.
No, that's fine. Thank you, Rishi. Any questions? You can raise your hand so I can call you for the question. Well, I don't see any hand. I'll start with one. You have made some very interesting asymmetric that NN ligand. I was wondering if you make monometallic complexes like yttrium you have made. I was wondering then where is the benefit of making that asymmetric, whereas similar ligand previously on a bimetallic platform, people will be able to make a one high valent, one low valent bimetallic assemblies, like to utilize the full potential of this asymmetric ligand. Do you see any advantage when you are making them monometallic in terms of even catalysis or reactivity?
Yeah, no, at the moment it's just at the proof of principle stage, but if you notice, this phosphorus is a phosphorus 3 oxidation state. So it would be possible for us to, for example, tune the reactivity further by engaging the phosphorus with other metals, and therefore that could impact the reactivity of the other. That is one aspect of it. So in terms of, therefore, the answer to your question is yes, at the moment there is really no advantage of this particular design just as it is. But this is right now really at establishing the reactivity of it in terms of what it can do. The second stage of it is to take it further in terms of can you bind the phosphorus 3 with anything, even with, for example, sulfur, selenium, or with a metal, and see how it impacts the catalytic reactivity. The third thing, in terms of the asymmetry that it offers, actually that the reason we chose this was really with this phosphorus design, can we prepare a monoanionic system? See, if I put 2 amino groups, I'll get a dianionic, it's possible to generate a dianionic type of a ligand, which we wanted to avoid because we wanted to have something that is analogous to a monoanionic, well-studied amidinated guanidinate. But the possibility of changing the reactivity at the amino centers is very clear. That is possible. So that is basically the approach that we are looking forward.
I was also looking on the basis of, because you have two different center in terms of electronic asymmetry, whether one will be able to bind two substrate in a very specific position, that one in terms of one element in the ligand, the another substrate in terms of another element. If that's a possibility.
No, that's true. That's I mean that is the work in progress, and that is why I'm figuring out how to. Clearly, we have a very nice and a quick and direct way of making interesting ligands. So now we need to figure out what are the other possibilities. So, for example, is it also possible to create a catalyst that is able to have chirality and have chiral induction? Is that possible? So these are things that we are grappling with. And I'm sure that in the coming months, we'll come to some answers with this.
Okay. Sakko? You are muted.
Sorry. Yeah, very nice talk. So in line with Jitendra's part, actually my question on the second part of your topic, where actually use this unsymmetrical ligand. And because you already have a success with yttrium, so I was wondering, have you ventured into alkaline earth metal? Because lanthanides versus alkaline earth metal.
Yeah. We have ventured into it. What we have done with it is still a story that will come up later.
Okay. And the second thing is that because you have a phosphorus at the backbone, did you notice any cooperative bond activation? Suppose you take BH bond or PH bond, do you see any cooperative bond? Because the phosphorus is in +3 oxidation state, right? So did you observe anything like that?
Yeah, so the only reaction we studied is this hydroboration, but we need to study more of that and to tell you the answers for this. But we have some results which are still kind of Himadri is working hard on this. After we convert this phosphorus into phosphorus selenium or phosphorus sulfur centers, so we observe quite a reactivity differences depending upon the metal that we interact. Whether the selenium interacts or the nitrogen interacts seems to depend upon the metal that is there. But that is still at a stage where we really can't tell a lot of details, because we need to have more examples and understand them better. But yes, reactivity differences therefore are seen.
Okay, thank you. Very nice talk.
Yeah, thanks.
Okay, we are running out of time, but Anantaraman, just a quick question, a quick one.
Yes, it was a wonderful talk. Yeah, it was a wonderful talk. I'm just curious only about the reactivity with water on PP compound. Why it is stopping up to the level of the one phosphorus getting oxygenated? Why not the second one also?
Okay, so in a sense of the hydrolysis of the compound, actually we must also the competing reactions after the first hydrolysis occurs. As you notice, there is a strong phosphorus oxygen bond formation taking place, and not only that, the adduct that it is forming with the imidazolium salt is also stabilizing this compound. So in either case, once this phosphorus bond formation is taking place, then that is stabilizing that. Of course, we haven't really investigated what happens if you, for example, take an excess of water, react it under harsh conditions, what happens. So these are things that we haven't explored, because that wasn't really the idea. The idea was to check whether reactivity of a PP double bond can be enhanced by polarizing that bond. So that was kind of the aim of it, and that was proven successfully. The idea was not really to check whether PP bond can be broken completely and it can be hydrolyzed. So that was not something we went ahead with that. Yeah.
Okay. And sorry.
We're running out of time. So we'll conclude here. Thank you, VC, for your very nice presentation. And now we'll move to the second talk in this session. Next speaker is Dr. Professor Sundar Gopal Ghosh, who is presently is a professor in the Department of Chemistry at IIT Madras. Sundar is a prolific researcher, published close to 250 publications in the field of boron chemistry. He is an elected fellow of the Indian Academy of Sciences and the National Academy of Sciences. And today Sundar will discuss a structural paradigm in metalloborons. Sundar?
Okay, thank you so much, Jiten, for your nice introduction, and good morning. So let me share the screen. Is this okay, Jiten?
Yes, it's fine.
Okay. So, so at the outset, I would like to thank this organizing committee, Molecules to Material, particularly Krishnan, for the invitation to share some of the results that we have been working at IIT Madras. So today, although my topic is structural paradigms in the metal-borne chemistry, not exactly match with the molecules to material theme. However, many of the molecules that I'm going to show you, they are actually good molecules for the materials. But I will particularly focus on some of the recent results, particularly with the borons that typically mimics many of the classical organometallic species. So as you know, boron is a very peculiar element and very different in the periodic table, and mainly because it follows the 6-electron rule, does not obey that octet rules, and because of that, and being next to carbon in the periodic table, it offers a varieties of bonding and structure and a lot of different coordination modes with the transition metal. So utilizing this, the special behavior of this boron element, particularly with a 3-center 2-electron or 4-center 2-electron bonds, we have been exploring this with different kind of reactivities, and we have a lot of different types of structure geometries. So I'm going to talk about today some of the very typical, organometallic species mimicking with that boron molecules mimic. If you look into the literature of different organometallic, classical organometallic species, which was synthesized long back, I have listed some of the a few examples here that you could see how nicely boron mimics this organometallic species. The first one, it was made by Sheldon Shore. It was a B2H6. Then it was a B3. Then it was a B4, B5, and then the last one is the pentalene one. This B5 molecule, which was a direct mimicking of the ferrocene, it was made by Russell Grimes in 1977. So this reminds me one of the very exciting molecule of boranes, that is the pentaboron 9. This molecule, once it was made by US Air Force in a very large quantities, considering the fact that it could be useful for a potential rocket fuel. Although this program did not go through, it failed. However, the amount of pentaboron made by this US Air Force, so they had to typically destroy it. So this is one of the very, the typical, the pentaboron storage site at the California Edwards Air Force Base. So this pentaboron 9 molecules, they had to destroy it, and in which they had made a huge amount that I had shown you stored in a tank. So these pentaboron 9 molecules, later on, they found many of the labs that they could gift it to work on. And that's the reason you'll see this molecule have been used in a large quantities to synthesize the decaborane or the development of the carbon chemistry. So I believe that many of the labs got this pentaboron 9 as a gift to work on this. So in continuation to the mimicking, the boron mimics, so another interesting molecule, it was the borylene, and the free borylene is extremely reactive species, and it is not easy to isolate it. However, many of the transition metal can coordinate with this, and people have isolated this molecule. We have isolated this molecule in a different way in the coordination sphere of 3 transition metal. I'll talk about that in a little bit. So typically, the synthetic part, we take a cyclopentadienyl metal chloride or metal carbonyl, and you treat simply with a metalloboron, with a boranes reagent, like lithium borohydride or borane, BH3SME2, BH3amine, so on and so forth. And you develop these metalloborane compounds. And in depending upon the transition metal, this leads to the formation of a metal hydride or metalloborane. Particularly with the early transition metal, the synthesis is extremely difficult. And if you look at the typical the metal precursor, particularly with the early transition metals, so they are extremely air and moisture sensitive. And that's why the development, particularly the early transition metals, are not much. Okay, so you know the isolable analogy, the BH is isolable with FeCO3 fragment. An isolable idea permits metal to be substituted for BH. So one of the molecules made long back by Geeta Rani, this is the ruthenium-2B2. So we thought whether one of the BH vertices can be replaced with the isolable FeCO3 fragment, and indeed we are successful isolating that molecule in which one BH was replaced by FeCO3. So since after that we had made a series of molecules in which that BH fragment got stabilized in the coordination pair of 3 transition metal. And this is a very typical mimicking of an organometallic species that is left that I have shown in the left-hand side, cobalt-3 CH3. Now the next one is a diborane molecule. The diborane molecule is extremely difficult to, as you all know. However, if you could coordinate with a different transition metal fragment, and this molecule can be stabilized. So the first one, it was the Sheldon Shore who made in 1989, and in which you see that this is a diborane 6. One of the hydrogen is actually replaced by FeCO2 CP fragment. So we also have synthesized a similar kind of molecule, diborane 6, in which you have this H, the bridging BHB is replaced by CP star ruthenium and 2 sulfur. That follows a typical 18 electron counting rule of this metal center and also satisfied this electron count. So this is the first structurally characterized neutral ruthena diborane 6 analog. And it may be measured as a derivative of diborane 6, in which the CP star ruthenium fragment has replaced the bridging hydrogen. Now we move on to another transition metal. So one of the molecule we want to utilize, that is the diborane 6 molecule, which was made by Simon Roldis long time back when he was a postdoc student with Thomas Fellner. So what we did that we treated this with carbon monoxide and at room temperature. And what happens that it replaces this chlorine and leads to the formation of this diborane 4 molecule. And as you see that the NMR at room temperature is almost like a flat. However, once you lower the temperature, you could see the boron NMR peak. Unfortunately, we have got the crystal structure for this molecule. The BB bond distance for this molecule is 1.69, in which you have 4 hydrogens attached to that. Now, this is again a classical organometallic molecule, the mimics, that was made by F.A. Cotton. This is the molybdenum CO2 dimer with acetylene, and we had the B2H4. So this B2H4 is isolable with the acetylene, and this you can consider to be a very nice mimicking of this acetylene metal complex. The earlier report of Sheldon Shore, as I had shown you earlier. Now, this molecule, we have done a theoretical calculation in collaboration with GEMIS, and we found that this is a 4 electron donor to this metal complex. Now, diborane 4 has all these 4 different symmetries, starting with this D2H, CS, D2D, and C2V. And as it's very interesting, this is the only molecule, the B2H4, that falls into CS chemistry. the structure of this was not known. So this is now, once we had this structure, now we can fulfill all these 4 diboron 4 molecules structurally known. I have not shown the other D2H, D2D, and C2V structure just for the benefit of the time. Now, once we have this diboron 4, as it is a 2-electron donor, and it's equivalent to tungsten CO4 fragment. So we wanted to treat this with a tungsten or molybdenum CO5 THF with an objective if these 2 hydrogen can be replaced. And indeed, when you do the reaction, it actually removes these 2 hydrogen and leads to the formation of a diboron. As you see both this structure, left-hand side, you have a diboron 4 in which a bond distance of BB is 1.71. And the right-hand side, which is a diboron, the BB bond distance is 1.59. So this is a very nicely correlated with the diboron 4 and the diboron 2 that reflect the corroborate with the bond distance as well as the other spectroscopic data. Now another diboron molecule is the diboron 6. Now if you look into the diboron 6, there are 2 types of molecules. One is a classical one, another is a non-classical one. So there are some theoretical study on the C2H5 cation, and in which you see that the different type of bonding with this the C2. So similarly, in the case of the diboron, the non-classical one is very well known. A lot of people contributed to this field and have isolated this non-classical diboron 5 molecule. However, the classical one, there is not a single molecule was known in terms of the classical geometry. So while working on the tantalum system, we treated this tantalum CP*Cl4 and with a lithium BH3 CS2 adduct and presence of the phosphine. And what we see here is this molecule. And when we first recorded the NMR, in which initially we thought probably it is a diboron 6 molecule that I have shown on the right-hand side. However, when we have done the theoretical calculation on that, it shows a completely different scenario. So the X-ray structure of this shows it's actually a diboron 5. The 6th hydrogen actually it breathes between 2 of the tantalum. So when we had the NMR, it was very structural puzzling because of this presence of tantalum is tantalum. It comes at a very positive region at 9.25 ppm. So we did theoretical calculation again with the GEMIS, and what we observed that the isomer, what I was talking about, this B2H6, it has this energy of 0, but the most stable one is the one in which you have a tantalum is tantalum, and the B2H5 actually it's it's in a classical mode. There is no BHB. And now it very nicely corroborate with your boron NMR that gives around 46.5 ppm difference, and everything matches very well now with this X-ray structure. Okay, and in the same year, Douglas Stephen also isolated a diboron 5 cation, and he made it from this molecule, a diboron in which they treated with ET3Si toluyl plus and very nicely isolated this molecule. Okay, now we wanted to see whether this diboron 5, if you treat with the molybdenum CO5, it can remove 2 hydrogen. Unfortunately, when you do the reaction, it simply coordinate with one of the boron atom, and that gives a adduct with MoCO3. As you see that boron NMR, once we coordinate with the molybdenum, the boron chemical shifted to the downfield region, and we did a theoretical calculation also shows that this the molybdenum H coordination with this boron is also fluctuate between these 2 tantalum, and that goes a different kind of isomer. And when we did this experiment at a lower temperature, we could see two different type of peak in the proton NMR and also the CP star region. So that shows that at room temperature, this molecule is very fractional, that shuttle between these two tantalum centers. Okay, the next one is the one which the dream for many of the boron chemists to have a flat B6 ring. A lot of theoreticians have been working for long time. There are a lot of theoretical reports. In generally, boranes do not form a flat B6 ring, and mostly it leads to the formation of a polyhedral cluster, particularly with octahedral. However, Alex and Jemis and many others propose that if you can make this B6H6 by 6 lithium plus, it can be stabilized. And again, the Boniface and UC Riverside, you also in the matrix, you have solid study has shown that this B6 ring can be stabilized in this form. So we have been working since I started my career. This was one of my dreams to make a flat B6 ring. So nonetheless, so we have been working with all the transition metal, and very nice report by Jemis in 1988 that says that a possibility we have investigated is to create an inverse sandwich structure, and particularly with the vanadium and titanium, that might give you a flat B6 ring, and making this B6 as a sandwich between these two CP star metal fragments. So we are interested mostly with these two transition metal. So we did earlier we used to work on a CP, but we did not get any success. However, once we switched to CP star, and I'm not going in details of all the story, but as you see here, this is the Chem-Draw structure of this B6H12. It gives a single boron peak. We have a beautiful B6 ring that is stabilized. As I said, that is the B6 with a 6 extra hydrogen to support the electron count. And so Cameron Jones in 2018 also isolated the aluminium 6, as you see that, but it's not a flat, but it's actually a octahedral structure. This is a very nice result. And in our case, we have a B6 that gives a almost planar B6 ring. We have extended this one to vanadium. In fact, the vanadium one is the one we got the preliminary result initially. It was almost 2 years back. And we have been working, we had a lot of difficulties. And presently this data is at the ANSTRO with Alison Woodward. Thanks to Cameron Jones to introducing Alison for this Newton diffraction study. So I believe that currently she is working on this, the Newton diffraction. Hopefully soon we'll get the data so we can present both the vanadium as well as titanium B6 ring in future, hopefully. Of course, there are a lot of theoretical study going on. Jemis is working on that. Okay, so the next molecule is your B7H7 molecule. If you look into the textbook, you will see all this different hydroborate, but not the B7 one. The main reason is not having enough literature on the B7. The moment it forms a B7, it immediately goes to the dodecahedral B8. And these are all the history of the different borates. And 2011, Bernhardt made this B7H7 as and it stabilized with different that anions. And so we have been working with the early transition metal with the zirconium. First, we made the B3. And when we are working with that, one of the another compound isolated in the same reaction, it was the boron NMR was very complicated. Mass spectrum shows the structure that I had shown in the right-hand side. It's a very nice B7, the core is your bicap, a pentagonal pyramid. in which this B7 core is stabilized by 2 zirconium Sp2 fragment. And this molecule, we have done a lot of theoretical calculation in collaboration with Lai Seng Wang. I'm not going with all those theoretical study. Another molecule with different reaction conditions and temperature, solvent. So a few of my very dedicated student was working on this group 4 metal. So another molecule isolated is the dodecahedral B8 species. As you see there are a lot of theoretical calculation have been worked on, is all I listed here. So this molecule is very special, mainly because this molecule, the B8, it exists in 3 different isomers, the D2D, C2V, and D4D. And the solid state and the solution NMR of these 2 molecules are totally different, and it exists in a different isomer. One is your dodecahedral, you have a bicapped trigonal prism, and the square antiprism. So the first time we have shown that the solid state as well as the solution, it shows a similar kind of behavior. This one we have worked with the JEMIS for the theoretical calculation. As you could see that the first one, in which it shows a good electronic configuration for the metal Sp2 to this B8, and it has almost a 43% contribution towards the B8 core. And NMR, as you see that, this is a very nice correlation with your theoretical data. So this is the first time we had shown that a dodecahedral is the one that shows a very distinct NMR peak in the solution and as well as the solid state structure. So now with this study, we can now tell that whether this a different hydroborate, which is beyond icosahedron, and particularly with B13, B14, can be trapped with this the Cp metal fragment to the code as a stabilizing agent, because B13, B14 hydroborate is still a dream to the chemist. So we are working on it. We have made B3, we have made B7, we have made B8. So we are working on it to see whether the other hydroborate species can be trapped with this metal Cp2 fragment. Hopefully, in future, we'll get more success with under different reaction conditions. Finally, I would like to conclude that my talk. I have shown you a different organometallic, classic organometallic species mimicking by boranes molecule, both with a single boron and the diboron species. First, we have made a neutral B7 heptaboron species. And most exciting, we are very much excited of this planar B6 molecule. This is the first time happened that a B6 can be stabilized, parent B6, in the coordination pair of a titanium and the vanadium, which was proposed long back by many of the theoreticians. Now it's a dream, and most importantly, they are now stable. We can do even column to separate this molecule. Finally, I would like to thank the people who did this work. The diboron work done by Bijan Mandal, who is with Manfred Humboldt, Kaushik, also the classical diboron is with Holger Braunschweig at the Humboldt, Ranjit, who just defended his thesis, Saurav and Anagha, who did this diboron, the B6 molecule, Gitarani Yuvraj, who is now with Cameron Jones, did this borylene stabilization. My collaborator, Edie Jamis, LS Wang, and my big thank to Babu Varghese, who helped to solve all those very difficult structures, and Sudha Devi IIT Madras for the X-ray. And of course, the support from the DST, SCRB, CPIPRA, CSR, and IIT Madras for BGWE doing all this fundamental chemistry. And I'm really, really thankful to all these funding agencies to support for the last 16, 17 years. And finally, I would like to thank you for your kind attention.
Thank you, Sundar. Wonderful area of diboron molecules and the stabilization. Anyone, can you please raise hand if you have questions? Well, before I see some hand, let me just ask you. So tell me, what is the working principle that stabilizes this unusual, not unusual in the sense that those have been predicted before, but that what is the, again, working principle that allows you to stabilize this molecule?
Well, I mean, it's many of the things, like a lot of effort been gone to make this. Now, see that vanadium chemistry, we have been working almost 3 years to have this B6. But titanium one is a very recent result.
No, Sundar, I'm asking in the terms of bonding, that what does allow it to stabilize? Like one can go from vanadium, titanium, or many other late or early metal, but I'm just trying to understand how to choose a metal system. There must be, because I could see some interaction, some diagram where you have figured out the donor acceptor, that how much of interaction from the boron unit to the metal unit, and the vice versa. So do you have an understanding that what does stabilize these things?
See this in terms of, I guess what you trying to ask me about, I mean, is it like whether you had any objective of the B6, B2 or something, that you have a principle which metal fragment it will stabilize? So typically we look into early and the late transition metal, and most of the cases our approach was to a cluster buildup reaction utilizing the BH fragment. Like if you say that like once you take a diboron, the BH3, and if you pyrolyze it keeps generating all these different fragments like BH, B2H6, B3, B4, B5, B6. Now, depending upon the transition metal, it can simply catch those fragments. Like if you have a diboron, like which you generate when you pyrolyze or photolyze. So depending upon the transition metal that you use, so the yield of this molecule always extremely low because it has other fragments in the reaction mixture. However, some of the fragments that the transition metal is happy to coordinate with to satisfy all those weights rule, electron counting rule, so on and so forth. So to answer your question, I think we don't.
Well, so what I'm looking forward is that can you identify what are the predominant interaction between the boron unit and the metal unit? Is it there's a tremendous amount of covalency, or it's a donor acceptor stabilized system?
In cluster, it's all like a 4-center 2-electron or 3-center 2-electron kind of bonding, and it follows very nicely. Like as you could see that most of the molecule that we have made, it follows a very nice weights rule. Okay, you can use that one with a fragment as well as BH, very nicely corroborate with the weights rule or the Mingo's rule. And based on that, whenever you get any geometry, and interactions is all like, it's a 3D aromaticity or a 4-center or 3-center 2-electron bonding. Interaction, probably I am not the right person probably to explain the typical bonding in these clusters or this diboron species.
Okay, good. Sakur.
Sundar, very nice talk. Sorry if I missed the last part. So the question is on your B6H6 molecule. Is this compound aromatic, anti-aromatic, or non-aromatic?
Well, Saku, we have no idea. These are very new. We are working now. I'm still about to send this molecule to GEMIS for calculation. So probably, hopefully, we'll see how. Most likely, we might get a aromaticity of this B6H6 6-, which is stabilized in the titanium case.
Okay. Okay. Yeah. Thank you.
Okay. I don't see any hand raised. So please join me thanking Sundar. Wonderful chemistry. The compound predicted not to be stable for so many decades, and that you are able to actually structurally characterize it, and that will initiate a different understanding even in the bonding and even the structural aspect. Thanks, Sundar.
Thank you, Jiten. Thank you very much.
Okay, we now move to the next talk. Next speaker is P. Tilagar. He is currently a faculty in the IPC department of IISc Bangalore. He is an alumni of IIT Kanpur. His primary research interest is chemistry of main group elements containing luminescent dyes. He also has a very strong program on the medicinal aspects of boron containing peptides. He is well recognized. He is elected Young Associates of the Indian Academy of Sciences. He is a recipient of CRSI bronze medal. With this very short introduction, Tilagar, floor is yours.
Thank you, Professor Jiten, for your kind words of introduction. Is my slides are visible now?
I will let you know. It takes some time. Not yet. Can you do one thing? Can you unshare and share again?
Okay.
I do not know the scientific logic of it, but see if that works. Yes. Can you go back to the first slide?
Is it visible now?
Yes. Full screen.
Yes, I did.
Perfect.
Yeah.
Go ahead.
Yeah, thank you. Thank you, Professor JKB, for your kind words of introduction. And also at the outset, let me thank organizers, especially Professor Krishnan, for invitation and putting up a great show. And also, nothing can satisfy the hungry stomach. So we are ready for our lunch. But the past two speakers, they did a wonderful job. They put you at the excited state. Let me complete my talk before you take free fall from there. Okay, before getting into the details of today's title, I would like to briefly mention upon what are the different type of research activities has been going on in our laboratory. Basically, we have a strong inclination towards boron. If you look at tricoordinated boron, the number of valence orbital involved in bonding are higher than the number of valence electron. As a result, it left with one p orbital which stands perpendicular to the trigonal plane. Okay, it's intrinsically electron deficient and also coordinatively unsaturated. Since it's coordinatively unsaturated, if you add any nucleophile, it can come and bind to the empty p orbital. If you compare these two moieties, this is electron deficient, here it's electron sufficient. Here it is coordinatively unsaturated, here it is coordinatively saturated. We utilize this structural and electronic perturbation to sense nucleophile or activate small molecules. Instead of a simple isolated nucleophile, if the nucleophile is a part of an enzyme, for example, here I am showing an active site of an enzyme, which is proteasome, which uses the nucleophilic hydroxyl functional group to cleave a peptide bonds in the proteins. Okay, so which controls various process, intracellular process. If we selectively deliver a Lewis acid to this active site, one can block or modulate its activity. Okay, that's what we do. Instead of making a C-terminal peptides, we make a B-terminal peptide where we introduce a Lewis acidic boron center and we can modulate the enzyme activities. We call it enzyme modulators. Apart from that, if you introduce a boron into a pi conjugated system, the empty p orbital on boron can have an interaction with the incoming pi system. This interaction is more facile in the LUMO, in the sense it can stabilize the LUMO. If it stabilizes the LUMO, that means you are making the molecule to accept the electron easily. So one can
generate a N-type organic semiconductors by introducing boron into the pi system, which are very rare and also in high demand for optoelectronic materials. But from that, we also exploit this BNCC isosterism for developing various materials. If you look at these two moieties, it's a homodiatomic carbon-based system. 2 atoms are involved in bonding and have a 4 + 4, 8 electrons. If you look at here, the BN unit, again, 2 atoms are involved, boron and nitrogen, 5 electron from boron and 3 electron from, 5 electron from nitrogen and 3 electron from boron, from total 8 electrons involved in bonding. But compared to CC double bond, if you look at boron systems, boron nitrogen system, there is a huge electronegativity difference between boron and nitrogen. As a result, the sigma bonding electron are very close to nitrogen center, but it has a lone pair. So this lone pair will be donated to the empty p orbital and boron center. So there is a synergism in the bonding. So you give sigma donation and take the pi electron, give and take synergism. So it's in a layman sense, I can describe it as a metal carbonyl bond. Okay, so it's metal donates, carbonyl donates and takes the pi electron from the metal center. So we utilize this synergism in the bonding and develop various materials. What we do in our group is we use these concepts as a guiding principle in developing various materials and medicinal molecules. And our efforts in this field of research is well documented in literature. I don't want to spend time on this one. Without that, let me move on to today's title, where the exploiting BNCC isosterism for generating delayed emissive materials. So I kept a very fundamental slide. Before that, let me say what is the overall conclusion of my talk, which is based on the structural and their optical properties, that how a small change in molecular architecture, connectivity, and conformation can greatly affect the luminescent properties of small molecules, and also how the solid state emission of a molecule is intrinsically dependent on their bulk organization, not the isolated behavior. And also, I will also show a few examples where a very simple functional changes may also bring upon unusual properties, and also it gives us opportunities for further developments. Okay, this slide I kept it for the sake of students' audience. It's a simple Jablonski diagram. If you supply energy to a molecule in the ground state, it will go to the excited state. From there, it can undergo vibrational relaxation or undergo internal conversion, come to the lowest excited electronic state. From there, it can come to the ground state. If this process is radiative, we call it fluorescence. Okay. If the energy match is perfect for the triplet and the singlet, then it can go from singlet to triplet state. Okay, from the T1, it can come back to the ground state. If it's radiative, we call it phosphorescence. Like the forward intersystem crossing from S1 to T1, there is a possibility that it can go from T1 to S1 state. Since it's going from, this one is a forward direction, this one is a backward direction, it's called reverse intersystem crossing because it's going from triplet to singlet. After reaching singlet S1 state, it can come back to the ground state. If the process is radiative, then we call it delayed fluorescence. The reason because it spends some time in going to triplet and coming back to singlet state. So that's why it's called delayed fluorescence, because it's called fluorescence. The reason because it's coming from the same S1 state, the spin state from S1 to S0. So the singlet states involved. Okay. So how do we differentiate the delayed fluorescence and phosphorescence? The energy. Okay. The triplet states are always lower in energy. So the emission will occur at a lower energy region. The S1, the fluorescence will occur at the higher energy region. The energy of your fluorescence and the delayed fluorescence will be the same, but the lifetime between the delayed fluorescence and lifetime of delayed fluorescence species is much higher compared to the fluorescent species. Okay, so based on this energy and the lifetime, one can differentiate whether it's a delayed luminescence or phosphorescence. Okay, this type of material find a lot of applications in various things like organic LEDs, and also this reverse intersystem crossing from T1 to S1 can happen only if there is a sufficient energy match between T1 to S1. Okay, so because the T1 is more stabilized compared to the S1, most of the times the energy difference is very high, so the reverse intersystem crossing won't happen. So to increase the energy of this T1, in 2012, Adachi and co-workers came up with a very nice idea, in the sense they spatially localized the HOMO and LUMO of a molecule by twisting their structure. For example, here I'm showing, I listed out 3 molecules. This is a donor moiety, it's a carbazole-based donor, and we have a acceptor unit. Okay, if they put a substituent at the ortho position so that they won't be in a plane. So there is a twisting. If you twist the molecular, I mean the donor acceptor, that means you are spatially localizing the HOMO and LUMO. If you spatially localizing the HOMO and LUMO, one can reduce the energy, the energy difference between a triplet and a singlet. By using this simple concept, they developed a device with this architecture having an external efficiency of 20%. It's a very high external efficiency for a device with the small molecules. Once the concept is rebuilt, there are many people came up with the twisted molecular architecture and come up with a lot of designs. However, the problem with this design strategy is that once you twist the molecule, that means you are spatially localizing HOMO and LUMO, that means you are reducing the overlap integral. If you reduce the overlap integral, that's going to affect your oscillator strength. That the oscillator strength determines the quantum efficiency. So one may sacrifice the quantum yield of the compound. And one more thing is that this triplet to singlet upconversion is energy driven process. You have to supply some external thermal energy to pump the molecules from triplet to a singlet. So once you give some more energy, that means the triplet to singlet is a spin Faruden transition, so one can enhance the non-radiative decay. We had a question in 2012 that can we design a molecular system which have the sufficient amount of HOMO-LUMO overlap, so one can enhance the oscillator strength and improve the quantum field, and also can we make a system which gives delayed luminescence independent of temperature. Okay, it's independent of temperature. For that, we have chosen BN system. The reason because if you look at the Al-Said rule, he stated that when the two orbitals involved in the triplet singlet transition, if they are in a different symmetry. For example, here 5 pi star singlet, if it is interact with the n pi star of a triplet, then the spin orbit coupling is faster. Spin orbit coupling faster in the sense the transition from singlet to triplet is quite possible. Okay, so if you look at the BN system, this architecture is nicely built in this system. So in 1976, if I'm not wrong, Williams did a lot of photolysis, laser photolysis of aminoboranes, and he came up with the orbital configuration of aminoboranes, saying that the singlet is in the n pi star is the singlet, lowest energy singlet excited state of these aminoboranes, and the triplet pi star is the the triplet pi star is the very close in a close match with the singlet state. So there is a possibility that the spin orbit coupling between these two states are allowed according to Al-Said rule. One can develop nice delayed emission systems. So keeping all this in mind, we synthesized a series of molecules. Before that, we are not the first one to synthesize these molecules. These molecules are known for quite a long time. So, but yearly studies mostly, concentrate on understanding the structural aspects of boron and nitrogen compounds. Whether it's a single bond or a double bond, if it's a double bond, how one can tune the interaction between this boron and the nitrogens. Later, most of the attention are given to using these molecules as a drug molecules, but the solid state emission and their emissive properties are not explored much. Okay, then in 2016, we synthesized and characterized a series of compounds. Here, so if you look at these compounds here, we don't have any substituents on the molecule. Again, just the difference between these two is one methyl group. You may think, what is a single methyl group going to make a difference? I will let you know later. So then we introduced a single donor. then introduce two more donors on this system. Okay. If we compare the optical features of these boron derivatives with carbon-carbon double bond derivatives, their optical features are exactly the same. That means that this boron nitrogen bond is nearly non-polar like a carbon-carbon bond. Okay, but once you start perturbing them with either structural or electronic perturbation, then it behaves completely different. So if you want to shift the color from blue to a cyan blue, you have to introduce 4 amine donors on the CC double bond unit. But we can achieve that color with one single substitution on boron, BN motif. And also we can shift this color from cyan blue to green with just two more substituents. What I'm trying to say here is this BN motif is highly susceptible for electronic perturbation compared to the CC double bond. Once we established this one, we went on to make other molecules and study their delayed fluorescence characteristics. Here I listed out 3 BN molecules. One is with pyridine 4-pyridyl. It's a kind of donor, weak donor. Then one can modify or modulate the electron donating or accepting capability of pyridine by changing the position of the nitrogen. Then we produced weakly donor for 3-pyridyl derivative and also strongly accepting 2-pyridyl derivatives. Okay, let me take only one of this example and explain what we got. So this is the simple synthesis route. Then once we have that dibromo derivative to the metal coupling, and one end up with these derivatives. This vinyl derivative is known to undergo photodimerization in the sense 2+2 cycler addition. What did we do was we just exposed this compound to the visible light. It undergoes, we were expecting it may undergo oligomerization because we have 2 double bonds, vinyl bonds, positioned nicely positioned in 2 different angles. We thought that it may undergo oligomerization, but surprisingly, we end up with a dimer. How do we know it's a dimer? We did proton NMR in the case of starting material, and in the sense it's a monomer species. You don't see the proton corresponding to the cyclobutadiene. So that is cyclobutane ring. So this in the starting material. Only in the dimeric case we can see. And also, if you look at the monomer, the vinyl peaks, this vinyl peak appear at this region. If you look at the dimer, we do see the residual vinyl peak in the dimer. Okay, after confirming with the NMR, we also did single crystal X-ray diffraction studies. We can do all crystal to crystal transformation or take a powder and expose it to the sunlight. One can obtain this dimerized product. Okay, to get further insight into why it's not forming a oligomer, why it stops at dimer, we did a crystal analysis. If you look at the interaction, intermolecular interaction between these motifs in solid state, so if you consider this one molecule, it has 2 interactions. One is with this molecule at a distance of 3.83 angstrom, and here the distance is around 4.8 angstrom. It's very long. So as a result, this interactions obeys the Schmidt's criteria in the sense if a molecule should undergo 2+2 cycler addition in the solid state, they should be positioned, the double bond should be positioned at less than 4.2 angstrom. In our case, it's much less, but this one is very far. So as a result, once you apply or supply photon of energy, only these 2 bonds undergoes dimerization, leaving this bond untouched. So that's why we are getting only their dimerized product, not the oligomer. If you look at their optical properties, or I just put the optical properties of both the compounds, but let's consider both are behaving similar. So let's consider this part. See, the blue color, dark blue color spectrum represents the prompt emission. That means collecting the light just after photoexcitation. It's dark blue color. Then this light orange color one represents the delayed emission. Delayed emission means collect the light from the molecule after few microsecond delay. So if you look at the energy of the transition, both are in the same region. In the sense the fluorescence as well as the delayed emission in the same region, either at 298 Kelvin or either at room temperature or at lower temperature. So it clearly indicates that our molecules, that the BN derivatives shows a delayed emission independent of temperature. Okay, so if you look at the lifetime, because the lifetime is very important to see whether it's a delayed emission or phosphorescence. If you look at that one, see the peak at for this region, either at 77 Kelvin or 298 Kelvin, it has both microsecond time as well as a nanosecond. Nanosecond for the fluorescence and a microsecond for the delayed component. Okay, so we succeeded in developing a simple molecular system which can exhibit delayed luminescence independent of temperature. Okay, then we thought of introducing heavy atom like sulfur. The reason because the sulfur, the heavy atoms can enhance the spin orbit coupling in the system. Then it can facilitate the transfer from a singlet to the triplet transfer. So here, if you look at these two molecules, the difference is here you have a mesitide, there's an additional methyl group here. Here we have a xylene, which has only that methyl group absent here. Okay, since the spin orbit coupling is stronger here, so the T1 state is more stabilized and it shows phosphorescence rather than delayed component. Here in both the molecules shows phosphorescence at room temperature. Okay, and also, so this molecule shows phosphorescence. Again, this molecule shows different properties like a triboluminescence, in the sense it can emit light when you press the crystal, it can give us a light. So the difference between these two motifs, if you look at it, just one methyl group. This methyl group makes a lot of difference in their solid state packing and impart completely different optical signature in this molecule. Okay, what's the possible mechanism for this? So the triboluminescence mechanism is not fully understood well, but based on the available data and the literature reports, we put up some possible mechanism, in the sense this molecule crystallized in a polar non-centrosymmetric piezoelectric space group. In the sense, if you press the crystal, this crystal can get charged. Okay, so this the recombination of the charges produces excitons. The free fall of those excitons to the ground state via radiative decay, we see the light. Okay, if it's not radiative, then we don't see the light. In our case, fortunately, this process is the free fall of exciton to the ground state is a radiative process. That's why we could be able to see light from these molecules. Okay, with this, let me move on to the slightly different topic, in the sense, so this molecule is not fully non-centrosymmetric, but it's centrosymmetric system. Fortunately, it crystallized in non-centrosymmetric space group. We got interesting properties. We thought of, can we inbuild non-centrosymmetry into the system? For that, we introduced a chiral pendant into the molecule so that we can inbuild the non-centrosymmetric in the system. And also we studied their ground state chiral purity and the excited state chiral purities under the optical studies. I don't want to spend much time on this one because one of my students, Jusaina, presenting poster on this one, and the poster number is 7. If anybody interested, you can visit that poster. Okay, and also though the BN derivative got a lot of attention in the recent past, but the ultrafast dynamics, how these excited states are behaving, how these excited state dynamics in this molecule is not well understood. Further, we have generated series of BN derivatives and studied their excited state dynamics, and some of the molecules shows the stimulated emission before going to the triplet state. This again, one of my student Muntasir is presenting poster on this one. I don't want to spend much time on that. Okay. So far we discussed about by introducing a substituent onto the boron having mesitide as a kinetically protecting group. The mesitide which can provide a kinetic stability to the boron center. Then we thought of replacing this mesitide with a larger pi system. Okay, when you introduce a larger pi system, we are going to have a competition because the empty orbital on boron can have interaction with nitrogen, lone pair, or it can also have an interaction with this aryl system. Okay, if this pi interaction is more stronger, then one can see the pi star emission. If the boron nitrogen, I mean the lone pair interaction is stronger, one can see the CT emission in the system. If both are coexist, both the species are equally populated in the system, then one should see the emission from this moiety as well as this moiety. So I just pictured the emission spectra of these compounds may have a different, I mean, almost 3 different spectra. Let me simplify it for you. Okay, this spectra we recorded using THF, 2-methyl THF as a solvent. This 2-methyl THF, once you frozen it, it will behave like a non-polar matrix. It's completely non-polar. It's like a simple cyclohexane kind of behavior. So this blue color represents the prompt and delayed emission collected at -77 Kelvin. In the sense, it's a completely frozen matrix. You don't have any freedom for the molecule to undergo rotation. So you'll see the nice interaction, I mean the structured emission. Okay, so this possibly because the pi interaction between the boron p orbital with the anthracene moiety. And also that we also got the lifetime, which behaves like a pi star transition. And once you increase the temperature from -77 K to 200 Kelvin, that means you are allowing the system to melt, but it's not completely non-viscous like simple THF. So it's become fluidic in the sense the molecule have a freedom to rotate. So once it got some freedom, it emits from the charge transfer state. In the sense, the lone pair on nitrogen is transferred to the boron center. You have a CT characteristics. You can see this cyan blue color spectrum represents the interaction between the boron and the nitrogen units. Yes. And also, if you look at the spectra, it's structureless in the sense the ground state and the excited state geometry are not the same. So you don't see the structured pattern here in the case of the charge transfer pattern. Once you increase the temperature further, I mean, it's a 300 Kelvin, that the red color spectrum represents these things corresponding to the temperature at 300 Kelvin. You could see the charge transfer emission as well as the emission from the pi star. That means at fully fluidic medium, in the sense completely melted system, and also you have a thermal energy is sufficient enough to equally populate these 2 species, and we are getting emission from both the units. Again, if you look at the lifetime, again for each and all the either it's a 77 Kelvin or it's 200 Kelvin or at 300 Kelvin, you could see both nanosecond and microsecond species. That means we can, wherever we see the prompt fluorescence, we could be able to see the delayed luminescence. Again, this molecule also behaves, what is that, temperature independent delayed luminescence characteristics. Okay, so then we decided whether the synergism in the bonding between boron and nitrogen plays a major role in this temperature independent delayed fluorescence characteristics of this compound. We just separated this boron and this nitrogen by introducing a spacer between them. And also we introduced a lot of substituents to avoid the through bond interaction between this boron and nitrogen. This is highly sterically demanding substituent as a dural group. Okay, so if you look at the photoluminescent characteristics of this molecule at room temperature, this is for these 2 spectrums, this purple and the blue. The dark blue is for the fluorescence and the purple is for the delayed fluorescence. Both are the energy is the same, and at the lifetime also it has a microsecond as well as the nanosecond. It clearly says that it's a delayed fluorescence. But when you reduce the temperature at 77 Kelvin, this red line represents the fluorescence and the green line represents the delayed fluorescence. That means it's the phosphorus. The energy of these 2 peaks are wide apart. In the sense, at low temperature, it gives a phosphorescence. At room temperature, it gives delayed fluorescence. That means once you remove the synergism between bonding interaction between boron and nitrogen, this in temperature independent characteristics goes on. Okay, so based on these results, we could conclude that the bonding interaction between boron and nitrogen in the BN systems plays a major role in controlling the reverse forward or reverse intersystem crossing in these systems and make it independent of temperatures. Okay, with this, I'm moving on to my last topic, which is boron nitrogen containing heteroazenes and its fullerene complexes. So far we discussed about these aminoboranes, where it's kind of open chain systems. So we want to bring this BN unit in a cyclic system. Okay, and also we explained in detail how one can perturb the electronic properties of a carbon system by introducing the BN pore, because this pore is highly susceptible for electronic perturbation. Okay, and also we thought of, instead of having a covalently linked boron nitrogen system, how this boron nitrogen system, if you allow this boron nitrogen system to interact with the other molecules or the system supramolecular, how does it affect its electronic properties? For that, we have designed a few molecules. I'm showing only a couple of them here. So, and also, why do you want to make a complex with fluorine? Fluorine is a very interesting system. It can accept 6 electron. You can see the 6 redox process, individual redox process. It's a very good electron transporter, but the problem with fluorine is it will aggregate quickly and it's insoluble in most of the things and make the life very tedious. For that, several groups came up with the different strategies to de-agglomerate them. So for that, they come up with a fully carbon-based system. They can trap it, and also with the non-planar heterocyclic system and trap those fullerenes, and also they come up with the planar porphyrin. The conductivity, the high conductivity of fullerene is because they are placed close by. That's why the electron can go from one fullerene to one fullerene. If you trap them and separate them individually, and if you increase the distance between fullerenes, then the conductivity, you are going to sacrifice the conductivity. For that, we thought of coming with a little bit of different, molecular design, in the sense, I'm sorry. Here I just listed out what are the different type of BN motifs are already known in literature, and none of them were complex with fluorine, and most of them are planar structure, not non-planar. This one is completely non-planar, but these systems are mostly planar structures. So here, this is our designed molecules. We have a heterocycle fused BN system. This heterocycle is completely non-planar because of this lone pair on a nitrogen, and this sulfur can make the system puckered. And also, if you look at the porphyrin is a nice planar moiety. But once we introduce BN onto the system, then it will, because of this tetrahedral symmetry of this boron, it will induce the strain in the system and make it helical. Okay, we synthesized this molecule and also we isolated the different isomers, either cis or trans isomers. And I'll take only one. Yeah, I'm done almost. I'll show you the crystal structure of this one of these moiety. If you look at there, they are completely non-planar. You can see the half circle kind of things. For this, for the phenyl, this phenyl derivative, and also this is for the pentafluorophenyl derivatives, pentafluorophenyl substitute derivative. So then, also if you look at the other derivatives, these molecules are completely different. In the case of porphyrin, you have a single curvature, but in the case of this fused systems, we have a double curvature. It has one curve here, this side, and also other side of the molecules. You can see one side and the other side of the curve. So it can interact, the single molecule can interact with the 2 fluorine molecules. Okay, like this. This is what we got. So our molecules, in our case, these fullerenes are nicely arranged in the columnar manner, and also these columns are surrounded by our molecular systems. It's nicely surrounded by our molecular system. So again, one of my student, Rajendra Prasad, presenting poster on this one. So without spending much time on this, let me conclude my talk. I'm sorry, one more. We also very recently, we are venturing into phosphorus chemistry. Based on phosphorus chemistry, we synthesized a series of molecules which can exhibit interesting properties like room temperature phosphorescence or ultra-long phosphorescence material. Here the advantage in the phosphorescence is that he can move from oxygen to sulfur, sulfur to selenium. Though we are sacrificing the electronegativity difference between phosphorus and the oxygen, but we gain more in the pi star orbital of this sulfur and selenium. So that can play a major role in their optical signatures. With this, let me conclude my talk by acknowledging my students who did all the works and my former and current PhD students, my collaborators for the structure solution and studying other CPL chiral photoluminescence, and this generous funding from various funding agencies like IISc, SCRB, CSIR, and Joint Solar Energy Research Center for India and USA, and ISRO for funding. With this, I thank you all for your patience, and also once again I thank Krishnan and Co for their kind invitation. Thank you.
Thank you, Tilagar. Any queries or questions? Well, Tilagar, I'll just start. You have demonstrated that when you have a boron nitrogen directly connected, and when it is you make the disconnection, nitrogen is far, there is a stark changes in the photophysical property. What I'm trying to understand is that is it due to the inherent boron nitrogen bonding, or it is because of the secondary effect? When you do not have the boron nitrogen connected, then you have structural changes on the other part of the molecule that would in turn change the stacking of the molecule. So whatever is the manifestation of the photophysical properties are because of the changes that is happening in the secondary region rather than the disconnection of the boron nitrogen unit. Yeah, I'm not sure whether I was able to convey correctly.
Let me go to that slide so that it will be easy for me to explain that.
Yeah.
Yeah. So when you have a boron nitrogen system, the aminoborans, where you have a boron and a nitrogen direct connection. Okay. The energy difference between the triplet and the singlet are very close. And also there is I believe, I am not a theoretician, we need to do a lot of computational studies to understand the bondings, the vibrational coupling between these two motifs to make the intersystem cross much faster. But here, once we remove that synergism, okay, that triplet of this moiety is more stabilized. Okay, it's more stabilized compared to the singlet. As a result, the intersystem crossing from a triplet to the singlet became more difficult. So it's, in my opinion, it may be due to the direct interaction between the boron and the nitrogens, not due to the secondary structural perturbations. In all our BN derivatives, except, again, I showed you one more example in the sense when we introduce strongly heavy atoms like sulfur, again, it stabilizes your triplet. In the case of aminoborans, it stabilizes the triplet, and there is a intersystem crossing from singlet to triplet. Since the triplet got stabilized, we are getting phosphorescence, not the delayed fluorescence.
So it's the intrinsic nature of the BN bond that changes.
Yes.
Okay. Let me see if there is there is no hand. So let me continue with one more question. Well, I see Todd is here. Todd, you can go ahead.
Hi, gentlemen, Tilagar. I just wanted to ask whether you were aware of a paper back in 2012 by Yamaguchi and Stefan Early on carbazole B MES2 compounds and their ticked behavior.
Yes, yes, we do know that. Yeah, I do know that one. So he published 3 papers on that. One is in a Dalton trans, one is in a physical chemistry about the trick and other things. Yeah.
I just thought it was fairly relevant to your BN.
I mentioned in one of my slides, I mentioned that one.
I missed
That shows tweaked and also it's a phosphorescent, not a direct luminescence.
Mm-hmm.
That sense, it's phosphorescence. Again, it's a big donor compared to what is that? Phenothiazine. Since it's a planar system, it can go to the twist geometry compared to our non-planar. This one, what is that? Phenothiazine. So the twist behavior is more predominant in the case of when you use planar carbazole. Here, since the ring is puckered, still it can accommodate and come in plane with the boron. We don't see tricked behavior in this system.
Thank you.
Okay, thanks. No more hand. Maybe I'll have just one question, Tilagar. What I was looking at that your porphyrin nickel molecule, you say that there are 2 curvature, and that as you predicted, it happens that a fullerene molecule does get attached to the, if I can use the word attached to that 2 curvature. I was just trying to understand on the ligand part, what are the interaction, because they are all lot of electron density, lot of pi cloud. I was trying to understand what are the interaction that is responsible for that more directed assembly, and on the same way, when you form this column of fullerene, what are the predominant interaction there?
Yeah, that's a very interesting question. Thanks. So the interaction between our molecule and the fullerene is the BN motif and the sulfur. They have a interaction with the fullerene pi system. Okay.
It's electrostatic. I do not now. Everything is electrostatic, but so it's a within the molecule there are charge distribution, and that's how it gets.
We haven't done it, but there should be some kind of charge redistribution there, because when we did the simple HOMO-LUMO calculations, the HOMO is localized on our molecule and the LUMO is localized on the fullerene. Okay, and also if I look at the interaction, the sulfur and what is this fullerene and the BN and the fullerene are quite different. Okay, this is both the BN moieties interacting with the fullerene phase, but here only the sulfur lone pair, maybe the lone pair is pointing towards the kind of chalcogen kind of bonding. There should be some electron distribution.
I guess other than HOMO-LUMO, looking at the HOMO-LUMO, I guess the electrostatic charge density analysis will give you that.
Yes, we did it.
Which part of the molecule is positive, which part of the molecule is negative. Okay, I get the idea. There are no more questions, so please join me thanking Tilagar for his excellent presentation. Let me also take this opportunity to thank all 3 speakers in this session, Professor B. Chandrasekhar, Professor Sundar Gopal Ghosh, and Professor P. Tilagar for sticking to the time and describing their beautiful chemistry. And thanks the organizer for giving me this opportunity to be a part of this symposium. Thank you.
Yeah, thank you very much, Professor Jitendra K. Bera, for sharing this session, and also thanks all the speakers of these sessions. We will get back to 2:30 IST time, And in between, there will be a poster session. And from 1 to 12, over presenting the poster, they can stay in the online. And the judges will interact people who are having the posters 1 to 12. If they have, the judges have any doubts, they will interact with you. And the rest we will join at 2:30. We'll come back at 2:30 in India's time. Okay, thank you.
Usually. Is there any option we can switch off the video? No? That is that I take part. That I cannot see, let's say, what the people are saying. Yeah. Nobody means no video, no audio. But in your case, it is video and audio both are. Yeah, but them still must No, not yet. I think till 10 it's a break, no?
Yeah.
No, at 10 is a break. I have to start 10:30, right?
Right. But before that, we have to be ready.
Good afternoon, Professor Rajeski.
You know this guy?
We'll start in 25 minutes.
Whether your voice is audible or not.
What means? This is the same. But this is not. You can click. The left should go left side.
Yeah, left. That can first you ask whether they are your voice is audible for them or not. Is it ready?
Hello. Yeah. Yes.
Yeah. I think after some time it will start automatically.
What does this mean?
Means they are host. So sometimes they come to check whether everything is okay or not, and sometimes they are off. But in your condition, you are visible clear.
Teilnehmer ausblenden.
You removed all.
Yes, yes.
You can start whether you will see how many.
Their connection.
Where did you get it?
Yeah, what I shall do.
You do once again. Some list was coming. You come to that list.
Stoppen. New.
Yeah, you come here. Try given.
Camera is on, that's that you can see, but but I do not know, let's say, when I can start and talk. Do you know?
I can see.
That means a filter. Yeah. It shows the what. Webcam.
Yes, is already.
And him. No, go back. Oh, let me do it. Someone must speak. But who can we move to him?
Yes, I'm searching that. Maybe they are on break. That's why we are not able to.
No, when you say, let's say, I start 10:30, yeah, then we have 20 minutes. That's it. It's the time. Nothing to do. Connect. Here.
Can I send it?
Yeah.
Maybe they will.
Should. That means more. Hello, can you hear me?
Good morning, Herbert.
Hello, can you hear? No, he does not react. Hello, can you hear me?
Can you hear me?
Chandra.
Hi, how are you doing?
Yeah, I think he can hear you.
But I cannot hear you.
Oh.
What can I do?
I will check with Krishnan. You can hear me? No.
Yeah, hello, sir. Hello.
Speaking.
Yeah.
Krishnan, Professor Roeski is not able to hear us.
Oh, really?
Yeah.
I cannot hear you.
You can remove your mic.
Everything looks fine, sir. We can hear you.
Yeah, they have mentioned we can hear you.
But I cannot hear you.
Can you log out and log in once again? Because, okay, he cannot hear.
There's a camera. Microphone. Here. Here's this microphone. This. No, this is with the left.
Working.
Microphone.
Yeah, it's all.
Yeah.
Now, can you hear?
This is, and this is the,
Yeah, we can hear you. No.
You have to.
Hi, Srini.
Good afternoon, sir. Yes.
So we both are in blue dress.
Yes, yes. Yes.
Professor Roeski is not able to hear us.
Yeah, that is what I am also closely monitoring. Not able to get connected. Professor Rice is having some trouble. Professor Rice. He was there in online. Yes. That also we can follow it up. Okay, he has to hear now. He has to hear. That chat is how to pronounce this. University front. Okay, this work can also not be said. That is better. Yeah, he came already. He came already. He had at least yes. No, he talked to him, but we are able to hear his voice, and he is not able to hear from us. What could be the reason? This one is off. I think that's okay. No, here we are able to hear. We are able to hear.
Other side, Germany, professor is not hearing our voice.
Something is not from us, not from us. EC sir is able to hear. So maybe EC sir is able to hear us. Not from. Okay.
Srini, there are some queries about how to join the poster session.
Yeah, that is there. Yeah, I think they have taken 5 minutes video session from all the poster people actually. That is shared with the expert members.
Expert members will go through the.
They will go through that video and then academy they will take a call. If any questions are there, they will be in touch with them directly. Yes. Yes.
Professor Srinivasan, how to join the poster session? How to join poster session? Poster session. How do I join poster session?
So poster session, I will share the link.
Oh, okay. Thank you.
So you can watch the videos.
Okay. Thank you.
Anytime you can watch it. I will share soon.
Okay.
There was one student. Oh,
He asked him to log out.
Yeah, no.
Can you hear me?
Yeah, we can hear you.
Can you hear me?
Yeah, sure.
Yep.
Hello.
Hello, Professor. Hello. Yeah.
Can you
we can
hear
see.
me?
Yes, Professor. Yeah.
Oh. Can you hear me?
Oh, just to type message. Just type. Can you hear us? We can hear you. Yeah.
Hello. Hello.
That should be okay.
Hello.
They have mentioned some chat. Should you give me?
Can you hear us?
What they are saying.
Hello. Hello. I don't see.
But now you're able to video mute or something.
There is no issue.
Oh,
Huh?
no. Can you hear us? No, he said no.
He said no.
We can hear you. Just
Or we can start maybe.
yeah.
We can hear you.
Yes, we can hear you. Yes. But the YouTube doesn't.
Okay.
Strange actually. Mute or something happened there.
No, his thing is fine, but some
audio channel.
there is a problem.
Same system.
Compatibility.
There is a compatibility issue.
Yeah. Compatibility.
Okay. So then we will go with the. Huh?
I think yes, headphone connected, but now not wearing.
Okay. How to fix it?
You have to tell him are you connected with some headphone
Your
or
screen was uninterrupted. Here. Here, not new. Here. Green.
Yeah, that's what do select there. Do you have headphone?
No.
Oh, students is there.
Yeah, somebody is. So, what he has today? No, he don't have a headphone.
No. Okay, then what should we do?
we need to check the audio channel of that text.
You have it.
No, I have,
Here.
but not big.
Hmm?
Small one. If they need, I can bring it.
Check the audio on the desktop.
Speaking.
You can check the speaker or microphone settings.
From this side, huh?
Yeah.
Check that.
Speaker and microphone settings make it same as the system or same as the computer.
Makes sense. They can hear you.
Same as.
I cannot hear you.
Oops. Ah.
We can see his screen, so it shows us something.
No, we can hear. But he's,
Yeah, we can see his screen. So if he shows us the settings, we can.
you just need to tell them that share your screen first.
So just check if any student is near to you, then so that he can share his.
Yeah, that's also fine.
Yeah. Yeah. Yeah.
Screen. You already
Yeah.
shared.
Only his presentations.
Yeah.
It's not full.
I think they are saying you can stand the lecture. You can stand. You can.
Maybe they are not.
I think your
Cannot hear us. That is. we.
I think he's starting.
Oh. Ask him to wait. It's possible to fix it.
Yeah,
If he shares.
In German language.
Yeah, but others.
Hello.
Others.
We will check how to do it.
Introduce you.
It's fine.
Yeah. That's
Yeah, could you wait for a few seconds? The share will introduce, then you can start. We are able to hear you.
You can start, right? No, this one also not working.
Okay, so the next is.
Could you wait a few seconds? The share will introduce, then you can start. Yeah, able to hear you. How can we start?
And now you come to your slides.
Direct them with the messages like where is the button and where to start. That will be better.
The slide.
The next chair will be Professor H. Srinivasan from NICER. So he will introduce Professor Royeski and others. Professor Srinivasan.
You down it.
Good afternoon to all.
Small size.
Thank you, Professor Krishna,
Yeah.
Professor Nammana, and the organizing committee members for giving me the opportunity to chair this
When
session.
they say you can
In
start,
this session,
then
we have 3 talks, 1 plenary talk and 2 invited lectures. The first speaker of this session is Professor H.W. Royeski from Göttingen University. There is no formal introduction necessary for Professor Royeski for the benefit of younger generation. I will briefly highlight his biosketch. He was the professor of inorganic chemistry at the Goethe University, Frankfurt from 1971 to 1980. And from 1980 to 2003, he was the director of inorganic chemistry of the Göttingen University. Currently, he is the emeritus professor at the Göttingen University. He received several awards. To name a few, in 2004, he received C.N.R. Rao Award of the Chemical Research Society of India. In the same year, he
Yes,
also received
introducing you, but I cannot hear the share. Yeah.
Award.
Share is introducing you, but I cannot hear him.
In 2005, he received Wittig Grignard Award. 2009, BRICS International Henry Moison Award. 2013, Annual Award for Chemistry and Institute of Chemistry of Ireland. 2018, he received Wacker Silicon Award, and in the same year, he also received silver medal from the University of Bordeaux. With this brief introduction, may I now invite Professor Royeski to deliver a plenary lecture. The title of his talk is "The Chemistry of Aluminum and Silicon is an Important Subject for Future Developments."
Kindly start.
No, you can start.
Where can I start? Here?
Here.
Here?
No, this is the start. You can speak.
What?
You can start.
Yeah, but
remove this. Yeah, now you can start.
can you hear me?
Yeah, all can hear.
Okay.
Yes.
First, I want to thank the organizers for inviting me. It's a pleasure to tell you something about my chemistry. Today, I will report on aluminum and silicon, and this is an important subject for future developments. Next. Thanks to my co-workers, Zakar, Nachish, Xiyang, Siddiqui, Ben Li, Hongping Chu, and support of Deutsche Forschungsgemeinschaft, they gave me the money. I'm thankful to the X-ray structure analysis by Professor Starke, Professor Dietrich, Dr. Regine Herbst, Irma, Professor Keim, Professor Schilwersky, and Stöckel. The DFT calculations by Professor Franking-Marburg, Professor Holthausen, Frankfurt, Professor Colley, Kolkata, Professor Parameswaran, Calicut, Kerala, and Professor Jemis, Bangalore. I show you the periodic systems with 90 elements. The green ones are those plentiful supply. But when you look, for example, to this one, the red, helium is a serious threat in next 100 years. This is also, let's say, true here for the catalysts, which are used in organic chemistry, ruthenium, rhodium, palladium, platinum, osmium, and iridium. So there will be soon, let's say, rising threat from the increased use. Also, when you buy a car with lithium as a battery, then it's lithium limited available. Therefore, we concentrate on aluminum and silicon. These are elements in the Earth's crust, which are plenty available. About here we have 7% and here 27%. We are looking, let's say, to the interstellar space about, let's say, molecules which are existing there. And in the interstellar space, of course, there are no chemists, no physicists, but by spectroscopy, you can, they are detecting molecules, but the distances are very far so that these compounds are stable. Here, short selection, molecules in the space. What you see here is elements in low oxidation state. And that's what we want to do. Let's say in aluminum and also, let's say, in carbon. Here, of course, let's say, it exists also C60 in the interstellar space. And the aluminum are having, let's say, oxidation state 2 here. And therefore, let's say, this kind of chemistry was not developed when we started this. It's very important for chemists. We all think alike. no one thinks very much. And that is important for doing, let's say, good research. I shortly will mention aluminum-1 compounds. And you can see here, aluminum-1 compounds has a lone pair of electrons and an R group. And it is like a carbene. We prepared this molecule a decade ago from aluminum diiodide. We reduced it with potassium and obtained aluminum-1, which is stable at room temperature, and you can isolate this. Many colleagues now using this compound, let's say with a lone pair, to do oxidative addition reaction. And so it developed, let's say, completely new chemistry. I only want to show you, let's say, this aluminum 1 and why can we stabilize this? Aluminum has 3 electrons, but when you count, let's say here you have a lone pair, the 2 electrons, 4 electrons, and 5 electrons. So the surrounding of the aluminum has more electrons as 3. And when we react this with acetylene, this is also in the interstellar space, with, we lose this in toluene at low temperatures, we are able to generate an aluminum cyclopropane. It is stable. And here's the X-ray structure, a 3-membered ring. And this compound can react further with acetylene, also at room temperature, no, at low temperature. And then the ring is opened, it forms, let's say, this alkyne with the transfer of hydrogen to this position. So even, let's say, with these no valent elements, you can do interesting chemistry. I want to mention, let's say, shortly, using aluminum compounds for catalysis. In this case, we have a hydrogen and a triflate. The triflate is important to polarize very strongly the aluminum hydrogen bond. And another aluminum which we are using is a dihydride for hydrogenation reaction. This is a ketone. The ketone can react with a pinacol carborane, and the hydrogen moves here to the carbon and the boron to the oxygen, so that you get, let's say, this type of molecules. You can hydrolyze this, and then you get immediately the alcohol. Very quick, simple reaction. Another, which we have published, is trimethyl cyanide, which we add to the aldehyde. And here you see, let's say, the hydrogen is in this position, then this CN goes in this, and here we have the trimethyl group is attached to the oxygen. And we have studied, let's say, in very low amount, the catalyst. And the yield is nearly quantitative. Now we use, let's say, also the dihydride for converting CO2 without solvent, that I have to say, without solvent, this pinacol borane, and then we get a methoxy group, And boron oxygen bond we can split and can generate methanol. The yield is 95%. We have to go to 100 centimeters and 1 atmosphere. The organoaluminum dihydrides catalyzes hydroboration of CO groups, of carbonates, esters, carboxylic esters, and carbon dioxide without using a solvent. That is very important, let's say, for the development in industry. They have not, let's say, to separate the molecules. I want to mention a few reactions which are, let's say, quite interesting. This is an aluminum with 2 alkyne groups, as you can see here. We add boron C6F5 3 times, and then we observe this boron C6F5 2 times attaches and moves 1 C6F in this position. So with heteroatoms, 5-membered rings are in general very stable. We were interested to see what happens when we look, let's say, the room temperature reactions with this used, let's say, here the beta-decateminate, here's a modified beta-decateminate, and this is an amidinate. So here you can see, let's say, already the boron has 2 of these groups, and adjacent is the C6F5. I want to show you, let's say, for this molecule, the intermediate, the X-ray structure. Then you see that we have from the aluminum to 1 carbon and from the aluminum to the other carbon. But in this step, the boron is still in the ring system. So when we heat it to 65 centigrade, then this moved out, and then the ring rearranges, so that we get the aluminum, as I mentioned before, with the 5-membered ring. Here's a C6F5 ring, and here's a 2,6,5 rings attached to this carbon atom. So the most stable is the 5-membered ring. Herein we have the alumol, which shows, let's say, an emission spectra and pictures of fluorescent emission. And this compound 2 and 2, and that is a bright yellow, let's say, compounds which you can prepare. It's very useful and easy, let's say, to prepare using aluminum. Also, want to show you, let's say, low valent boron compounds. This is CO. It's isoelectronic to N2 and also to BF and SiO, low valent. So this was reported already, let's say, in 1967 by Timms. And you see how high temperature he has to use, 2000 centigrade, to convert boron with BF3. So we were interested to generate, let's say, BF, because BF is also, let's say, a carbene type, has a free electron, and therefore we treated, let's say, this carbene, cycloalkylamminocarbene, with BF3, makes an adduct. That is the base, and this is the acid. And we take another carbene in toluene and reduce with KC8, and then we get the BF. BF with the lone pair here and stabilized, let's say, with these two adjacent lone pairs of the carbene. Now, when you look, let's say, to the cyclovoltammetry, this is, for example, here we start with 50 millivolt, then 100, 200, 300, 500. All are reversible. So you can see from that this molecule is very stable and can be used, let's say, doing interesting chemistry with the BF. This is a UV spectrum of this molecule. Now we did a reaction with this molecule. This is a BF, this lone pair, and treated this with lithium BC6 4 times the salt. And what we observed is the formation of lithium, and here is the cation. So one electron is removed and stabilized, let's say, this is a plus, and this is the anion of this molecule. The EPR spectrum is here simulated, and here in this, let's say, the experimental, that because we have the splitting of N14, 11 boron, and 10 boron. So therefore, let's say, the pattern is a little complicated. The X-ray structure of the BF and also, let's say, the BF plus is in brackets here. When you compare, for example, B1, F1, that is a neutral with the carbene with the 2 electrons, you find 1399. When we make the positive, then this bond 1.36, so it becomes shorter. But surprisingly, the adjacent bonds, B1C1 or B1C3, are becoming longer. I gave you, let's say, an example. B1C3 in the neutral compound, it's 1.5 and here 1.554. 2 and here 4. So, and this is also, let's say, valid for the B1C1. In this case, here we have this, and then in brackets, this one becomes longer. So this was mainly done by Motner-Zisch, and he used, let's say, this carbene, which we have prepared, let's say, a decade ago, with dibromoborane, and under this condition, we get this KC8. We remove this, we get a radical. So the radical is quite stable, and you have the radical on the silicon, you have the radical on the boron, and partly you have also the radical in this part of the molecule. We have published this with tertiary butyl and with N-TMS 2 times. This is the structure where we have one boron-bromine bond, and here, let's say, you can see the silicon the boron bond. So compounds of this type are, let's say, have not been published before. I change now to silicon chemistry, to the other part. This is very old chemistry. Silicon is treated with HCl to HSiCl3. From this HSCl3, all your chips in your computer, also in my computer, the origin is this molecule. And it is an exothermic reaction. This form, you have to use hydrogen. It's operating at 1500 Kelvin. So it is an endothermic reaction, but you have a lot of side products here. We tried, let's say, to improve this reaction, and Robert Gnann, head of the Wacker Silicon Business Division, said in the internet, since chlorosilanes also occur as intermediates in the production of hyperpure silicon and silicones, Rösky's work is pioneering and also of great interest for making process optimizations. So even, let's say, in industry, these low valent elements create, let's say, an important impact. I switch now to a phosphine and to a silylane. So we were phosphorus and introduced, let's see here, silylane. So both have lone pairs, and we were interested how, let's say, this influences coordination chemistry. This kappa chloride, one kappa, let's say, is coordinating to the boron, to two molecules. And as you can see here, the borons coordinating and the silicones are coordinating under formation of kappa dichloride. This is also, let's say, kappa dichloride. It's it's a dismutation, but not a disproportionation. In the zinc, also, let's say, phosphorus and silicon equally coordinate to zinc and to the silylane, this lone pair. Extended this with phenylboron dichloride. And in this case, let's say boron has only 4 orbitals. It makes a plus here, and this is the anion. This, and here again, you see that the silicon coordinates and the phosphorus coordinates to the boron. The aluminum trichloride has, of course, more than 3 orbitals which can be used, and therefore, let's say it's very easy to coordinate aluminum trichloride to this molecule. When we introduced, let's say, a more basic group, a more basic group, here the acyl, then it's preferentially it goes here to silicon coordinates, not to the phosphorus atom. This is a very new reaction which we have done very recently. This is a bisilane. We treated this with trimethyl silyl azide. And then you can see that this silicone here forms to 1 nitrogen. And this nitrogen has, of course, a trimethyl silyl group. This trimethyl silyl group makes a shift and moves here, let's say, to this trimethyl silyl. So in this case, we can, let's say, stabilize this, we call this a nitrone. I'll come back to this in a few seconds. And this silicone coordinates here with this lone pair, an additional lone pair to the nitrogen. Here you see is nitrine and binds to the silicone and here to the silicone. What is the difference, let's say, between this nitrogen and this nitrogen? Both have in the neighborhood this one silicon and the other silicon. But this silicon uses only 4 electrons. This silicon has 5 electrons. You can see here 1. Here is an carbene type. That's 3, 4, 5. One is a sigma bond, and this is a coordinating bond. So here we have the same, let's say, we have here 5 electrons. Therefore, we are able to isolate this nitron for the first time. It's not a cation, it's just, let's say, and you can compare this, let's say, with a carbon. Carbons have instead of silicon phosphorus here and here. And we have prepared, let's say, some years ago, silylones. And silylones have silicon here, also with 2 electrons. So this is quite an exciting reaction. We are not using, let's say, any reducing agents. No potassium and no anion. This is the X-ray structure. The X-ray structure tells you, let's say, that this nitrogen, the silicon, this nitrogen, and this nitrogen here are nearly in a plane. So there is a lot of back donation from the silicon towards the nitrogen, and from the nitrogen back, let's say, to the silicon. I have not time, let's say, to tell you all the details. Now, can we prove this? Let's say I mentioned that this is more sensitive, more reactive, this nitrogen, in comparison here to the nitron nitrogen. And we use the silver triflate, and then you can see, let's see, that the silver triflate coordinates to this nitrogen, not to the nitron here. Because the reason is, here we have only 4 electrons at the silicon. And here we have 5, and here we have 5. So I give you an example. Let's say I mentioned this already. That is a carbon. Here's a phosphine with the lone pairs. And here's a carbon with 2 lone pairs. Therefore, it's called carbon. And it has it's not linear. It has an angle. And here's a other PR2. And that is the same you will find, let's say, in the silylone. There's also, let's say, I think, an interesting reaction. That is a silane, and this is a nitrile. So we used 2 of these molecules in a ratio, and then the silane adds to the CN bond 2 times, this and this. It's important to have, let's say, in the para position, CF3, fluorine, Cl, and bromine, electron withdrawing reaction to activate the CN bond in this molecule. But when you look, let's say, carefully, let's say, to the X-ray structure, then you can observe, let's say, that the carbon shows an inverted structure here on this point here. And here, let's say, you can, from the angles, you can see normally you would expect that it is a tetrahedron with 109.5 degrees. But what we observe here is 55 and 57, and a super long carbon nitrogen bond. So this is And when we have compared all the carbon-nitrogen bonds which exist, and then we found that our CN bond is 23% longer. So it's you can say a world record for the CN bonds. This is a typical organic Huckel molecule, 2 pi systems with 3 carbon atoms. And the Huckel rule, as you know, 4n plus 2 electrons. If this is if n is 0, then 2 gives this an aromatic system. When we look to the literature, we found, let's say, quite a number of cations. Here, germanium, boron, and finally nitrogen. But we did not find any, let's say, neutral compound. So how can we generate a neutral compound? We have here a silylane, and we have here a dibromide, and we reduce 2 of these, and then we generate the silicon-silicon bond, a boron, and then we get an aromatic ring. This is a 2 pi system. This 3-membered ring is aromatic, and this was done by Jemis. The HOMO shows, let's say, the delocalization of the electron density over the molecule. When we treat this with an azide, then a nitrine inserts here, and only this part is still, let's say, delocalized. Of course, it's not any aromatic anymore, but we can incorporate and do reactions, let's say, to insert into the silicon-silicon bond. It opens up, let's say, quite new chemistry. This is this silylane, which I mentioned before. We treated this with aluminum hydride as an adduct, and then for the first time you get a 6-membered ring with 2 aluminum, 4 silicon, and this is nearly planar, this ring. Byproduct is an L means amidinate here, and aluminum. So we started with the silicon, and the silicon is replaced here by the aluminum. In the case of trimethyl aluminum, we have only, let's say, the interaction with acid, with base, with acid, with base. This is the X-ray structure of this molecule, and this is nearly planar with the silicon, aluminum, silicon, aluminum. I think it's an interesting development in this direction. Also, let's say, this is a calculation of the energy. It's a very, let's say, energetic molecule with 188 kilocalories. So I think I'm nearly at the end. If you have questions, you are welcome, and I hope I have shown you, let's say, some interesting results. Thank you for your kind attention. Thank you again for your kind invitation.
You can open this chat.
Yeah, now the seminar is now open for discussion. The issue here is professor is not able to hear from us. So those who are having the question kindly type, or you can read out your question so that we can put it in the chat box. He can answer.
Are there
accordingly.
questions? I think that's not the case. I cannot hear you. And
You can see.
So, Srinivasan,
Yes.
shall we type it, or he said he is,
if you have
he can
questions, you
present.
also can write it if you want. You can write it. Anulko, how are you? I see you on the, on the screen.
Fine. And how are you?
But I cannot hear you. That's the
Oh.
problem.
Ankur, he cannot hear you. You can type.
Professor Anantaraman, can you type your question?
Yeah.
Anantaram.
Yes,
Yeah.
sir.
He cannot hear
I
you.
see you on the picture, but I cannot hear you.
Yes,
Yeah,
sir.
he is typing.
Yes.
I still remember you quite well.
Yes, sir.
They are saying excellent talk.
Hmm?
They have mentioned excellent.
No, I have a question. I'm just typing a bit fast. Okay.
Yeah. Please go ahead. Yes.
Great. They are appreciating.
Yeah, thank you. Thank you for your compliments. And thank you, let's say, for your following me during my lecture. Thank you.
They have a question.
The nitrone, the situation of the nitrone is you have two lone pairs at the nitrogen. It is bent, and this nitrogen is supported, let's say, through the two adjacent silicon atoms, which the silicon atoms have 5 electrons, as I counted with you. And therefore, let's say the stabilization to the nitrone is very good, and therefore we were able, let's say, to isolate the first uncharged nitrone. And we compare this, as I mentioned in my talk, to sillones and to carbones with phosphine on both sides. It is also, let's say, contributing electron density towards the carbon atom. So in principle, we can compare, let's say, through the nitrogen has one sigma bond, and therefore it's isoelectronic to carbon and isoelectronic to silicon. So that is therefore we call it nitrone. Sorry that you have to learn if you want to use this compound a new word.
There is a
radical behavior we have not studied. We have just, let's say, happy that Angewandte Chemie accepted this paper. But believe me, let's say, we can do or will do, let's say, a lot of reactions with this starting material. We are working on this. Have you other questions? Then write it. I will try to answer these.
Yeah, professor will share the answers. Kindly send your queries to professor so that he will be in a position to answer your
We
questions.
have just, let's say, sent yesterday, I have sent another, let's say, interesting paper So zur angewandte Chemie. If you are the referees, you will see it soon. It's also, let's say, between boron and the silicon done by Mode. So in this field, there are many, let's say, new discoveries. Thank you. I'm awaiting your mail very soon. And thank you. I hope to come, let's say, next year personally to India. The Deutsche Forschungsgemeinschaft granted me with a travel grant for India. But we have also, let's say, presently a lot of problem with Corona, as you know from the Omicron grant is a problem, let's say, starting in Germany. Of course, let's say I will visit Kanpur, IIT. That's a famous place, and I have been there, let's say, maybe 10 years ago, the last time. But it's a wonderful campus, and during when I was there, Chandrasekhar was still there, but now he's in Hyderabad, and Anulku, I think, was also in Kanpur, and so on and so on. Yeah, Hyderabad. Yeah, I'm coming to Hyderabad because the Deutsche Forschungsgemeinschaft recommended, let's say, to start my lecture in Hyderabad. So you can be sure that I'm also coming to Hyderabad. Probably this is the first place I have to follow. Let's say I get the money from Deutsche Forschungsgemeinschaft, and therefore I have to follow the advices. Yeah, thanks, Varapalli. You are the organizer or co-organizer, let's say, and you introduce this, and thank you so much. When I come, that is a question you ask the virus. If the virus stops this, then I will
stop
come.
it now.
I have
We have to move on
already
to the
3
next
injections,
session.
and maybe I will take in a few months the 4th injection. So when you are becoming older, you see you are not anymore so resistant against the virus, and when you are younger, then it is easier. So therefore, they have postponed my visit to India for the next years. Yeah, thank you. I'm very proud, let's say, of all my students, my colleagues, my postdocs from India. So I have a very good relation with India. Thank you again very much for your very kindness.
Now they are moving to next lecture.
Okay, so bye-bye. Here?
Yes.
Yes.
Yeah, you can cancel it. You can remove your slides also. Otherwise, you can give me. I will do it.
Okay. Yeah, we'll move on to the next lecture. The next speaker is Professor Shigeyoshi Inoue. Professor Inoue, can you kindly share your screen? Yes. Yeah. Professor Inoue gozaimasu. Yeah. Professor Inoue did his doctoral research work at the University of Tsukuba with Professor A. Sekiguchi. He was the Humboldt postdoctoral fellow in the Technical University of Berlin with Professor Matthias Dries in 2008. And he was also a JSPS postdoctoral fellow from the same institute. Currently, he is a professor of Silicon University, Technical University of Munich. He received several awards, to name a few. Carl Duisberg Memorial Prize from German Chemical Society in 2017. NISTEP Award from Ministry of Education, Culture, Sports, Science and Technology, Japan in 2018. And he also received a EDC Consolidator grant in 2020. His area of research interest is main group chemistry, silicon chemistry, organometallic chemistry, and catalysis. With this brief introduction, may I now invite Professor Inoue to deliver a talk. The title of his talk is Aluminum Complexes with N heterocyclic carbons and N heterocyclic imines in bond activations and catalysis. Professor Inoue, please.
Thank you very much for your kind of introduction. And also, I'd like to thank the organizer for having me invited. Yeah, I changed the title slightly, sorry. Yeah, but today I'm going to talk about some aluminum chemistry, particularly low oxidation state or low valent aluminum compounds. And also, I'd like to show you some application of these aluminum compounds in bond activation and catalysis. Yes, like other previous speakers, our research group have been also interested in main group compounds or main group chemistry, because as you know, main group elements are relatively earth abundant, cheap, and environmentally friendly. If you compare it to the transition metal, of course, depends on which transition metal. But you can see the aluminum, for instance, is the third most abundant element in the Earth's crust. As I mentioned, we are particularly interested in low valent, low oxidation state main group compounds, because these compounds, for instance, compounds with multiple bond, like a double bond, triple bond, or compounds with open coordination site, like metallylene species, having amphiphilic or biphilic nature, have available HOMO and LUMO, and also have great potential in bond activation and catalysis. Can also be used for the new material or clusters containing main elements. As also described by Phil Power in 2010, this very famous paper, these main group complexes or compounds can also be mimic of transition metal, like bond activation of various small molecule, as you can see here, activation of dihydrogen or other small molecules, and they can even also act as a catalyst for various various transformation. Therefore, these main group complex can be a good candidate for the alternative of widely used transition metal based chemical transformations. In my presentation today, I'm going to talk about our attempts to the low oxidation state aluminum compounds, for instance, aluminium-1 species, right? We call it like aluminylene or aluminylene, and its dimer, right? compounds with aluminum double bond, so-called dialumine. And I'd like to show you some of our result in their application in bond activation, small molecule activation, and a homogeneous catalysis, and material science. While material science, this part is still it's in infancy in our research group, but I'd like to show you some example of model reaction, bottom-up synthesis of main group containing cluster, small cluster compounds starting from aluminum containing double bond system. So, of course, in general, main group chemistry or organometallic chemistry, the choice of ligand is, of course, very important. Here you can see the list of ligands that or what we always used, right? We are addicted to the solid ligand, solid group. We love solid groups. You can use very bulky solid group to stabilize reactive main group center, and also this sigma electron donating effect is also useful for the stabilization. And you may also know alpha effect, beta effect of solid groups. And for comparison, we also use the aryl groups, like deep or tough angle ligand system. As a support ligand, we also utilize an heterocyclic Calvins to stabilize highly Lewis acidic or electrophilic main group metal center, like aluminum metal center. And the derived ligand system, right, so-called N-heterocyclic imine or imidazoline 2 iminosyl type ligand, we also use it. This iminosyl type ligand, due to their exocyclic nitrogen, you can describe several mesomeric structures, and you can see highly Lewis basic nature, right? And if you can also use it as an anionic ligand to stabilize Lewis acidic electrophilic main group metal center for their donation, electron donation to intercept or stabilize this species. Yes, as you know, well, aluminum is most abundant metal or solid most abundant elements in gas rust, and yes, oxidation state 3 is a very stable form and well known in widely used industrial catalysis like Ziegler-Natta reaction, Friedel-Crafts reaction. But on the other hand, how about the aluminum 1? It's highly reactive due to the singlet gland state, right? Amphiphilic or biphilic, and its chemistry is still relatively undeveloped. How about its dimer, right? And due to the very well-known like CZMT model, don't accept the type of interaction. You can see the trans-band geometry. Therefore, aluminum double bond is very weak. It's quite difficult to intercept or isolate. Therefore, the compounds with aluminum multiple bond is still very rare. Right? The problem is inherent Lewis acidity of aluminum, as you might know. Like often, you can also see that the disproportionation reaction, right? And also very weak aluminum bonding energy, and a lack of suitable synthetic methodology. But thanks to the development of main group chemistry, aluminum chemistry, you can see now many or number of beautiful compounds with low oxidation state aluminum. If you have a look at this slide, for instance, a neutral compound, like Schunukel example, or Habat just now presented very beautiful talk, right? This aluminylene or aluminum 1 species, and Holga and also Phil also described very nice example, right? Stabilized by 2 Calvins or barely bound ligand. Also, anionic aluminum species is nowadays kind of like a fashion or a very hot topic in the main group chemistry, kicked off by the Simon and Jose in 2018, and then followed by the Martin Cole, Mike Hill, and Makoto Yamashita and Ray Kinger. But how about like a dinuclear, diatomic system? This could be a kind of like a Bernoulli chemistry, as you might know. Like we need, even for a single bond, aluminum single bond, we need a sterically bulky ligand to stabilize such a reactive aluminum-aluminum bond. But the double bond without additional Lewis space stabilization is so far still elusive, but this reactive double bond does react even with solvent like toluene or benzene, reported by Phil and Norihiro Tokito. And very recently, my colleague group reported very nice example, right? Phosphine stabilized monomer dimer system. Our approach to intercept or to isolate these species is to combine this N-heterocyclic carbene as additional Lewis space to protect the aluminum-aluminum bond, also with acidic aluminum center. And yes, our favorite sided group, which can probably also reduce the NP promotion energy to facilitate strong aluminum-aluminum bond formation. By using these two ligand system, we started this chemistry, the percentage, right? Percentage back synthesize this sided group, substituted aluminum dihalide with NHC, di-tertiary methyl sided group, reduced by potassium graphite, and we were able to isolate our desired or target compounds with aluminum-aluminum double bond, decorated by 2 NHC. And you can see in the HOMO and LUMO corresponded the pi and pi star orbitals, and the aluminum-aluminum bond length is 2.39. It's shorter than reported aluminum-aluminum single bond for the molecular complexes, and Lebesgue bond order or calculated bond order is also large enough. UVB shows absorption maximum at 573 nanometer, which also strongly suggest or support the double bonding nature of aluminum-aluminum central bond. In this reaction, the reducing reagent is very important. When we use sodium naphthenide instead of potassium graphite, we obtain the aluminum naphthalene adduct. We propose this in this reaction, the generated NHC, so to say, stabilized aluminum or aluminylene, that react with naphthalene before it's dimerized. And then we could isolate this aluminum naphthalene adduct. We are now currently working on this reactivity studies of masked aluminum. Yes, double bonding nature of aluminum-aluminum center can also be confirmed or supported by its reactivity. We found that this dialumin or sided substituted dialumin does react with olefin, like ethylene, and also alkyne, terminal alkyne, and found that formation of cycle addition product, concomitant formation of insertion product. If you have a look at the aluminum-aluminum bond lengths of these products, right, 2.65 or 2.63, 2.64. These are longer, much longer than that of precursor, like dialumin, which is also experimental evidence for that of dialumin's double bonding nature. Yes, together with Cass Whitman, we also found very nice CO2 reduction reaction. This dialumin does reduced CO2. We were able to isolate a CO2 adduct or CO2 fixation product, if you like. Interestingly, upon heating or slightly elevated temperature, you can see the isomerization to the CO reached species, as you can see here. And in the presence of excess amount of CO2, we found this ring expansion product, right? 6-member ring of dialuminum skeleton compound. Of course, with concomitant elimination of carbon monoxide in this reaction. But we were motivated by this reaction and then tried to expand catalytic reduction of CO2. Well, pinacoborane in the presence of pinacoborane, catalytic hydroboration, as a, so to say, the proof of concept catalytic application. And in fact, it does catalyze this CO2 reduction or hydroboration. And initially we proposed the simple, well, it's not simple, bit tricky, but simple, straightforward reaction mechanism, right? After the formation of 6-member link and the sigma bond metastase type reaction or reduction, and then formation of aluminum oxide dimer, and then back to the 6-member link. To confirm this hypothesis, we also synthesized aluminum oxide dimer from the reaction of dialuminum with N2O or dioxide, dioxygen, and then treated with CO2. Yes, it converted to the 6-member link, but need a higher temperature or elevated temperature, and also found a different species in the NMR spectrum in the catalytic cycle. Therefore, we propose an alternative pathway together with computational support calculated by Tibor Silvasi, University of Alabama. And we proposed this alternative pathway, the CO2 reduction by a CO2 fixation product, 6-member link, phenylchloroborane, a hydride transfer, and a CO2 attacks from the backside on this ring, and then 8-member link, sorry, formation intermediate, and then 6-member link product. And the overall phase transformation was proposed by the DFT calculation. Yes, we found this nice catalytic reduction, stoichiometric or catalytic reduction of CO2, but we have feeling that the reactivity of sided substituted, this prana stable dialuminum, is still limited, probably due to the high stability of sided substituted dialuminum. Then we try to modify this dialuminum to enhance the reactivity by introducing aryl group instead of sided group, which can be anticipated to have transband structure or twisted structure, transband structure, and could be more reactive than planar stable dialuminum with sided group. And Cas synthesized tip substituted aluminum diiodide, and then reduced by potassium graphite, we were able to isolate the tip substituted dialuminum. And as we expected, this tip substituted derivative shows highly twisted and transband. As you can see here, the transband angle is 20 or 24 degree, and twisting angle is 12 degree. Now you can see her here also, obviously, transband and twisting angle here. In comparison to their sided derivative, completely planar, you can see the slightly elongated their bond lengths and also smaller bond order, and UVV shows also more than 800 nanometer, right? And the homolumo gap is also small. This twist and transband, let's say, the tip substitute dialuminum can be expected to have more reactive nature that can also be reflected by its reactivity. And as we expected, this tip dialuminum does react with even the di-substituted alkyne, right? It doesn't show, or with sided derivative, or dihydrogen at slightly elevated temperature, right? Yes, we could confirm the more reactive nature than sided derivative, and then we also use this tip derivative, tip dialuminum, in a catalytic reaction or catalytic use of this tip dialuminum. And for instance, again, the proof of concept catalytic reaction, hydroboration of CO2, or dehydrocoupling reaction of amine bolane. Yes, we found that even for the catalytic conversion, this tip derivative is more reactive or more active, but less selective. This is probably due to the different reaction mechanism or pathway, and because this tip derivative can access the hydride species, right? Therefore, we are now thinking about a different reaction mechanism. But we are also currently trying to find the other catalytic application by using not only the tip derivative, but also Sader derivative, and also modifying aluminum ligand system. Let me move on the other topic, or our next target compound is aluminum chalcogenides, right? Because we thought that this aluminum chalcogen or chalcogenides species could be an excellent precursor for the bottom-up synthesis of aluminum chalcogen containing cluster or a material system. But to isolate such a reactive monomeric system, you need the Lewis base or Lewis acid stabilization. As you can see here, very beautiful example by Habit. This donor acceptotide stabilized aluminum oxide, or Georgi Nikonov also reported aluminum sulfur system. As we have already nice precursor like a dialuminins or masked aluminum, of course, we tried to make this aluminum chalcogen system starting from dialumin or a masked aluminum reaction with various group 16 legions. However, we were not able to isolate so far this target compounds. Therefore, we changed the strategy, and we came up the idea with the aluminum hydride, right? Because aluminum hydride is of course a great candidate for making or crafting the various main group containing materials. It's very beautiful review, very recently described by the groups of Mike Hill, Simon Aldrich, and Eric Weber. And Habit also described many examples of beautiful compounds like aluminum sulfur systems. And some of these species can also be derived from aluminum hydride. Therefore, we saw that aluminum hydride could be an excellent candidate or starting material for our target compounds. We synthesized this air substituted tip or tophenyl substituted aluminum dihydride with NSC. You can see here NSC and a tophenyl decorated aluminum dihydride. And then tried to study the reactivity towards chalcogenes. It was done by Huifuit. She made a great job in this chemistry. And we could isolate, or we could find the stepwise synthesis of the, let's say, aluminum sulfur, let's say, containing compounds. Right? We found like single or double insertion product treated with 1 or 2 equivalents of elemental sulfur. We can also directly synthesize double insertion product when we treat it with excess amount of sulfur. We could also isolate very rare example of, or first example of NSC stabilized the aluminum containing sulfur 6-member link system. And yeah, we also did some reactivity studies of this single insertion product reacted with CAC, cyclic alkylaminokalvine. We found an insertion product of the sulfur hydrogen bond. And also we tried to generate our desired or target compound starting from the single or double insertion product by treating several base or other lesion to make the aluminum sulfur double bond or terminal aluminum sulfur bond. However, it was not succeeded so far. And also we of course tried to aid a Lewis base, other phosphine, for instance, to get rid of sulfur atoms from the 6-member link. Yes, indeed, it converted to the 5-member link. I mean, 1 sulfur we could kick off. But further, let's say the dysruphy or the sulfur abstraction reaction was not able, we couldn't see this conversion. Therefore, we changed again the ligand system, and then came to this bidentate chelate type ligand system, so-called bis imino type ligand. And we started with this cationic aluminum dihydride because we found that several years ago, in the case of boron or derivative, it was done by Daniel. When we synthesize this boron dihydride, cationic boron dihydride with bis neutral NHC ligand, this compound reacts with sulfur, and then we were able to isolate a cationic boron sulfur double bonding system with concomitant elimination of H2S. Therefore, we saw that yes, we could probably also synthesize aluminum derivative, something like this, starting from this cationic aluminum dihydride. However, well, aluminum is very tricky, difficult, right? Didn't succeed. Then we changed again the ligand system from the neutral or bis imino NHI system to monoanionic NHI system. The idea is to stabilize such an aluminum triclosanide by using this anionic NHI with additional Lewis space. But we found that when we synthesize this aluminum dihydride by using NHI ligand, it shows dimer, right? But we thought that, okay, this aluminum center can be stabilized by or considered as like additional Lewis space stabilization, right? Single and a donor, something like this. Therefore, it's also interesting species, the compounds containing 2 aluminum dihydride units. And also due to the highly loose basic nature of NHI, this can be, of course, reactive catalyst or hydride. In fact, like Herbert Lusky just now presented some nice catalytic application of his system. We could also show this our aluminum hydride and catalytic hydroboration, as well as dehydrocoupling reaction, and also CO2 reduction. And yes, to achieve our target compound synthesis or isolation, we of course did the reactivity towards tractogenes like sulfur. Yeah? We found that it's a single insertion product, right? Position or double insertion right here, but need a slightly or with elevated temperature. And of course, we tried to generate or convert to the aluminum sulfur terminal double bonding system. However, these species are quite stable and not succeeded so far. We also did the selenium reaction that shows the same, let's say, the result. But interestingly, in the case of tellurium, we found very interesting, unique, so-called the cyclic tellurium single bond type small ring. And we found that this is quite interesting, let's say, ring strain. We can probably break the ring by adding additional, so to say, Lewis space. In fact, we could convert or isolate our target compound by adding 5 equivalent of Lewis space NHC. We were able to isolate aluminum telluride with NHI and 2 NHCs. And you can describe some several mesomeric structure containing Twitter ionic form. More interestingly, you can kick off just one of the NHC upon heating. Then we can say that this is kind of like a molecular model of monomer to dimer, heteromer dimerization of bottom-up synthesis of this oligomerization or polymerization process. We also isolate this crystal structure or obtain crystal structure. We found this aluminum tellurium bond length. It's shorter than reported aluminum tellurium single bond, and also this dimer, and calculated or obtained VVAG bond order is also larger than this single bond, and therefore we suggest somewhat multiple bonding nature. And we are currently doing reactivity investigation of this aluminum telluride system, for instance, tellurium transfer reaction to the organic substrate, or also like a Chaktin transfer or scrambling reaction, or tellurium abstraction reaction. Yes,
Professor
let me
Vinay.
sum up this talk, and I have shown you in the first part some aluminum or dialuminum chemistry, and also in the second part aluminum packaging system like aluminum sulfur or aluminum tellurium system, and a synthesis isolation and some bond activation and catalytic applications. With that, I'd like to thank all my coworkers, of course, people who did or involved in this project, like Percentage Cass and aluminum dialuminum, and Daniel and Fui for our aluminum packaging system. I do want to thank internal, external collaborators, and of course, the private and public funding agency. And thank you all for your listening.
Yeah, thank you, Professor, for the nice lecture. Now the seminar is open for discussion. Professor Anandaraman, please go ahead. One or two quick questions because we are running out of time. Professor Anandaraman, please go ahead.
Yeah, Professor Inouye, thank you for the results and congratulations. It's an excellent piece of work. In fact, I enjoyed your talk. Especially coming back to this, the aluminum containing the tellurium compounds, especially you have got this tellurium bond with a bicyclic model. So what is exactly is happening in that case? Because in all the other cases, like you are expecting like ASH and other thing, in the case of an tellurium alone, you have a tellurium bond.
Mm-hmm.
What exactly is the reaction it is going on to form this?
Probably the initial step should be somehow the same with other like a selenium or sulfur. We have already seen the insertion product, right? Insertion, single insertion or double insertion. But of course, the exact reaction mechanism is so unclear, but we are guessing that this due to the, let's say, the highly reactive nature, and also, of course, tellurium is also known like oxidative coupling, right? Therefore, this hydrogen elimination and then tellurium bond formation. But we haven't, let's say, calculated, but we are just, let's say, assuming such a process.
Okay, fine. Thank you very much.
Professor Momita Majumdar, can you kindly go ahead?
Yeah, thank you. Hi, Shige. Very nice presentation. One question. So with this aluminum bonds that you're synthesizing, have you ever tried using the organosilicon reagents as the reducing agent? Does it work?
You mean from the dihalide to the...
Yeah, from the dihalides?
I think you mean the Mashima type?
Mashima reagents, yeah, exactly.
Yeah, I think we have tried, but the aluminum dihydride or dihalide, sorry, I think we didn't see the formation of the aluminum, but the sided group, I think we should check again. But since we obtained this double bond with standard reducing region, but we didn't study further. But yeah, it's of course a good option to use as a reductive dehydrogenation. Therefore,
right,
yeah.
Right.
Thank you. Yeah.
Thank you.
Yeah, we will move on to the next lecture. In the meantime, kindly join along with me in thanking Professor Inouye for the nice lecture on low oxidation state aluminum compounds and also N-heterocyclic carbene on aluminum hydrides, aluminum dihydrides, and NHI on aluminum dihydrides. Thank you, Professor. We will move on to the next lecture. The last speaker of this session is Professor G. Anandaraman from Indian Institute of Technology, Kanpur. Professor Anandaraman did his doctoral work with Professor Royeski at University of Göttingen, Germany. He joined as a lecturer at IIT Kanpur in 2004. Currently, he is an associate professor at IIT Kanpur. He was a member of Board of Studies of Madan Mohan Malaviya University of Technology, Gorakhpur from 2017 to 2020. His research area of interest is main group chemistry and organometallic chemistry and catalysis. With this brief introduction, may I now invite Professor Ananda Raman to deliver a talk on multifunctional MOFs for docking, sensing, and catalysis. Professor Ananda Raman, please.
Yeah, thank you, Dr. Srinivasan, for your kind words of introduction. And I must thank the organizer for giving me this opportunity to show some of our results. Okay, so in fact, we were working earlier on this metal organic frameworks from last 10 years. And, we have picked up from there, and then, we have moved on to the very recent results. These are some of the results which we have obtained in the last 2 to 3 years. Before that, I must thank all the group co-workers who are involved in this work, and especially the ones in the orange color, like started with Shriram Balaji, and then Dr. Namita Singh, Dr. Sarita Tripathi, and then major work has been today. What I'm going to show is the work of Sharad Kumar Sachan, and the other 2 students are still continuing this work. Okay, so these are some of my group members. So mainly I'll be just focusing on one of the topic out of the interest in our group. So that is the coordination polymers or metal organic framework. But the inspiration came from many such, over the period of time, started with the metal hydroxides. That's like a molecular precursors for the generation of some of the MOFs. Today, what I'm going to show in, conjunction with some of this, the functionalized imidazolium compounds and so on. Although this particular part of the work, I'm not going to dwell it in detail today, or I'm not going to present it. So therefore, some of the things, already published in literature, some are going to come up. You can always look at it. Okay. So what are these metal organic frameworks? The metal organic frameworks are nothing but it's formed by the connectivity between the metal and the ligand to form like a networking kind of a structure, to form like 1-dimensional, 2-dimensional, or 3-dimensional structure. Further, if you apply the knowledge of a crystal engineering, then by invoking the concepts of a supramolecular chemistry also, then one can actually design and create like a functional groups, and also the interaction leading to certain very interesting applications, which is currently of study. One of them is like a water adsorption and so on. Okay. So when the chemistry has begun with respect to the framework structures, in fact, it started off by the yogis and co-workers, and especially in the cubical formation of a metal organic framework. The interesting design in this case is the formation of a YAM containing the oxygen, which is actually further connected to 3 other metals, which is something like a tetrahedrine, like a connectivity, which is formed like a node. And then with respect to that, the spaces are connected by this benzene dicarboxylic acid. As and when this particular, the publication came, there are so much of interest because it generates a huge amount of void, which is shown over here in the yellow color sphere. And as a result of it, a lot of gas adsorption studies and the certain applications like housing some of the nanoparticles of metal systems have been incorporated. And then people said this is one of the fantastic systems for the futuristic model of generating materials through which one can actually utilize various applications for gas adsorption. Not only that, the extension of this or the parallel ones which appeared in the literature was the copper-based MOF. And if you see it compared to the earlier, the node, here the node is somewhat different. It is based on the dinuclear structure, and this dinuclear structure indeed formed with respect to this copper chemistry, and then simultaneously the ligand which is bound to it are labile. So people have used this particular center for absorption or catalysis and so on, as compared to the ligand centers which has been there. That is nothing but the benzene tricarboxylic acid. But more interest came into this field because of the preparation of this UiO66 as well as the MIL 101. In both the cases, if we actually see it, this particular central node, it actually plays a very, very important role in generating a larger porous structures. Not only that, even some of these, the oxygen containing or the hydroxide containing systems, they have been utilized during the adsorption, or some of the cases it has been utilized in the catalysis part. But the interest towards the ligand at that time was somewhat less as compared to what it is. But yet, if you see in all the 4 cases, the metal node played an important role in generating a larger structure, which is actually playing an important role. Not only that, in fact, the ligand in these cases also play, in fact, a very, very important role too. So that is where, in fact, the Yagi and co-workers, they have actually evaluated by the method of like called isoreticular method, where the changing in the spacer group from a simple benzene dicarboxylic acid to a biphenyl containing the dicarboxylic acid, or the other functionalized models of these things with respect to this bromo or amino or the other ethereal containing systems, it has in fact increased not only the void size, but also some of the functional properties have been evaluated using this by increasing the carbon dioxide absorption and so on. So by typical system is like when you increase the size of the linker, the void size increases. As a result of it, it was anticipated that the more the gas and the can absorb, and as a result of it, one can get a better applications. So that is what here it has been shown. One such example with respect to the IR-MOF6, where they have observed that the quantum of the methane absorption was double the time as compared to a simple zeolite 5-angstrom model itself. So having said to this, then the functional group importance were also equally been highlighted, and people started emphasizing on how one can vary some of these things. So here is the particular chemistry. It came up by invoking some of the ligand design based the supported models, where if you increase the linker size, then one can actually create a larger size of the metal organic framework, which has a functional group. If it is there, one can even house some of this metal catalyst itself. So therefore, this becomes like one of the important part of it, where one can even invoke some of this catalyst inside the channel, and after the catalysis is over, one can actually make them as a heterogeneous medium for the catalysis itself. Okay. We have started off this chemistry by taking some of this simple ligand design, such as like pyridine containing imidazole, to understand the fundamental nature of the rigid systems, wherein some of these cases where the connectivity between the nitrogen and the pyridine, the carbon, which plays something like like semi-rigid kind of a model, which actually leads to the formation of very interesting architecture, invoking like one-dimensional to the two-dimensional grids and so on. But more importantly, the orientation of this nitrate ion also were very interesting, and they actually vary from a simple like planar to other sort of some deviation from the planarity it was there. By controlling these factors, we could even generate some of the chiral polymers too. So the last set of speakers on these things, when they have invoked on this thing, like the chemistry of low valent chemistry, I'm going to switch over into the next couple of slides about how does the high valent, the group 13 element, can play a very critical role in the designing or in bringing this some of this nitrate ion connectivities, and how it is important in terms of its application, what I'm going to show you in a couple of slides later. But before that, when we have learned this lesson of how to create this two-dimensionality, there is further things it got triggered by varying the central atom, the ring size. That means from a 5-membered to the 6-membered or vice versa, they started generating a particular fragments wherein a corrugated structures to herringbone plated structures or even other 3-dimensional structures were there. So inspired by those things, then we try to see how does this central atom, which is actually non-coordinating to any one of these polymers, they behave, but unfortunately we were not successful. At this juncture, we have actually utilized and played around some of these ligand designs. Instead of having a similar to whatever the earlier ones it was there, we thought, let us use the imidazole as a central one and simultaneously go and substitute different ring sizes and their position or functionalize them, and then create them like a imidazolium unit, which can actually act as one of the position for coordination in the metal organic framework itself, which I will detail to you in the forthcoming slides. But the most important thing is how to generate the nodes, because the nodes are very challenging in the metal organic framework. It is something like if you try to see the papers that are published in the literature, you take a metal precursor like metal chlorides or nitrates or any other metal salts, and then add one ligand, then you get the framework structure or a coordination polymer. But however, such reactions have the limitations in the product formation as well as their diversity in the structures. So therefore, many of the times their functionality versus the applications were so restrained, therefore the application could not lead to several of them. So we have utilized our expertise, a decade ago also, we have published this paper about the metal hydroxy formation. How do I control this metal hydroxy formation? By invoking the N-heterocyclic carbene, and then simultaneous a careful hydrolysis, how one can selectively get the metal hydroxy system, whether it is like a bis or a monohydroxy system, then simultaneously how one can invoke the corresponding product formation and so on. This particular one has also become handy to us while designing, because if you see the entire sequence of a reaction that is occurring in generating the metal node, even in a metal organic framework, it also follows something like a sol-gel mechanism. So in that sense, if you try to see, the first step of a reaction is very, very critical if you want to generate the metal hydroxy. Then simultaneously, if you allow the system to proceed, then it will undergo the condensation reaction. So many of these structures, if you see it, whether it is having one oxo with several metals or like metal oxo hydroxy system, everything is being controlled by these first three steps in it itself. The fourth step is somewhat like complementary to the second one, whether it is ovulation or this, then both the cases you can have it as an intermediate, and then simultaneously we can get the final product. So having said to this, then how did we went on to this, generating this particular metal organic framework? First, the importance of this is we need to know how to do the cross-coupling reaction. So this cross-coupling reaction, some of the students, they worked extensively to generate some of the Suzuki-Mura cross-coupling reactions, such as this one such slide shown over here, where we have used functionalized imidazolidine to generate like CC bond coupling and so on. So with the variety of substrates we have checked, and then it gave us a excellent yield to somewhat very good yield also. At that time, another student, he was working on the dibromo or a tribromo based the catalysis, especially on the Suzuki cross coupling. We started off thinking, why can't we embed some of this functional group with the carboxylic acid system? So some of these reactions, what he has carried out, it became also one handy to us to finally stabilize the ligand model itself. So the person who is standing in this particular slide, Sharad Kumar Sachan, who extensively worked in this particular area, most of the results I'm going to present is going to be from now onwards is carried out by him only. So what are the things he has done? So if you want to have a multifunctionality, there are two parts it is important. One, as I said, the metal-based the functionality, the oxo or hydroxo. The second importance is the functional group containing system in the ligand model itself. So in the ligand model, we have chosen this imidazole, where one of the nitrogen, we deliberately kept it as vacant so that this can behave as a base within the framework structure, and simultaneously, then we can even utilize them for the gas adsorption to various other applications, some of which I'll be showing you. But the interesting part of this ligand, if you see it, this is not like a truly like the C3 containing system. It's like a pseudo C3, or even there is no C3 in it, I can say. So because of this presence of the methyl group, this particular compound does not generate the traditional, the metal organic framework structure that used to generate by Yogi or some other co-workers using the Tris type of a ligand and so on. So in the benzene tricarboxylic acid, it typically forms like a hexagonal channel, whereas the moment when you vary this with respect to the 5-membered ring and containing 3 such phenyl carboxylic acid, instead of an expected, the hexagonal pattern, we get something like a cubo-octahedron containing pattern with respect to the indium nitrate reaction. So what does it actually it does in this reaction? In fact, when we got this result, we were amazed to see what sort of a product it is formed, because there are more intriguing the aspect about the structure it is there, and some of them I'm going to detail it in the next slide. So first is, if you look at the 3-dimensional picture of it, it looks like the starburst containing model. So as though some of these things, they're containing the star, inside that there is something, the atoms which are present, And if you carefully see the color coding, there are some nitrogen and also the oxygens are there. And if you take up one such unit and then, look into the more detail, then what we see it is the ligand is present and which is actually connected to 3 such indium trinuclear cluster, where there's 3 indium trinuclear cluster, each and every one of them having like the indium hydroxy indium kind of an connectivity, where the central atom is only connected by the carboxylate unit. Not only that, the N terminal of these 2 centers of the system has got a nitrate ion which is bound to it and which is further connected to form like an interesting crown type of a structure, wherein within the hexagon, suppose if you plot it, this is something like a wave kind of a structure, or the overall, if you see it in the other view, it looks like a crown kind of a structure itself. In fact, this particular one, it plays an important role because barring that central atom, the other 2 centers not only carry the nitrate ion, it also has an, one water molecule, which is also coordinated. Before I dwell on to this, the water importance in this particular one, let me just take you to little more interesting aspect about this particular structure. Having said this, the formation of this, the hexagon type of a pattern, that suppose if you connect it to this particular unit, which is actually is there, then if you compare the second and the third layer with respect to that, or above and below, they are looking like another hexagon layer, half of which falls on the middle of this particular layer itself. So as a result of it, the orientation of these things in a particular in this particular system, it gives you like a cubo-octahedron kind of a pattern. And when you look at the cubo-octahedron, when you view through this the C-axis, that is the middle of this triangle, then you do see there is a nitrate ion present. It is there. That is what actually it is looking like, a wheel type of a thing. The question comes immediately, why does it show like a wheel? If like a regular patterns are there, normally we can see like 1 nitrogen and then 3 oxygen should be there, and then that will be uniformly, it will be there. As we all know, nitrate is like known for its the planar containing systems, so therefore we should not expect any deviation from that. But more the things when we probe and when we expand it, we do see the cubo-octahedron structure is getting extended in this particular morph, and only suppose if we take the nitrate ion alone, then we see all the nitrate ion layers are not equal. So if you see it here, I have presented this, the layer 1 to layer 7. So the layer 1 and layer 7 are overlapping each other, whereas layer 2, layer 3, and all the other layers doesn't overlap each other. If we further closely look at this particular one, then what we realize is the orientation of this nitrate ion is no longer like a planar in nature, rather than that they are like a pyramidal type of a system. So if you actually see it between the 2 such, the nitrate ion present in this particular here, they are not being there in the same orientation. And also, if you see it, their way of, the connectivities and the nitrogen orientation, they are not the same. So this is the one, when we actually expand it to see, you can now see it in this picture, it is clear, where the one of the nitrate ion, which forms something like a pyramidal nitrate type, and another nitrate ion, it forms something like an inverted pyramidal type of a system. And put together in a hexagon kind of a model, if you try to take it, the alternate, the pyramidal, containing system of these nitrate ions are present. And then when you stack it, these are the ones that is actually responsible for showing such the wheel type of a structure. So this particular wheeling is playing an important role in the porosity and the direction by which any such gas or the other substrate molecule can come and go, because one phase of the the unit, that is the entry pore, is fixed, whereas the the sidewise, whatever the space that is available through which only the molecule can go. So this is in fact plays a very, very important role. And to prove that this particular morph is highly stable in the system, so we have done some of these thermal studies, so such as the TGA, and then variable temperature containing PXRD, and also we have also soaked the morph in water. In all the cases, what we have seen is this particular morph is very highly stable. So in the variable temperature PXRD, it shows the metal organic framework is highly stable up to 240 degrees centigrade. Whereas if you try to see it, in fact, this particular one like simulated as synthesized. So when we do the synthesized to the activated, if you see it, we do heat and then we do evacuate in order to create the channel. So even under that condition also, the activated, the MOF is very highly stable. So when we have looked at the porosity, what we have got is this particular MOF is a highly porous, and it has BET surface area of is like 523 meter square per gram, and then it shows the porosity is sufficient enough to house certain molecules. So we have recorded certain gas absorption studies. One is the carbon dioxide, second is acetylene, and also third is the hydrogen. In all the three cases, what we noticed is the absorption capacity was better, not the excellent result, the way Yogi or any other people, they have it, but the absorption at the room temperature, which of the carbon dioxide, which prompted us to look for it, how does this MOF can be utilized for the other applications. I'll just show you in a couple of minutes. But if you look at the literature about the metal organic framework, especially on the indium-based cubo-octahedron MOF, what we have realized is some of this VTPXRD of the known example of this, it shows the decomposition of this particular system, whereas in our case, we could see the stability of this system is very, very high. That means we can even do this, the metal organic framework, and utilize it for high temperature containing catalysis and so on. But what we have chosen is we want to show some of the sustainable model, how one can use some of these compounds as for the catalysis. And this is one such reaction I have shown over here. That is like a simple reaction from an epoxide to cyclic carbonate. Remember, we have discussed, or in the literature several times also it's been reported, where CO2 is one of the toxic and the greenhouse gas, where people want to either store it or convert it into a useful product. In that sense, if you see it, the cyclic carbonate systems are one of the very attractive products because it has been used in variety of application, including in our mobile, like the display in the mobiles. If you see the the sheet that is being placed on the mobile is based on the polycarbonate system. So in that sense, the particular the method of conversion, if you can reduce it, if you can provide them in the cheap and low cost, the method of synthesis, then the polycarbonate systems can be utilized for variety of application, including even in the storage containers and so on, which has been used in the Japan itself. Okay, so having thought about it, then we try to activate this MOF, and we have chosen the indium containing MOF, where one of the position of water molecule is present, which we have heated to say 100 degrees to eliminate this water, or by even the activation has been done by changing several times with the different solvents, including the ethanol and so on. Then we try to replace this water by other weakly coordinating solvent molecule. Then we have evacuated to generate the activated MOF. So once we have generated the activated MOF, this particular position of the water is there, that is has been lost, and then it is vacant. And simultaneously, the epoxide can be utilized for the coordination, and hence the net reaction can be performed. So having thought about this, we have performed, and then we have done with respect to this the epichlorohydrin. In fact, to our delight, we have got a very good yield, and with respect to the good turnover number and the frequency, and then even this particular conversion can be done even in the room temperature itself. So having seen this, the very good catalytic activity, then we started looking at the substrate scope. We have varied from the alkyl containing chain to the cyclic containing systems, or the strain systems, or with respect to the phenyl containing groups and so on. We have noticed in all the cases, the room temperature reactions that is going on, and then the corresponding cyclic carbonate is formed in a very good yield that is excellent to the very good yield we could obtain. So therefore, this particular one has prompted us to probe the recyclability of this particular model, because one of the challenges, sometime, during this reaction, some of the MOFs gets collapsed or it is getting trapped with the first cycle of the substrates what is being used. So therefore recyclability became unchallenging. So we have checked in our cases, this particular catalyst can be recycled for more than 5 times. So as I said, the first particular step involves the creation of a vacant coordination site wherein the epoch site comes and binds, and then simultaneously, the tetrabutyl ammonium bromide, it helps to open up the ring of an epoch site, and then simultaneously the carbon dioxide comes, and then it forms like a cyclic carbonate, and then this particular process keeps on moving in the catalysis. Okay. After we have succeeded with respect to this, then we went on to look for what are the other catalysis can be done. When you have a Lewis acid as well as a Lewis base, then plenty of other applications are possible. One such application what we have chosen is like the Strecker synthesis. In the case of a Strecker synthesis, what we have used is it's a multi-component synthesis wherein the keto groups can be utilized for the coordination to the indium center, and simultaneously the amine groups can be used for the formation of an alpha aminonitrile compounds. What is the significance of this reaction? These are something like the artificial peptide precursors which can be utilized for the applications to generate the synthetic peptides, and as a result of it, this can be later on utilized as one of the the drugs itself for the genetic modulation and so on. So having said this, then we started looking at it, how effective this particular MOF would be in order to generate some of this alpha aminonitrile. So in this case, we could see the variety of substrates from a simple, the estophenone to the corresponding cyclic ketones and so on, or the sterically hindered amides. In all the cases, we were successful in getting the particular alpha aminonitriles. So needless to say, as we have checked in the previous case, here also we have seen the recyclability of the system is excellent and so on. And then as a result of it, then we started looking at the the stability of this compound, and the stability was excellent after 5 cycles. And then when we looked at the literature to our delight, in fact, our catalyst is one of the lowest, the catalyst loading. We could use it to prepare and then to get the best result of alpha aminonitrile, which is known so far in the literature itself. Okay, so coming back to this, the presence of a Lewis base, which is there on the MOF, which we have utilized for some of the acidic containing system, especially on the explosive systems, which is one of the nowadays, if you see it, one of the important one wherein we have to sense some of this toxic containing models. So in that sense, the explosive picric acids have been used for the testing. And then, in fact, to our delight, in fact, this particular MOF senses very efficiently, and then their sensitivity was found to be as low as the 0.5 ppm, so on. So one of the reason why our MOF is also luminescent is because of the presence of the imidazole containing the phenyl, which is something like has a property upon the coordination with respect to the picric acid. The nitrogen abstract the proton. As a result of it, it quenches. So we do see the quenching effect of this particular one upon addition of this picric acid at different concentration. So having said this, in fact, this is also, we have found is one of the lowest quantity of the LOD, and also the very high sensitivity with respect to that is getting reported. So this is one such cases. Upon set to this, how one can actually utilize this particular MOF. In fact, if you see it, one of the literature report, it says that each and every one of the MOF has its own uniqueness. So when you change the metal from the indium to some other metal, then we are likely to get a new application. But the maintenance of this, maintaining this, the structurality is somewhat critical. So my student has excellently modulated this particular experimental condition by taking a cadmium as an precursor with respect to this to get the isostructural MOF, but with an exceptional properties, whatever we have. So what does it has got? So the synthesis is shown over here in the beginning, where the imidazolium containing phenyl carboxylic acid is used to prepare some of this sorbus containing system. And some of this sorbus containing system, if you narrow it down, its basic core is made up of the cubo-octahedron. But if you look at each cubo-octahedron node, it has got a new and the rarest SBU which is there. So the new and rarest SBU has to play with some of this, the red dots, whatever is there, like the way the previous cases. We do see this particular one, but with an interesting one where some of these, the dots, it represents the water molecules. So does it have a 6 water molecule? No, it does not has a 6 water molecule. It has got like a 3 water molecules. What are these 3 cyclic water molecules? It is there. If you closely probe on them, these 3 water molecules are connected together, but not by hydrogen bonding, with a short electrostatic contact. In fact, when we measured these distances, it was alarming because the distances were close to 2.3 angstrom. In fact, if you see in the literatures as well as the other places, the acceptable, the OO distances were like 2.8 and so 2.8 to 2.56, or in the case of an chiral trimer reported by Sekele in 1992, this is something like 2.97 angstrom. But what do we have? We have something like a trapped water trimer in between the channel as shown over here by means of the oxygen atoms which are protruding out in the channel and which actually traps this particular trimer to form something like a non-hydrogen bonded contact. So this non-hydrogen bonded contact is not something unusual because this has been first evaluated by Professor Satyamurthy group here, wherein in an hydrophobic systems such as if you take it like C60 and so on, if you place these 3 water molecules, they form something like a very short oxygen-oxygen contact where this is closer to that of 2.27 angstrom itself. So this particular one, when we, I'm going to speed up and then I'm going to complete also. Yeah, thank you. So having said this, then the question comes, how does this water trimer forms and what are this particular one it has? So this particular one, if you compare it, this is forming like an hexameric unit containing model, but it forms like in an octahedron. If you try to take it like through the C3 phase, it is forming like a 3 such oxygen atom of the alternate ones, it are oriented, and 3 oxygen atoms of this O6 is oriented in the bottom to form something like an octahedral space cavity. And within that space cavity, this water trimer is actually encapsulated. So this encapsulation has led to the very good applications, and as usual, like the way what I have showed, the gas absorption studies and so on, it is excellent. And then the nitroaromatic compound, it is sensing still because we have the vacant nitrogen. But if you see it, some of this metal ion sensing is also an exceptional one. In fact, this is one of the MOF where it can show all the anion, cation, as well as the molecule can be sensed. And if you see it, this quantities are almost in the ppm to the ppb range. But what is more interesting is in the last 2 weeks of time, what we have done with respect to this, if the water trimer is encapsulated on the faces of a cubo-octahedron, then this particular phase can be utilized to sorb or to even use as a, the carrier for the remaining water molecules in the channel itself. So that is what in the Yogi's, one of the paper he has listed out here. Typically in the MOF, we have 3 such domains. One is like a sorting domains. That's like the sieving model. Second is the coverage, where it gives us the overall idea how much the molecules can be sorbed within the channel. And third is if you are very specific, if you can introduce some of the struts containing the functional group, they can trap some of this metal ion. But to our delight, what we have done, we have just taken some of this cadmium MOF and then soaked in water. What we have observed is the water is getting trapped all over the metal organic framework. And then in fact, the number of water molecules in the channel, which we after resolving using the X-ray crystallography was found to be like more than 100 water molecule itself. So in fact, this is one of the excellent model where whether we can use it for water harvesting, this is going to be like another set of studies, which we have to do it in future. But what I have showed is from the previous case, the paddle wheel structure to the the metal containing the other the octahedral structure node, when you go for like simple dinuclear containing the stardust unit, in fact, if you have a optimized spaces out there, in fact, this water harvesting can be done even more better. Why this particular result is an important one? If you compare it, some of these water molecules in the phases, and if you correlate with respect to the results, what I have got it with respect to picric acid or anything, if you see it, it is much higher than the indium morph. That means the water primer is acting like an entry port to help and assist some of the molecules to go inside, and also the nitrogen atoms which are present in the morph, which assist in the metal ions to encapsulate or capture, and then thereby one could see the some of the properties of docking, which is getting replicated in our morph itself. So if I remove some of this, the framework, this is how the water molecules it looks like. And some of these water molecules, if you see it and then look at it, it also forms something like a digital type of the points that is being placed over here. In fact, we needed to probe, and then we needed to see, can these morphs can be used as a hydrogels for the carrier of drugs and so on. These are some of the things in future I'll be showing. Since I have a very short time, I'll just take up only 2 slides to show you the final results. So we have done in few years ago with Professor VC, some studies where when we have utilized one of the imidazolium salts with respect to the tin, we have got a very interesting hexameric, the tin compound, where the iodide ions are trapped, where some of these, the methanol molecules, they are getting trapped in the channel to form like a short contact between iodide ions. But if you try to modulate further to make it like an imidazolium salt with respect to the one of the spaces, what we have found is not only we could prepare a metal organic framework in the 2D form, but we can also dock some of this palladium catalyst inside. Of course, the future is like, we are going to look at some of these morphs, how they are going to be utilized for the catalytic application. So far, what I have shown, several core structures have been developed, but only few cores containing the metal nodes are only known in the literature, which is found to show an excellent application. So the 4 are listed over here, and this is one of the 5th one. We believe that it could also do the same type of a magic, as we can see. Although I haven't shown you several results, only 3 such applications I have showed. Already we have got more than 5 such applications using this metal organic framework, some of them which we will be showing you later. So to summarize my overall talk, so I have showed you about the metal organic framework of containing the indium and cadmium morph, and in that the nitrate ion, which is there in the pyramidal shape, which is a very unusual one as compared to whatever is known. And if you try to take from the indium to the cadmium, those central faces of the triangular units are now trapped by the water trimer rather than any other system itself. So the docking principles have been utilized to dock some of these palladium molecules in that, and some of the some of the catalysis using this organometallic morph is under progress in our group. Okay, so with this, I thank you for your kind attention.
Yeah, thank you, Professor Anandaraman, for the nice lecture. Now the seminar is open for discussion. Only one quick question. As we are running out of time, already we are the next session about to start now. Yeah.
Hi,
Rajesh Das, kindly go ahead.
Yeah,
yes.
Yes, sir. Sir, good work, sir. Sir, I have only 2 small questions. Did you calculate that QST with the CO2, that indium morph?
No, we haven't gone for the QST. Okay. We haven't done that. We haven't done.
You told that in room temperature it absorbs CO2 in good amount of CO2 it absorbs. That's why I'm asking this question.
Yeah, we haven't done that. Actually, see, initially, we haven't planned to, do the room temperature. This has come up much later stages. So we have utilized as it is, because the QST and other thing is important when you want to go only about the gas absorption alone.
Okay, sir.
But our aim was more towards the application, so we went on to the other side. Yes.
Okay, sir. That in mechanism you showed that water molecule, that coordinated water molecule can be removed by the application of heat.
Yes.
How you confirm that all water molecule is removed?
Okay. So if you actually see in our TGA itself, it shows that. Okay. So if you heat it or if you exchange it, some of these. One minute. I'll just come back to you. Okay. Yeah, this is the activated MOF what we have. So when you heat it and then, when you activate it, less than the 100 degrees itself, we can do that. Okay. So after that, the MOF is stable from 100 degrees to 300 degrees or 350 degrees to you.
Yes, sir. But there are some wet loss below 100.
Rajesh
Sorry?
Das, kindly touch with the sir. We are running out of time.
Okay, sir.
Yeah.
Okay, sir.
Okay, maybe I can discuss with him in the chat box or anything. Yeah.
Yes.
Okay, sir. Okay.
Yeah, kindly join.
Thank you, sir.
Yeah, kindly join along with me in thanking Professor Anandaraman for the nice lecture. And I also take this opportunity to thank the organizers for giving me the opportunity to chair this session. Thank you. Now I will hand over to Professor Krishna.
Okay, thank you very much, Professor Srinivasan, and also all the speakers of this session. And since we are running out of time, we will start the next session immediately. Now, I request Professor Mamita from IISc IISER Pune to share this session.
Thank you, Professor Krishnan. Good afternoon, everybody, and welcome you all to the continued last session of today. So our first speaker for the session is Professor Todd Mader from the University of Würzburg, Germany. So it's my pleasure to invite you, Professor Mader, to this session. Professor Mader has made gargantuan contributions and achievements in science over many years now. He began his career as a faculty at the University of Waterloo in Canada, followed by Durham University in UK, and then he moved to University of Würzburg in Germany, where he is currently working. He has published more than 400 peer-reviewed journals and has an H-index of 91. He has received several honors and awards, to name a few: Fellow of the European Academy of Sciences, Fellow of the American Association for the Advancement of Science, RSC Awards in Main Group Element Chemistry and in Organometallic Chemistry in UK. Today, he will deliver his plenary lecture on the fantastic organoboron compounds and their applications. Professor Mader, the platform is yours. Thank you.
Thank you very much, Dr. Majumdar, and thanks to Krishnan and all the others for inviting me to give this presentation. I will share a screen now if I can. Can everybody see my screen and hear me?
Yes.
Okay, so I will do my best to stay within my allotted time if I can. And so what I want to tell you one story today. And if I have some time at the end, and we'll see how that goes, I'll tell you a few other things we've been doing recently in this area. So what I want to talk to you about today is 3-coordinate organoboron compounds and their optical properties and applications in cell imaging. So I thank the various organizations here that sponsored the research. And I won't go through the whole list. We have a large team, if you like, in boron materials chemistry. And I will focus today on the work of just a few people, 3 excellent postdocs. Let me see if I can get my laser pointer working. So 3 excellent postdocs. Hello? Can you see it now?
Yes, we can. Please
Okay,
proceed.
so 3 excellent postdocs, Jilei, this was Zhulan Zhang, and Bob Edkins. They're all professors now, Jilei and Xian. Zhulan is a prof in Changchun at Jilin University, and Bob Edkins at Strathclyde University in Glasgow in the UK, and Steffi Griesbeck, who won several awards for her PhD thesis. And these people developed the project I'm going to tell you about. What you can see here quickly is that we collaborate with many people all over the world. in our own university and different parts of our chemistry faculty in Rennes, Bordeaux, in France, in the US, Canada, and I'll show you some of the work we did with the groups in Nagoya in Japan and in Zagreb in Croatia. And we also work closely with several groups in China. Okay, now you saw a little bit about this area this morning from Professor Thiligar, who nicely hosted me for a couple of weeks at the IISc a few years ago. And I just want to give you a bit of a background to the field, which I hope you will find somewhat useful. So we're going to focus on 3-coordinate boron. Boron is just to the left of carbon, so it's got one less electron. And 3-coordinate boron, therefore, has a vacant p orbital perpendicular to the trigonal plane, isoelectronic with a carbocation. It's able to accept electrons and form radical anions. I'll show you a couple of quick examples of that. And more importantly, for most of what we do, it's a strong pi acceptor which can conjugate with adjacent organic pi systems and function that way in dipolar, quadrupolar, and octopolar systems. I'll show you examples. So unlike most normal organic pi electron acceptors like cyano and nitro and carboxy groups, it's an inductive sigma donor, because boron is actually more electropositive than carbon. Now, of course, the empty orbital is readily attacked by nucleophiles, so you know it as a Lewis acid. And that can be important for certain types of sensing, like sensing of selected anions like fluoride and chloride, but I won't address that today either. What I will address is the problem, and the problem is that, of course, water can bind if you make a strong Lewis acid. And that can either do two things. One, if you bind a Lewis base of any kind, water or otherwise, in this to this empty orbital, you no longer have an empty orbital and thus no longer a pi acceptor. On the other hand, you can also undergo hydrolysis of these BC bonds. The R groups are going to be carbons. And so if we want to work in ordinary atmosphere, or especially, as you'll see later, in water, we need to protect the empty orbital on boron. And the way we do that, and you saw some of these mesotyl compounds in Thiligar's talk, is we use sterically demanding aryl groups to basically build a cage around the boron atom. So if you look at this picture, this is trimesotyl borane, 3 of these 2,4,6 trimethylphenyl groups. And the little pink thing in the middle is the boron, which you can barely see because it's completely shielded from external attack by these orthomethyl groups. Now, I don't know if I'll have time, but if I do at the end, I'll tell you a little bit what we're doing with this so-called fluoromez group, which is even more effective. Anyway, if you want to read about the synthesis of triaryl boranes, we've just published a review on the 135-year history of the field. Now, this field actually goes back a ways. We've been involved in it for over 30 years now. So our first papers were around 1990, and there was a group in France, Lequin's group, that was looking at nonlinear optical properties as we were a little over 30 years ago. But in fact, it goes back even before that. And the first papers on these luminescent systems came from Kodak, the camera company and film company, back in the 1970s. And in the 1980s, shortly before we started working on these, the group of Wolfgang Keim in Stuttgart put 2 of these borons at para positions of a phenyl ring, and I'll return to that later because they looked at the redox chemistry of these, that is the electron accepting properties. Now, a little after we got working on these BMES 2 compounds, we call them, Tamao and Yamaguchi, at that time in Nagoya, in Kyoto, and then Yamaguchi has done a lot of work in Nagoya. We collaborate with them strongly. Now, they looked at solvatochromic emission. I'll explain that in a minute. My colleague here in Würzburg, Christoph Lambert, the organic division, also examined that in the 1990s. And more recently, Matthias Wagner, who will talk to you tomorrow, Shige, Yamaguchi, Ingelsson, now in Edinburgh, have built boron-containing polyaromatic hydrocarbons. And many groups, several groups early on, Shiroda's group in Japan, Suning Wang in Canada, and then also in Beijing, and Wei-Yung Wang in Hong Kong began to explore boron applications of these BMES groups in OLEDs. This has really kicked off, and there's lots of work on that. And then we were interested in two-photon absorption, two-photon excited fluorescence, which I'll tell you about today. But in fact, Fang's group at Shandong, in Shandong, in China, Shandong University in Jinan actually moved into this area with some of our compounds and their own a little before us, and then sent over an excellent postdoc who worked with us for several years. So there's a bit of a history here, and I think it's important. And if you want to read about the history, we've published 3 reviews, and indeed one this year on applications in bioimaging and related chemistry and Materials Horizons. It's just out online, not with page numbers yet. So let me go back and focus on one of the compounds I just mentioned from the Keim group as an example. So he published a series of papers in 84 and 89, just before we started. And we played with this system for many years. And in fact, he reduced it and measured the EPR spectra of it. And we went back and reduced it again chemically, with just potassium at 18 crown 6 and THF. And what we were interested in was the crystal structure of the compound. And what you can see as you add an electron to this system is what would be expected. That is to say that the benzene ring goes towards a quinoidal geometry. There's a lengthening of these 2 bonds. There's a lengthening of these 4 bonds, a shortening of these 2 bonds, and the shortening of the BC bonds indicative of the buildup of double bond characters. So that implies, as we and others had calculated back in around 2000, and we published the crystal structure of this with Gile in 2015, that you have complete delocalization of the electron density between the 2 borons and the phenylene ring in the middle. We then, because we have a strong interest in pyrene chemistry, we then went on to make the pyrene analogs, and I'll focus particularly on this one, where we put 2 of these borons at the 2 and 7 positions of pyrene. If you put one on, you can see the ESR spectrum in its simulation, which shows coupling not only to the boron, but to many of the hydrogens on the pyrene. And if you put 2 borons on, actually you don't see the coupling, because the electron is so delocalized across the whole molecule that you lose the fine structure. But you can reduce this not only once, but twice, and put 2 electrons in. Now, why is that interesting, and why do we like pyrenes? Well, the interesting thing is that if you look at the LUMO, so if we're going to put electrons into this system, we look at the LUMO, and if you look at the LUMO of pyrene, it has a nodal plane passing through carbons 2 and 7. So attaching a pi acceptor, which would conjugate with this, and then putting electron density in, you might wonder, how does the electron density, if we put an electron on boron, how does it conjugate with the pyrene if the LUMO has no electron density at the 2 carbons, C2 and C7? Well, the answer is that it's such a strong acceptor that it interacts with LUMO +1, the higher energy orbital, and actually drops it below the pyrene LUMO in energy. And you can see that here in the mono case. The new LUMO of the molecule in the radical anion, or in fact in the mono boron compound, is actually this one. So it takes this orbital and stabilizes it by pi accepting into the empty orbital on boron. And if you put 2 borons on, you get the same thing. And therefore, you can already see that the LUMO has this quinoidal type character. And if we put electron density in here, you're going to see buildup of bond character at these positions and the buildup of the BC bond. So that's a rather interesting thing. And we've published a lot of work on pyrenes with donors and acceptors. And we use our own technology to put groups at 2 and 7 because they're chemically typically inert. We use sterically selective catalytic CH correlation to make these compounds. Now, you can see the geometry change in the crystal structure, both of the monoanion and the dianion. If we compare them to the neutral compound, I won't go through all the bond lengths, but you see the expected quinoidal distortion. And what you can also see as you build up BC double bond character is that these rather twisted systems. So if you look at the boron 3-coordinate plane and the angle it makes with the pyrene, it's about 30 degrees in the neutral compound. And as you build up double bond character, it begins to planarize down to 13 and then down to about 8.5 degrees as you put the second electron in. So that's good evidence for the formation of significant BC double bond character. Now, I want to focus on optical properties more than electronic ones. So what I want to do is tell you a little about charge transfer and how the boron can act as a pi acceptor in these types of systems. So if we take a very simple conjugated system, we put one of these borons with an empty orbital here, so the LUMO is going to be on this side of the molecule, and we put a pi donor here with a lone pair, so the HOMO is going to be on this side of the molecule. When we promote an electron from the HOMO to the LUMO, of course, what we do is we basically move an electron from here over to this side of the molecule, and we generate a very large dipole moment in the excited state, even though in the ground state, there's almost no dipole moment. In fact, the dipole moment would be pointing in this direction from right to left in the ground state because nitrogen is more electronegative than boron. In the excited state, it's strongly in the other direction because we've made this kind of anionic and this cationic. Now, what you can see if you look at the compound in solution, under ordinary light, you see that they're all basically just the same slightly yellow colored solution with absorption in the edge of the blue and into the violet. But if you put them on a UV light and look at the fluorescent emission, what you can see is strong solvatic chromism. That is, as we go from nonpolar solvents such as hexane towards polar solvents such as DMF or acetonitrile, you see a huge shift in the color of the emission. And you see that reflected in the emission spectra. So we can span almost the entire visible spectrum just by changing the solvent in which we dissolve the compound. And why is that? Because the polar excited state is heavily stabilized by the polar solvents. And thus the emission energy to the ground state, which is not stabilized, in fact, destabilized in the polar solvents, becomes much, much, much lower in energy, okay? All right, so that's an interesting proof, and we'll come back to that compound in a minute. Now what I want to tell you about is another optical process. It's a nonlinear optical process, and it's called two-photon absorption. So I'm sure you're all familiar with the fact that, if you absorb a photon, generally you do a transition from the HOMO to the LUMO. Not always the case. It follows Beer's law. Absorption is linear in the intensity of light. But in fact, it is actually possible to absorb 2 photons simultaneously, for example, at half the energy, to reach either the same excited state or a higher excited state. So that violates the basic rules that you probably learned in school about absorption, but indeed it is quite possible. And it has a number of very interesting applications. And we're going to focus on 2-photon excited fluorescence. So instead of a 1-photon excitation, we're going to excite with 2 low energy photons. We're going to reach an excited state. We're going to get fluorescence the same way we would if we excited with 1 photon. But what's the advantage of 2-photon absorption? And that is 3D spatial resolution. It can be excellent down to the micron level. not only in the 2 dimensions of the laser, but in the depth dimension. That has a lot of importance in biological imaging, high resolution biological imaging, especially because we can use this near infrared window in which biological tissues and most compounds do not absorb very strongly. That gives us deeper penetrations into cells and into tissues. We can also use it for localized photodynamic therapy, that is optically induced, that is a laser induced killing of very specifically of cells. Now, if you have someone with a problem in their eye, particularly called macular degeneration, a common problem in older people, and you want to selectively kill cells by shining a laser at their eye, you don't just want to burn a hole through the back of their head. You only want to absorb the light at the cells that you want to kill. So you need excellent 3D spatial resolution. Now, I won't go into the other processes in detail that you can do, but here's the basic simple diagram. So this one photon absorption, you simply absorb a photon, you go from a ground state to typically a singlet first excited state. And you can then emit a photon, and that's called fluorescence, okay? On the other hand, you can absorb 2 half-energy photons, or slightly more than half-energy photons, and depending on the symmetry of the compound, you can either go to the same excited state or the higher excited state S2, from which you rapidly decay back to S1, and then you get fluorescence from the same excited state that you did here. Now, what are the rules? The rules are that if you have a dipolar compound, the donor acceptor, like the one I showed you, you can absorb 2 half-energy photons and go to S1. But if you have a centrosymmetric molecule, a quadrupolar molecule with an inversion center, S0, S1 is forbidden, so you have to go to S2, relax to S1, and then emit. So what's the interesting thing? The interesting thing, of course, is that since you have to simultaneously absorb 2 photons, like a second-order chemical reaction, the absorption is proportional to the square of the intensity of light. So it's not linear in the intensity, it's proportional to the square of the intensity. Now, if you focus a laser beam on a sample, as is shown in the bottom part of this slide here, or in this one here, so this is normal excitation of a simple chromophore with UV light. Here is the same excitation, but in the near infrared, so absorbing 2 near infrared photons, focused on a point in the center of the cuvette, and you can see this little tiny dot. And you might ask, why the little tiny dot? Why this depth resolution? And that is because not only is the 2 photon absorption dependent on the square of the intensity, but the intensity is related to the square of the distance. It falls off, it decreases with the square of the distance from the point at which you're focused. So what that means is that the 2 photon absorption will decrease with the 4th power of distance. And that's what gives you the depth resolution. And you can see the little tiny blue dot here, which is the emission from our simple donor acceptor borane excited in the infrared. So we're using infrared light, we're getting blue light out. 2 photons go in, 1 photon comes out. Okay, so it doesn't violate conservation of energy, but it gives us exceptional depth resolution in all dimensions. So we're going to apply this to cell imaging and related processes. And we want to use this near infrared window because most biological molecules like hemoglobin and the like have very little absorption here. They have very strong absorption in the UV and into the visible, but as you go into the near infrared, this dies off. So we don't have a lot of background. We don't do a lot of damage to biomolecules, and we don't have a lot of background luminescence as well. Okay, so here are the molecules that we looked at first. So we designed a series of molecules with increasing numbers of thiophene in the core and these BMES2 groups at the end. Initially, we call them V because we put these vinyl groups here. These are simple to make by hydroboration of the alkynes with HBMES2. This is a very simple reaction. So we generate these trans double bonds at both ends of the molecule. So we made the one with 2 vinyls, 3 vinyls, 2, 3, 4, 5 thiophene with the vinyls at the end. Then we made one here with just the thiophene and no vinyls. And we made also one with an E dot, which is a strong donor. So these are quadrupoles because they're basically centrosymmetric molecules. And here's a good example of a crystal structure. It's just one with four thiophenes and the vinyls. And you can see that the pi system is basically planar. And there's a bit of a twist here because of the steric hindrance of the BMES2 groups. But the angle isn't too bad. It's in the 20, 30 degree range. And so we get pretty good conjugation along the whole chain. But it is centrosymmetric. In fact, this one is crystallographically centrosymmetric. So if we do a 2-photon absorption, we will not absorb to S1, we will absorb to the S2, the second excited state by symmetry. So here are the absorption and emission spectra. You can see that as we increase the length of the spacer and the conjugation, that we redshift the emission significantly. And the one with the E dot in the middle is particularly redshifted. Now, to give you an idea, these absorb strongly. This is all 1-photon absorption. These are the molar extinction coefficients, and they range from about 50 to about 100,000. So these are strongly absorbing compounds in the blue, blue-green to green, almost green in the 1-photon absorption. The Stokes shifts, that is the difference between absorption and emission, are moderate. And the fluorescence quantum yields rise to about 25% or so, and then stay stable as we increase the chain length. So that's also quite good. Now, I mentioned that whether we excite to the first or second excited state, there's a very rapid relaxation to S1. This is known as Koch's rule. And almost all compounds emit from the first excited state, regardless of which one you populate initially. There are exceptions, but most do. And here's an example of one of our compounds. This is the emission spectrum, and the black line is excited at 400 with 1 photon, 400 nanometers, and the red line is the emission spectrum excited with 2 photons at twice the wavelength. So you can see they're exactly the same. So regardless of whether we excite to S1 or S2, we emit from S1. Now, the next thing about 2-photon absorption, I mentioned is directly proportional to the square of the intensity of the laser. And if you plot the log of the fluorescence intensity versus the log of the laser power, what you get is a straight line with a slope of exactly 2. Okay, that's F proportional to I squared. So these are unquestionably 2-photon absorption, 2-photon excited fluorescence. Now, I also told you that for a quadrupole or centrosymmetric molecule, you will actually absorb to S2 and not S1. So what I've got is a couple of the absorption spectra. In black, you see the 1-photon absorption plotted on a normal wavelength scale. In these blue dots, what you have is the 2-photon absorption spectrum plotted on twice the wavelength scale. Now, if we were absorbing with 2 photons to S1, to this state, these two curves would overlap. And you can see that the blue one is shifted to higher energy and is actually at a minimum here. So that implies that we are not absorbing to S1 with 2 photons. We are absorbing to probably S2. Okay, nonetheless, we still emit from S1. So this is just a plot of the 2-photon absorption. The units are called Geppert-Meyers after the physicist who proposed the 2-photon absorption effect in the 1940s. She really had a very good idea in mind, and it wasn't until somewhat later that people demonstrated it. But then the units, Geppert-Meyers, are named after her. And what you can see is that, as you'd expect, there is an increase in the 2-photon absorption. This is basically like an extinction coefficient for 2 photons, that the TPA, 2-photon absorption cross-section, goes up, but it plateaus around 4 of these units between the 2 borons. So no need to make anything longer than that. So here are the compounds we made, the vinyl and the one without the vinyl groups. And you can see here, for example, with this one, that the 2-photon absorption cross-section is over 1,500 of these Geppert-Meyers. And all I can tell you is that that's a big number, okay? So that's a very efficient 2-photon absorption. Now, we wanted to use these for cell imaging, but of course, these are hydrophobic, okay? These are extremely hydrophobic. So the question is, how do we get them into water? Well, we took a trick that we learned from Francois Gabay, who I believe will talk to you either tomorrow or Wednesday. We used a trick that he developed, and what he did was he took the Paris substituent here and changed it from a methyl group to a trimethylammonium cation. And as you increase the number of these trimethylammonium cations, you actually do two things. One, at 2 of these units, you begin to get water solubility. You get more with 3 units. That's the first thing. But the second thing that's rather interesting is that because these are cations with electronegative nitrogen and a positive charge on it, what you do is you actually make the boron a better and better pi acceptor because you have a strong inductive withdrawing effect of these ammonium groups. So what we did was we just made this compound quickly with 2 thiophene and these trimethylammonium substituted boron mesodyl units. And we checked for water solubility, and it was pretty soluble, greater than 5 millimolar, which is way over what we need for imaging. But even though normally in air and in organic solvents, these are quite stable, in water solution, what we could see in the absorption spectrum was a decrease in the intensity and new peak growing in as a function of time over a matter of 30 minutes, an hour, several hours. And we need to think to be stable for about 48 hours for imaging. Hello? Okay, so what we did was then we went back one step and we inserted this xylyl ring so we could get another 2 orthomethyl groups around the boron. So now we have 6 orthomethyl groups around the boron. Our chain is a bit longer. Even though there's a twist here because of the sterics, we get excellent water solubility, 14 millimolar, and the compound is absolutely stable in aqueous solution for 48 hours. So how do we make these things? Well, we take the amino substituted bis-xylyl BF compound, lithiate this material, stick it on here, and then we use the trick. We use the same trick we used for pyrene, which is the sterically directed direct CH borylation. And we put in a pinnacle boryl group here, and then we do a Suzuki-Miura cross coupling. And once we have this, we can attach any dihalo system to our compound. So in this case, we use the dibromo dithiophene. Okay, so how does it work? It works quite well. First, the interesting thing is we get a pretty good fluorescence quantum yield, 41 in acetonitrile, drops to 10 and 10% in water, but that's still pretty good in water. So the thing is still pretty emissive. What you can see is that the 2-photon cross-section of about 700 Geppert-Meyers is also pretty good. And again, you can see that absorption is taking place not to S1 strongly, but to S2, emission still coming from S1. And the interesting thing is that these compounds are non-cytotoxic to cells. The cells don't mind them at all. They're not toxic, up to concentrations as high as 100 micromolar, way over what we need. We can do imaging in the 100 nanomolar to 1 micromolar range. And so here, the 2-photon excited fluorescence, that's 1 photon, 2-photon excited fluorescence. You can see they're the same. And this is a localization study where this is our compound in these cells. And this is a compound, mitotracker red, which is known to localize in the mitochondria in the cells. That's the cell organelle, which is responsible for energy production in the cell. And what you can see if you overlap this image with this image is that they're pretty close. And therefore, we have some degree not great, but some degree of localization of our dye at the mitochondria. We can image the mitochondria with our dye. In fact, we found later that it ends up in other places in the cells as well, but it certainly does go largely to the mitochondria. Okay, so if we compare our compound to the commercial mitochondrial imaging agent that you can buy, you will see that theirs you're supposed to store at -20 and protect from light. Ours is bench stable. Ours is about 14 times more soluble in water, and it's definitely more photostable and more water stable. Okay, it's definitely more water stable than the commercial dye. Okay, so this is looking good. And with this in mind, what we did was we decided to play around with the pi bridge. So instead of 2 thiophene, we decided to cross-couple our xylol material to several other conjugated chromophores. So here's pyrene, biphenyl, here's a flattened out fluorine, and here's carbazole, and here is a very interesting thing, dithienol system here, pyrrole. This is a very, very, very interesting chromophore. And so we inserted this in between the 2 aromatics here, and you can see that we can essentially cover the visible spectrum in terms of emission just in the same solvent, acetonitrile, just by changing the core of this. And you can also see, for example, for this one, that it's severely redshifted from the others, which is a good thing. The fluorescence lifetime is quite short, only about 3 nanoseconds. And the quantum yield is almost 60%, 55, 56%. Okay, so we're going to focus on this one first. The other thing I just reiterate is that these 3 are centrosymmetric, whereas these 2 are bent. So these do not have an inversion center. So in these cases, the 2-photon absorption to S1 is allowed, and you can see the overlap of the 2-photon absorption spectrum with the 1-photon absorption spectrum. So in these, we excite to S1, but in these, which have a center of symmetry, as before, we excite to S2. We do not excite to S1, we excite into S2. Okay, so what about the 2-photon cross sections? They're reasonable, moderate for most of them, but exceptional for this one. 4,500 Geppert-Meyers. That's 3 times the best of the thiophene, 2 to 3 times the best of the thiophene with this chromophore. So we decided to explore these and compare them to a different dye, this dye, because what we found was that these were not going to the mitochondria. These go to lysosomes in the cells. These localize very efficiently. So this is the overlay of our dye with the commercial lyso tracker, lysosome imaging agent. The overlap is excellent, leading to a Pearson value of 0.81. So 1 would be 100% overlap. So this dye now, our new dye with the thienols and this pyrrole in the middle of it is taking our material to the lysosomes. That's an important cell organelle where most of the cell waste is disposed of. Okay, so that's what collects the, if you like, the trash, the garbage in the cell, and brings it to the outside, destroys it and brings it to the outside of the cell. Okay, here's the 2-photon excited fluorescence imaging, exciting our dye at 720 nanometers and emitting slightly above there. So that's quite interesting. And again, the cytotoxicity is very good, is almost no cytotoxicity up to and beyond 10 micromolars. And we only need 1 or less micromolar for imaging. So this is looking pretty good. And we were also able to show that our dye is more photostable than the commercial lysosome imaging agent, which is also interestingly a boron compound, but it's a BODIPI type system. And for those of you of the biological interest, we have also been able to show that the method in which the compound penetrates through the cell membrane from solution is called endocytosis. Okay, so I'm coming sort of towards the end. I still have a few more minutes, I think. So what I want to tell you is that we've explored this in some detail. We've published quite a few papers on this now. We also explored the dipolar systems, and I don't know how well you can see it, these trigonal compounds, octopole, they're called octopoles, and the octopolar system that has a nitrogen donor in the middle and 3 branches around the outside with these NMe3+ groups around the borons on the outside. These are very effective. The octopole is particularly good in terms of cell viability and also highly increased 2-photon cross-section. So very efficient dye. The other thing we did was to explore exactly, because we know if we put the thiophene directly on the boron, the system isn't water stable. If we put the xyl group on the boron, it's very water stable. We explored other groups, including anthracene. You saw, I think, you saw an example of an anthracene boron from Tiligar this morning. In fact, it was the Yamaguchi group that developed trianthroboranes some years ago, and anthracene is pretty good, as Tiligar pointed out, at protecting this. So if you want to know about what exactly you can put in here to trade off between stability versus pi conjugation, because they tend to twist a little bit when you put bulky groups, you can read this recent paper. Okay, I don't know how much time I have left, but I'll just tell you that in collaboration with a couple of groups in Zagreb, Ivo Piantanidis group, Sonia Tomek, and Jelka Ban, we've begun to explore other properties of our compounds, just the dithiophene one initially, more systems more recently. And what we were able to show was that we could bind the chromophore to DNAs, RNAs, and proteins, and that there was a distinctly different fluorometric response to DNA and RNA versus proteins. So we could actually measure DNA and RNA in the presence of proteins or vice versa. A rather interesting thing, and we have been exploring this now in some detail with other molecules. So I just give you an overall conclusion. We can make centrosymmetric quadrupoles, we can make octopoles, and we can make dipoles with these dimethyl boron or related groups. These have been easy to synthesize. They're very efficient acceptors. Pi acceptors make highly luminescent compounds which exhibit pronounced sulfatochromism, at least the dipolar ones, not the quadrupolar ones particularly. They have good nonlinear optical properties, including 2-photon absorption. We can reverse the order of LUMO and LUMO +1 in pyrene, for example, by putting these BMES2 groups on and isolate radical anions and dianions. We can make various devices, OLEDs and other devices, use them for 2-photon excited emission and for the imaging of cells, as well as sensing of DNA, RNA, and proteins. If we fluorinate them, the tris-trifluoromethyl, this has a very good effect on not only on the stability, but it also drops the reduction potential by about 1 eV because of the electron withdrawing power of the fluorine. So that's an area we've explored in detail. And we can make even borols that are normally very unstable. We can improve their stability by a factor of 600 with respect to hydrolysis by just employing a single one of these fluoromers groups. Okay, so am I out of time yet?
You're on time. Perfect.
How much?
You're on time.
On time. Okay, so I will just flash through a couple of slides quickly without discussing them in detail. That's my group, or at least that was before the pandemic, when we could actually stand together outside. All right, and this is the beautiful city of Würzburg, right along the River Main. Those of you who like drinking wine, I can tell you this is the largest wine producing region in the country. And this right behind the central train station for the city, these hillsides are covered in grapes for wine production. So do I have about a minute or two, or am I at my limit? I'm at the limit.
You can use a couple of minutes, please.
Well, I won't go through. I just will flash through a couple of things. No, maybe I won't. Why don't I just stop here and let's try and get back on schedule. So with that, I thank you guys all again for inviting me to participate, and I will stop my talk at this point. Okay.
Thank you, Professor Madhav. Thanks for the wonderful lecture. So now the platform is open for discussion and questions, please. Yes, Thilagar.
Yeah, Todd, thanks for the beautiful lecture. It's very nice.
Hi, Thilagar.
Beautiful. I have a couple of queries. One is about the redox chemistry of your pyrene boron derivatives.
Yes.
One with monoboron and another one is diboron. So the one with the diborane, in the sense 2 boryl units, is it?
Yeah.
Exactly here. Yeah.
Oops.
So if you compare the redox potential of these compounds with the parent pyrene.
Yeah, it's significantly shifted to lower energy, right? It's much easier to reduce these than pyrene.
Okay, here you can get 2 different redox couples for the second one.
No, you don't get 2 radicals. When you do 1 electron reduction, the electron is completely distributed across the whole molecule.
Okay.
Okay. So when you do a 2 electron reduction, both electrons are distributed into basically this new LUMO, which is this one come down. Okay. And the molecule is diamagnetic, although our calculations show that there is a degree of open shell singlet character.
Yeah, that's what I wanted to ask you. I mean, there will be a possibility of a triplet. So
no, it's actually a singlet, but there is a degree of open shell singlet character. So it's a singlet, and so it's diamagnetic.
Okay. Is there any temperature dependent studies on this one? Is it possible to flip it?
No, I don't think we did any temperature dependent studies on this one.
In the last section, you discussed about biological applications of your compounds.
Mm-hmm.
Yeah, I mostly use a triplet as a counter anion for your cation.
Say again?
Mostly you are using triplet anion as a stabilizing agent, right?
Triflate, yes. We use triflate as the counter ion because we prepare the compounds from the amino precursors by alkylation with methyl triflate.
Yeah, but is there any studies on counter anion dependent uptake of this compound?
Yeah, it doesn't seem to have much effect. I mean, the point is once it goes in the cell, you're going to end up with a mixture of anions. Okay, but what was interesting to us was that the triflate gives it very good water solubility, and at the same time does not cause us any cytotoxicity problems. Okay, so we have generally stuck with the triflates for virtually all of these. In fact, if you go to this octopolar system, this is a 6+. The trigonal octopolar system has 6 of these NME2 groups, and that's still fine, quite soluble, and in fact has very low cytotoxicity. So the triflate seems to be fine.
Oh, okay. It's very interesting system. Thank you.
Anukul?
Yes. Yeah, Professor Mara, this is Anukul from TFR Hyderabad.
Sorry, could you say it slowly?
This is Anukul from TFR Hyderabad.
Yes, Hyderabad. Yes,
Yeah,
thank you.
Yeah, so I have a question, the continuation of the first question of the Tilagar. So I can see the pyrene bridge 2 boryl unit. When you reduce, it's a closed cell. Even also like there was a report with a anthracene bridge or thiophene bridge, also closed cells.
The anthracene compound was made by another group,
Yes,
and
another group, like a thiophene by Holger group and anthracene I forgot. And but there is also compound by Kaim group. They did not mention about the electronic property. But
well, okay, you can read the original papers, but
yes.
So I think they made the dianion electrochemically.
Yes.
So they measured the redox potential, but I
Yes.
think that should be diamagnetic as well.
Yes.
And the anthracene derivatives was made by a different research
Yes.
group just after we, maybe 6 months or a year after we published the pyrene. There was an Angewandte paper on the anthracene compound itself. This BMES2 anthracene is our compound. We published it 25 years ago or something like that. And another group reduced it the same as this in 2016 or so.
Yes, yes. Yeah, Professor Mada, but on the other hand, I see you have a multiple thiophene bridge diboryl compound.
Yes.
So in that case, there is a spacer is longer. So maybe what could be the implication if we reduce that compound?
Okay, we
like
did not,
these-
I don't know, I don't remember whether we studied the reduction of these neutral ones. Okay, we did look at the reduction of the cationic ones. In fact, you can read, I didn't mention, we published a paper this year where we made the monocation, the dication, and there are two of those. You could have the cations on the same side or on opposite sides, and the trication and the tetracation, and compared all the reduction potentials. We published that a few months ago, maybe June or so, in Chem European Journal. So if you want to look at the redox chemistry of the cationic ones, that's discussed in detail in Chem European Journal 2021. Serena Berger is the first author on that.
Yeah, I will look into it. Yes. Thank you, Professor Mada.
All right,
Okay.
thank you again, Professor Mada.
So
Yes.
This
Yes,
person
please.
here, Serena, did all the mono, di, and trications, their redox chemistry, their photophysics,
Yes,
and cellular work. 2021. Yeah, this year.
Yes, thank you.
Okay.
Thank you.
Thank you, Professor Mada. Thank you for this
Thanks very
wonderful
much.
lecture. So we move on to the next lecture by our by my colleague and a good friend, Dr. Ajay Venugopal from IISER Thiruvananthapuram. Ajay, yeah, I do see you, yes. So Dr. Ajay Venugopal has joined IISER Thiruvananthapuram in 2016, and since then he has made significant marks in exploring the potentials of antimony and bismuth as Lewis acids in catalysis. So all of us, particularly myself, having recent interest in heavier nitrogen chemistry, we look forward to your talk. Dr. Venugopal, please go ahead. You are muted.
Can you hear me?
Yes.
Yeah, thank you very much, Dr. Majumdar, for the kind introduction. I will start sharing the screen before I start my talk. I hope the screen is visible.
Yes, it is.
Yeah. At the very outset, I would like to thank the organizers of the conference from NICER Bhubaneswar, Professor Dr. Krishnan and Dr. Sharanappa, for inviting me for this conference, and also all the other friends from NICER Bhubaneswar. So today I will be presenting some of the latest results from our lab on antimony and bismuth Lewis acids, and also their application in catalytic hydrosilylation reactions. So before I start the talk, I would like to briefly tell something about my institute. Thiruvananthapuram, which is located in the southern tip of the country, and we have a very beautiful campus, and you are all welcome to visit over here. And we also have an excellent lab to perform main group chemistry research. So I would like to acknowledge many people here who have helped to do this research in the last few years. I would like to thank all the funding agencies, starting from ICER, who have been very generous in providing funds to undertake all this research. And then I would like to thank my current group members who have been deeply involved in this type of research. Of course, the alumni and our collaborations with Professor Gemmes from Bangalore and Laurent Meron from France, and also Dr. Babu Varghese, who was at IIT. Cations and dications. We look at their Lewis acidic properties to enable them to facilitate them use in catalysis. And in particular, we are looking at hydrosilylation reaction, activation of SiH bonds. And we try to isolate many of these reaction intermediates and elucidate the structures by solid state structure XRD, X-ray diffraction analysis, as well as NMR. And we also do mechanistic investigations of some of the reactions.
Is Ajay frozen? The organizers?
He is frozen.
Okay.
I think he has some internet problem, seems.
No, we are fine.
Krishnan, do you want to give a message to Ajay that he's frozen?
Yes, sir.
Can you hear me? Hello?
Yes, Ajay.
Yeah, I think
I
have a weak internet here. To save the bandwidth, I will switch off my video and go to the talk. Is that okay?
Yeah, absolutely fine.
Dr. Majumdar, can you hear me?
Yes, I can hear you.
Yeah, fine. Oh, yeah. Sorry for the interruption.
No worries. You can turn off your video if you think so with the internet issues.
Yeah, that would be yeah. So we try to deal with reactive cations, and we employ weakly coordinating anions to charge balance these cations, and we work with weakly nucleophilic solvents to enhance the Lewis acidity at these p block element centers. In the activation of CO bonds, and we have worked with aldehydes, ketones, carbon dioxides, and so where we have seen, for example, here in the first case, we have accessed an aluminium cation, which actually dimerizes aldehyde to corresponding ester, which with record-breaking turnover frequencies. At the same time, we can use the same catalyst the elementary reactions of these mechanism of the zinc hydride mediated carbon dioxide reduction. And also we have been interested in the electrophilic magnesium compounds. We have prepared these propeller type cationic magnesium compounds and try to understand some of the reaction mechanisms involving hydroboration reaction. But today I will be talking about the Lewis acidity of heavy elements. In particular, as the title tells, I will be explaining you something about antimony and bismuth compounds, which we have been working in our lab since the last few years. So the salts of antimony and bismuth are considered to be Lewis acidic, and organic chemists employ them in various organic transformations. And the concept comes here. It was actually Alcock. It was Norman who actually in 1990s who tried to quantify the Lewis acidity, and he was basically looking at these pnictogens, in particular bismuth and antimony, and he brought in this concept of primary and secondary bonds to especially to bismuth and antimony. And if in principle, if you have a bismuth chloride, for example, each of the bismuth chlorine bonds has a trans position, which is a site of electrophilic attack by a nucleophile. So with this in concept, many people have used these salts for various catalytic processes, and we were basically interested in using them, trying to achieve molecular compounds so that we can try to understand the snapshots of individual reaction pathways. So this was one of our first works which we tried to do. What happens? How do you quantify the Lewis acidity of these simple salts like trichloride salts of bismuth and antimony? What we try to do is take bismuth trichloride and antimony trichloride and treat it with minimum amounts of triethyl phosphine oxide, which is a Lewis base, and then you try to monitor the 31 phosphorus NMR and see what is the deshielding of the phosphorus signal, which is an indication of the Lewis acidity at these centers. So we found out that as much of the literature tells that bismuth trichloride is more Lewis acidic than antimony trichloride. And we also performed some solid state structure analysis where we introduced the ligand. This is a beta diketiminoate ligand. Of course, you can introduce any ligands here and try to understand this, but we were fortunate enough to get structural details of these adducts of antimony trichloride and bismuth trichloride, where you have weaker bonds with antimony oxygen as compared to the bismuth oxygen. So hence, we came to know that bismuth trichloride is more Lewis acidic than antimony trichloride, both in solution as well as in the solid state. Having looked at this, we thought of accessing molecular bismuth compounds and antimony compounds where we can actually look at the Lewis acidity at a very molecular level, because all these halides tend to redistribute in solution, and one never comes to know what is the active species in a catalytic reaction. So what we did was we took this basic model, which was designed by Norman in 1990, and we tried to choose a ligand which will fit into these orthogonal positions of the primary bonding. So we chose a tris pyroxolyl borate ligand, which is a tridentate nitrogen donor ligand, which easily fits into this position. And we wanted to have this ligand coordinated to the bismuth center. So if you try to do this, you end up accessing a dication. Okay? And this should be sufficiently reactive, and we wanted to have to look at into the reactivity studies of these dication. In fact, at this point of time, because this is a 6-electron donor, we try to compare it with the cyclopentadienyl ligands, analogs. And in fact, cyclopentadienyl is a soft donor as compared to the tris pyrazolyl borate. And hence, we thought that this could enhance the Lewis acidity at bismuth center. Before we moved on, we also looked into some of the literature where people have problems in accessing dicationic species. So these are some of the instances there. It is very difficult to remove a second chloride from the bismuth center, and you see lots of decomposition. And even there is a second example when Schulz and co-workers actually tried to access a dication, and they resulted in decomposing the bismuth compound into the elemental form. Recently, Chitnis and co-workers have tried to again access the dication, and however, they report that this is thermally unstable and it is characterized only in solution. So our strategy, actually, this is a long story which I am telling you in a short way. We took bismuth trichloride and treated it with the potassium salt of the ligand and got the dichloride. And we had several failures in actually abstracting the two chlorides from the bismuth center. And finally, we used the silyl cation to pluck the two chlorides to get this dication. It's thermally stable, except the fact that it is highly sensitive to air and moisture. And you see that we have actually satisfied our initial hypothesis, where you have 3 vacant sites and then you have 3 primary bonds, and the 3 nitrogens of the ligand fit into these positions. And you can see very short coordinate bismuth nitrogen distance of 2.1 to 2.3 angstroms. Jemis and co-workers performed DFT calculations, and they arrived at the molecular orbital picture, which actually tells the origin of Lewis acidity with 3 orbitals. 2 of them are actually degenerate, and there is which are pi in nature, and the third one is sigma in nature. And this is the source of Lewis acidity. And we also came to know that the bismuth center has a nearly dipositive charge, and the covalency of the bismuth nitrogen bond is just nearly around 50%. So it's highly ionic, and the Lewis acidity at the bismuth center is preserved. And the Weberg bond index also told about the ionicity of this bond. Having established the structure of this compound, we tried to look into one of the catalytic reactions which is challenging in the literature, and we chose olefin hydrosilylation as an example, and we could perform olefin hydrosilylation of various olefins, and we came to know that this was highly efficient, and this was actually occurring via an SiH activation. And this requires very low, relatively low catalyst loading, unlike, and also it's relatively inexpensive as compared to the expensive platinum catalysts which are traditionally employed, and all the catalytic reactions happen at room temperature without any side reactions. Usually with the transition metals, you see polymerization, oligomerizations, and other undesired reactions happening during olefin hydrosilylation. So we were successful in demonstrating the Lewis acidity at bismuth, and this till date, this is one of the benchmarks of highly reactive bismuth compounds so far known in the literature. Having learned that, we try to think of other dicationic species where we can have multiple Lewis acid sites and perform such catalytic reactions. So we started with an organic group now here with an aryl group, and which has a pendant arm of this nitrogen donor, and we initially got this dichloride and treated this with the silver salt to abstract the chloride, and now you get a ligand adduct of the dication. It could be trapped as a phosphine oxide adduct, and we could actually crystallographically characterize this compound. Nevertheless, this is a dead compound. You cannot do anything because it is coordinatively saturated, and the Lewis acidity at bismuth is quenched. Nevertheless, it tells us that this bismuth center can be employed for actually coordinating multiple ligands. At the same time, we got the theoretical calculations done by Jammis and co-workers, who actually came to know about the 3 positions of Lewis acid sites on the bismuth center, and you can actually successively add 3 ligands to this Lewis acidic bismuth center. We further used this dication. We generated this in situ and performed aldehyde and ketone hydrosilylation. This was highly efficient, and as you see, for simple aldehydes, it goes up to 50 per hour turnover frequency, and in the case of benzophenone, it reaches up to 200 per hour. And we were also able to perform both aryl and alkyl ketones and aldehydes because this is one of the challenging things. Most of the catalysts are quite good at performing hydrosilylation of aryl ketones, but here we could do for both alkyl and aryl substituted ketones and as well as aldehydes. The next question was, what is the active catalyst? Because we were always mentioning this L. Can we come to know the nature of the catalyst? Of course, yes. We tried to make a tris aldehyde adduct of this bismuth compound, and we could actually isolate the compound as a tris aldehyde adduct, and we got the solid state structure solved with short bismuth oxygen bonds ranging from 2.26 to 2.33 angstroms. We further wanted to have a look into the solution properties of this compound, and we could actually see the deshielding of the carbonyl signal, a good indicator of Lewis acidity at the bismuth center. And as you go on increasing the aldehyde concentration, the aldehyde binding to the bismuth center keeps on exchanging, and this is highly dynamic in nature. So we came to know the active species as well as the nature of the bismuth oxygen bond, which is highly dynamic, which is a good way to have a catalyst where you can have something as an incoming nucleophile and going out as a product. We later actually wanted to look at single sites. This is one of the works which we did in 2017, where we came to know that the ligand bite angle, a parameter which is commonly used for transition metal compounds, can be actually successfully used in case of main group chemistry. And we came to know that the 4-membered ring is more Lewis acidic than a 5-membered ring. Okay, and you can also see the bite angle here, where you see the shorter bite angle in the case of 4-membered ring as in the case of 5-membered ring. We performed a test with a base, and we could establish in solution that the 4-membered ring is indeed more Lewis acidic than the 5-membered ring. But things start changing. Okay, so we went one step before. Okay, and we started looking at some of the compounds which are well established in literature. Somehow they have not caught the attention of Lewis acid chemists, and people have not looked in fine details, finer aspect. So we started with very simple compounds, a bis-aryl adduct of antimony chloride and the bismuth analog. And we came to know, as expected, the bismuth compound is more Lewis acidic than antimony. But then once you replace your chloride with a triflate, there is a flip in Lewis acidity, where the Lewis acidity shifts from bismuth to antimony, and now you have the antimony triflate, which is more Lewis acidic than the bismuth triflate. So this has to do with the nature of the primary bond, because your chloride is a strong donor and your triflate is a weak donor. And once you have a weak donor, the scenario changes. So Lewis acidity now needs much more revision for the pnictogens, and one needs to talk about Lewis acidity depending on the nature of the ligand environment around it. So we did the structural studies, we made the triflate and the phosphine oxide adduct, and when we actually looked into the solid state structure of the triflate of the antimony compound, you have a primary bond which is a triflate, and you have a secondary interaction with the neighboring triflate anion, which are long distance of 2.78. When you are looking at the antimony center, which has bound to the phosphine oxide. Okay, and this scenario reverses, and hence you come to know that your antimony becomes more Lewis acidic than bismuth. So we wanted to use this strategy to perform and to actually, as a proof of concept, to perform a deoxygenation of phosphine oxide, which is one of the important reactions while doing the Wittig reactions. Okay, and we took the phosphine oxide and we actually took both the antimony as well as the bismuth compound, and we could successfully deoxygenate the phosphine oxides to the corresponding phosphines. And this could be performed for a variety of substrates, and this happened, the efficiency of this catalyst is comparable to many of the other benchmark compounds reported in the literature. However, we could not activate carbonyl bonds using these triflate compounds. That means you need much weaker ligands than triflate at the antimony center if you want to bring in substrates like aldehydes, ketones, or esters. So what we did was we, instead of the chlorides and the triflate, we now introduced a neutral nitrogen donor ligand, and as expected, the Lewis acidity is reversed, and you see that the antimony compound is more Lewis acidic compared to the bismuth compound. So this was confirmed by doing the Guttman test by treating the respective Lewis acids with triethyl phosphine oxide. We further went one step ahead and we tried to see, this is the most interesting thing. We were quite lucky enough. One of our co-workers, Ms. Deepti Sharma, was very successful in making lots of compounds with varying one of the ligands trans to the nitrogen. And once you do this, you get systematic data both in the solid state as well as in the solution, and you can actually establish a trans effect series here. You see that you have a chloride which is very strong, and as you keep decreasing the strength of your base, your the antimony nitrogen bonds get stronger and stronger. This is actually very well evident by the decrease of the antimony nitrogen bond from 2.16 angstroms to 2.42 angstrom. So in principle, this is the trans influence series, which is a very common series when ones deal with transition metal complexes. We then wanted to see what is the effect of the series and its implications in catalysis, because you can generate all these things. Most important is whether you can really apply this for a catalytic process. When you see at the extreme end, you have a ketone binding to the antimony center. That means we can use this in some reactions where you can actually activate carbonyl ligands. We parallelly synthesized a few of these compounds with the 5-membered ring, and we came to know that as you go from the, so there is a curve which we have drawn here. The first curve, the orange one, is actually the one which tells about the replacement of the ligands which are trans to the nitrogen, and the blue one will tell about the antimony nitrogen bond. So the numbers here depict the deviation of the distances from the sum of the covalent radii of antimony and the elements. If you do this with the 5-membered ring, the two lines cross with each other, telling that the antimony nitrogen bond, which was actually primary in the first case, now actually is, which was actually secondary in the first case, becomes primary, and your SBX bond is, which was primary initially, now becomes secondary. To our surprise, we see with the 4-membered ring that the antimony nitrogen bond throughout remains secondary interaction, whereas your SBX, even in the case of your carbonyl, is actually still a primary bond. This means that you have a very good chance of activating such carbonyl species at the primary sites, primary bonding sites. So we further looked into the chemical shifts, carbon chemical shifts of many of the carbonyls, like your benzaldehyde, benzophenone, and an ester. And we came to know that the carbonyl gets more activated or deshielded in the case of the 4-membered ring. This is consistent with aldehyde, ketone, and ester. And you see that, for example, benzaldehyde from 192, it is deshielded to 201. Benzophenone, you see up to 208, and the 5-membered ring is somewhere in the middle. And same with the case of the ester also, where you do not see any significant deshielding of the carbonyl with the 5-member, whereas you see deshielding, appreciable deshielding with the case of the esters in the 4-membered ring. So this is some of the latest result from our lab. This is all unpublished result. I wanted to excite everyone with these results. We have actually ventured into this area of carbon and olefin metathesis, where we could now actually activate the carbonyl compounds and actually treat this with olefins and do a metathesis. There are some of the main group salts like aluminum chloride, gallium chlorides, which are known to do this, but the area is still in the infancy, and we thought we could venture into this area and look at a molecular level. And this is the active species in solution which activates the aldehydes, and we could successfully perform cross-carbonyl olefin metathesis involving one aldehyde and a non-olefin. This is still at the stoichiometric level, and you can even do a ring closure with stoichiometric amounts of the catalyst. And when you have to do a ring opening of the carbonyl olefin metathesis with if you have cyclopentene and benzaldehyde, the reaction becomes catalytic. The yields of the reactions go up to 40% or so, which is actually what is observed with many of the main group catalysts. So this now becomes actually a model compound to study the carbon olefin metathesis. So in conclusion, I would like to mention that the choice of the ligand and the weakly coordinating anions actually, and also the solvents, play a crucial role in isolating such reactive species. And we have tried to explore the limits of electrophilicity of these both cationic and dicationic species of bismuth as well as antimony. And we come to know that the Lewis acidity of antimony and bismuth centers are severely affected by trans donors, wherein you can try to have a trans series. And as proof of concept, we have demonstrated hydrosilylation of carbonyls and olefins, as well as very recently olefin carbonyl metathesis. So I would like to again thank the organizers of this conference for having invited me to deliver a presentation here. And I would like to again thank all the audience for their kind attention. And I would be happy to answer the questions. Thank you very much.
Thank you, Dr. Vedagopal, for this wonderful lecture. So now the platform is open for discussion. Questions, please. The questions, yeah, Adi Narayan, I find. Yeah, please go ahead.
Yeah, Ajay, Adi from IISER Barampur.
Yes, please.
Very excellent talk, Ajay. It's a very interesting, Lewis acidic antimony and bismuth compounds. Could you please go back to your this 4-membered and 3-membered? Could you comment on the stability of this 4-membered and 5-membered antimony compounds?
Both are stable. Both are actually stable, except the fact that you have to handle them under inert atmosphere. But otherwise, thermally, both of them are stable. But as you go down the series, you see that you are trying to now bind weak donors like ketones and trying to make ketone adducts. And there are very few examples of crystallographically characterized carbonyl adducts even in the case of transition metals also. So this becomes more and more labile, and it becomes a bit tricky to access. But once you access that, they are all stable under inert conditions.
Yeah. Now, if I see from different angle, this four-membered, this is 1, 2, 3, 4, and between four-membered and five-membered ring, they have different ring strains, right?
Yes. Yes.
So that's what I'm
Yes,
wondering. Maybe one of them would be relatively less stable. In many other
No,
ways.
actually, we see enhanced Lewis acidity. Due to the ring strain, we can induce more and more Lewis acidity.
Okay. Yeah, that is interesting. Good. Thank you, Ajay.
Thank you, Adi.
Shakku?
Hi, Ajay. This is Sakya.
Hi, Sakya.
Excellent talk as usual. So my question actually from the last part of your talk, probably the last slides, the olefin metathesis, the carbonyl metathesis, what you have shown.
Yeah.
So is it the 2+2 cycloaddition, or I mean, what is the mechanism? How is it happening?
Yeah, so we actually started this work to actually decipher the mechanism of this carbonyl olefin metathesis. But what we come to know that the mechanism is not so simple, because Schindler and co-workers from the United States, they are organic chemists. They have looked at aluminum chloride and gallium chloride, and they actually talk about the carbonyl activation. And we somehow get doubts, because we have actually taken lots of Lewis acids. We have started with trityle. We have done some of the benchmark Lewis acids. Surprisingly, tris pentafluorophenyl borane doesn't catalyze this reaction.
Okay.
And even trityle, and even if you take antimony chloride, nothing happens. So I think this is not just carbonyl activation, and also this may not just be a four-membered metathesis, and this is something more than that. But at present, we are just in the infancy level, and we only are looking at the carbonyl adducts. But this carbonyl, it's not just the carbonyl activation what we know right now.
Yeah. Okay. Thanks.
Can I quickly ask something? Have you tried DFT for this?
No, we have not tried.
Okay. Yeah. Thanks, Ajay.
Thank you.
Any further questions? All right, then let's thank the speaker for the wonderful lecture. Thank you so much. And I hand over to the organizers, as well as I thank them for inviting me for chairing this session. Thank you very much.
Okay, thank you, Momita. And I think we come to an end for this today's presentation. And we once again thank all the speakers and the chairs of all the sessions. And with this, we'll close today. And tomorrow we'll meet with the new link. So please join us with us tomorrow also, 8:30 a.m. Okay. Okay. Thank you all. Good night. Good evening to everyone.